Decision and control. The meaning of operational research and management cybernetics. Stafford Beer. To Cynthia. From women's eyes this doctrine I derive. They sparkle still the right Promethean fire, they are the books, the arts, the academies that show, contain and nourish all the world. Shakespeare in Love's Labour's Lost. 7. Contents. Part I. The nature of operational research. Connective summary. An initial posture. 3. On fixing belief. 17. Some dangerous precedents. 33. The wedged bear. 47. The new look. 69. Part II. The activity of operational research. Connective summary. 93. About models. 95. Models in ASPIC. 120. The formal languages. 142. A walk in the ramified system. 172. Apollo's gift. 204. Part III. The relevance of cybernetics. Connective summary. 239. About systems. 241. Coping with complexity. 270. Controlling operations. 299. Self-organizing systems. 345. Controlling enterprises. 370. Part IV. Outcomes. Connective summary. 399. 16. The outcome for industry. 401. Information and automation. 432. The outcome for government. 461. The outcome for management science. 496. On practicability. 525. Preface. This book is about management, and the way in which it may invoke the use of science to help solve problems of decision and control. Just what that means will be explained in the next several hundred pages. Who wants to know? It seems that many people are interested in these topics and would like to think them through. Most of them do not want to be blinded by science or, for that matter, assaulted by mathematics. On the other hand, those who would like to think seriously will not be satisfied with something condescendingly simple and didactic. Hence the book is written in a very definite order. In the first part there is a general and I hope lively discussion of the possibilities for interaction between science and management. It is urged that management is not a scientific topic, just as science is not in essence managerial. But the area of overlap, where the manager may draw on science, is identified. Here lies the scope for operational research. How this activity ever came to begin, and what it is really like, are brought out. This sets the scene for an investigation of its work in the second part. Part 3 continues that story, drawing especially on the science of cybernetics. And in the final part there is a discussion of outcomes for industry, for automation, for government, and for the profession of management science itself. This seems to offer a logical development, and I have tried to float on top of it a steady evolution of concepts and terms. Thus, although the book gets increasingly difficult as it goes along, the reader is supposed to have every chance of keeping pace with these. The insights which I want to communicate are not trivial ones, and they have to be fabricated of sophisticated concepts and terms. It seems to me high time that management, which is now a profession on which turns the future of every company, every country, and indeed of the world itself, should accept the need for a more advanced language than basic English. So the book is written for people who are prepared to make an attempt to follow this development, and they would be well advised not to plunge into it in the wrong order. I have tried to restrict the use of sheer jargon, and have relied rather heavily on some intricate diagrams to help out the verbal explanations, but no doubt many difficulties remain. Whether he be manager, or scientist, or someone else altogether, the reader will surely encounter ideas and words he has not met before. Whether he regards this as tedious or exciting is likely to depend on his own view of the state of the world and its need for better results. My view is this: the old ideas and words have proved inadequate for building new approaches, and without new approaches to our problems we are due to be overtaken by discomforting events. The claim for novelty in this presentation of science in management, then, is gladly and recklessly advanced, although I know it to be tactically unsound. The manager, it is often said, eschews novelty on purpose and on principle. The scientist, it is often noted, will never admit it. Never mind. If my view of these things is idiosyncratic, at least it is coherent. The main trouble with existing orthodoxy in this field is its fragmentary, partial character. We shall not be able to make a bold new stand against the troubles that beset us, armed to the teeth with one favorite sort of mathematical equation or with the solitary slogan "cut the costs." We need a larger and a rounder view. It is for those who recognize this, and who accept that thinking time is needed to formulate such a view, that I have written at such length. The book derives from over 20 years' work in this field, and all of it in active leadership of active operational research. It has taken 4 years to write the book itself, and every word has been written, rewritten, and corrected in the hours after midnight. This circumstance is made public, not to excuse the faults it may help to explain, but to emphasize that this is not an ivory tower composition. I earn my living thus, and what is written here was written in day-by-day interaction with its remunerated practice. This is how the text comes to be studied, with a great many practical examples which really happened. All of them have been altered slightly, or compounded of 2 or more real-life cases, so that no one will be embarrassed. But they are all otherwise genuine, and almost all refer to projects for which I personally have been immediately or ultimately responsible. Whenever this is not the case, the fact has been acknowledged. And this brings me to acknowledgments proper. I have made references in the text to certain people and to certain books, but in neither case does this exhaust my infinite indebtedness to others. Especially do I salute many colleagues, past and present, alongside whom I have worked, and the few close personal and professional friends, whether 11 colleagues or not, whose thinking has influenced mine. Clearly one never knows the full extent of this influence, but they should know that I am thankful for it. In particular, I am grateful to Professor Russell L. Ackoff of the University of Pennsylvania for his extensive comments on the manuscript. He bears no responsibility for anything here, but many points are the clearer because of his intervention. When it comes to acknowledging books, the situation is yet more difficult. The present volume is in no sense at all a review of management science. I felt under no obligation, therefore, to provide that extensive bibliography which is available elsewhere in any case. This feeling led to the compilation of a select bibliography, consisting of a short list of books which I felt I should like to recommend. The outcome was invidious in the extreme. It looked like the work of a censor, which I have no desire at all to be. I have left it out. In fact, many of the books which delight me most are by authors long since dead. I have rated their works for the chapter headings used as texts on which to hang some thoughts. The English quotation is often my own translation, and when it is I have done the author the courtesy of quoting his original as well. There is, finally, one other acknowledgement that must be made by name. Christine Lindsay has typed and retyped these long and difficult pages, and I thank her very much. SB 1. Part I. The nature of operational research. Connective summary. Insofar as the application of science to the process of management is an innovation, Chapter 1 considers the managerial approach to what is novel. It sounds a warning to those who have prejudged the possibilities without realizing the fact, and points to the changes that have made contemporary science a different thing, of different relevance, from its popular image. Thus not only have its potentialities in management been hitherto unrecognized, but what has passed for science in management hitherto, was not. In fact, the taking of a decision is best described as the fixing of a belief. In Chapter 2, the ways in which belief is actually fixed are shown to be based on mechanisms which, though rational, are not logical. They derive from biological necessity, not from intellectual processes, and result in decisions which have more to do with learning to survive than with the objective analysis of profitability. Industrial examples are given of the way all this works. Into this picture is now projected an account of the origins of operational research. How did it come about that real science penetrated the zone of managerial intuition? Chapter 3 answers this question, and develops from this wartime genesis an examination of the civil relevance of the work. It ends with a brief example of a famous and very early job. This job is then used to investigate, in Chapter 4 and with considerable detail, 6 major aspects of the operational research activity that are commonly misunderstood. It considers the stereotyped 2. Notions of what the scientist is like, what is the nature of the problem to be solved, what science itself is like, what sort of solution counts as appropriate, what the payoff of the study ought to be and what counts as success. It shows precisely how these stereotypes constitute major barriers to the proper understanding and utilization of this work by the manager. Finally, in Chapter 5, some of the questions raised are answered to show what scientific research can really do for management, and how this is not dependent on having all the facts available for analysis. A modern industrial study is expounded, and the 6 stereotypes are again identified and replaced with more useful notions. The part ends with a formal and official definition of operational research, and a commentary on it. 3. 1. An initial posture. There is nothing more difficult to carry out, nor more doubtful of success, nor more dangerous to handle, than to initiate a new order of things. For the reformer has enemies in all who profit by the old order, and only lukewarm defenders in all those who would profit by the new order. This lukewarmness arises partly from fear of their adversaries, who have the law in their favor, and partly from the incredulity of mankind, who do not truly believe in anything new until they have had actual experience of it. Machiavelli in The Prince. 1. How to neutralize a revolution. Machiavelli was perhaps the best 16th-century writer on management topics. He knew a great deal about the ways in which a man in authority could wield his power for the primary purpose of staying in authority. The recommendations he made to his prince were notoriously unfeeling toward those who had to be manipulated, or degraded, or indeed sacrificed in the process. But his methods were in use before his time and have been since, and for the same purpose. Only the degree to which it seems expedient that the motives and the methods should be overt or covert seems to change. When it comes to revolutions, the advice becomes especially immoral. Neither the anarchist nor the established ruler can afford many scruples when he is involved in a revolution, and there is likely to be a good deal of bloodletting on both sides. Yet some reforms are not concerned with the overthrow of power, but of ideas. Such revolutions, mounted on a purely intellectual plane, are readily dealt with as Machiavelli points out above. They do not even have to be suppressed. The basic technique 4. Is to pretend that they do not exist. As a refinement, it is more advantageous still for authority to allege that it has encompassed these ideas all along. In the 60-odd years of the present century, there has been a colossal intellectual revolution in the basic thinking of science. Basically, certainly chronologically, it began with the overthrow of classical physics. The universe of space, time, and gravitation became a different universe for the scientist after the theory of relativity became known. The particles with measurable position and momentum which populated that universe took on a different meaning for the scientist after the discoveries of quantum mechanics. The intellectual revolution of 20th century science has been accepted by the scientist, for it is proper to his work to uncover the essential characteristics of things. From that revolution has stemmed a series of new discoveries, and indeed new sciences. Atomic physics, astrophysics, a new chemistry, a new genetics, biochemistry, and biophysics are all children of a revolutionary regime. For the man of affairs, however, the position is quite different. His job is not to seek the truth, but to be the prince. He manages companies and industries, civil and military services, parties and policies, administrations and governments. He manipulates large systems of men, materials, machinery, and money. The intellectual revolution of science has largely passed him by, it does not exist for him. For the man of affairs, in Britain at least, to know much about science at all is rather unfashionable. We have heard a British Prime Minister declare that when he sanctioned the use of the atomic bomb in Japan, he knew nothing whatever of its possible effects. We have heard company directors boast of their ignorance of science, as if this automatically conferred a certificate of preoccupation with the higher things of life. So far so good. It happens, however, that during roughly the same period that we have been discussing, another intellectual revolution has occurred. This has concerned basic thinking about the nature of management and control. This particular revolution may at once be allied with the one earlier discussed. For one of the subsidiary features of the revolution in scientific thinking was the realization that science is basically concerned with investigating how and why things are as they are. Science, in fact, is organized knowledge about the world, not organized knowledge about itself. Of course, the historical origins of the subject make this clear. But it must be confessed that, to this day, the organization of our universities and scientific institutions does not make the fact quite so. 5. Plain. They suffer, as it were, from a hardening of the faculties. So the man of affairs is not altogether to blame, if, when confronted with a scientist, his first question is, "What is your subject?" It is not enough to reply, "I investigate the world." One has to be a chemist, or a physicist, or a biologist, one has to acknowledge a slant. All this adds up to a confusion in the public mind between science and technology. To get back firmly to science, its job is to investigate the world, then it may as well investigate the nature of management and control as of the structure of benzene, or the atomic nucleus. Indeed, science has been doing just this. It has been investigating the processes of management. The movement began early in the century and made slow progress until the First World War, when military exigencies caused it momentarily to flare into activity. Between the wars it was quiescent. But 20 years ago it began a vast surge forward. Out of the work done since 1940 has emerged a corpus of scientific knowledge about management and its problems that is called operational research, and about the nature of control that is called cybernetics. Today it is a sober fact to state that the pursuit of these two topics has wrought an intellectual revolution in the very basis of the conduct of affairs. But remember what happens to reformers. In the first place, the man of affairs is not, by nature or in fact, much concerned with science. His concept of the subject is probably 50 years out of date. This anachronistic outlook is at once reflected in a denial that his area of action is a fit and proper field for scientific investigation at all. People still write to the newspapers on these lines. Next, the obsession in the public mind with topics of science, especially with technology, prompts the man of affairs to say that even if his preserves are not forbidden territory, at least science has no means of entry to them. He thus ignores the fundamental motivation of science, which is not to apply techniques, nor to do chemistry, but precisely to find an entry. And so it comes about that the intellectual revolution concerning the basis of management and control does not exist for the man of affairs. It is easy enough, and common enough, for such a man to declare that scientific activity in this area does not and cannot exist. His motives are pure. He does not engage a Machiavelli to advise him to say this. But the ghost of Machiavelli is feeding him the ammunition just the same. And suppose this man of affairs should meet the operational research scientist or the cybernetician one dark night. What shall the ghost of Machiavelli prescribe then? We saw the answer at the start of this chapter. The man of affairs should reply, "There is nothing new about." 6. These subjects, we have been doing them all the time. Seek out some of the employers of operational research scientists and they will tell you just this. That ends our primer on how to neutralize a revolution. The question is whether it also ends the attempt to make a revolution effective. This book is about the intellectual revolution in management and control. It talks about reform compared with which there is nothing more difficult to carry out, nor more doubtful of success, nor more dangerous to handle. For this reason, and unlike other books about operational research and cybernetics, it is concerned mainly with neither teaching techniques nor stating facts. Indeed, the first quarter of the book is concerned precisely with this question of management and science as interacting activities. A serious but not solemn attempt will be made to investigate the nature of the muddle so far uncovered, and to break through the grave misunderstandings that have arisen. Anyone who really wants to join in this inquiry with an open mind, suspending judgment on the nature and value of this intellectual revolution until the end, is most heartily welcome on the journey. But here is some free advice for the real prince, whose object is not to be disturbed in his seat of power, and who seeks no exorcism for the ghost of Machiavelli which comforts him. These pages are full of reasons why there has been no revolution, and full of demonstrations that science cannot handle management problems. It is guaranteed to convince you that it contains nothing new. Please do not bother to read further. To be proved right at such great length will be bad for your soul. 2. Science and decision. The whole idea of using hard science as an intrinsic part of the managerial process is alien to many. It is a proposal often countered by such remarks as management cannot be reduced to a science, or even management is an art. But neither of these replies is at all relevant to the issue. The processes of management are complicated. They are complicated for the individual manager for whom insight, value judgment, flair, acumen, maturity, and experience count. They are even more complicated for the social entity that is a management group. Inside this, the climate of opinion, fashion, reputation, maintenance of face, dominance, and every kind of personal relationship also count. There is neither need nor intention to complain bitterly about all this, or to demand that frail humans be replaced by infallible electronic computers. It is only in the 7. eyes of the layman that science imagines itself omnipotent, and the human brain is still the best computer we have. Now the input to the brain consists exclusively of sensations which are arranged in meaningful patterns. The meaning starts as a raw awareness of our place in the world that lies outside us, thus the pattern may be passively received. Or it may trigger off a whole series of physiological reactions, leading to a physical or emotional response. Reflection on these patterns is an intellectual process that forms new patterns of a higher order. Distinctions are drawn between facts and illusions. Particular facts may be generalized, inferences of many kinds may be drawn. Decisions are patterns of a still higher order. So for science to examine decision is itself a most complicated business. It cannot involve less than is involved within the managerial society and the brains of its individual managers. In fact, it must involve a good deal more, or it has nothing new to contribute. Let us examine briefly how this fresh contribution may come about. A decision has to be reached about a certain piece of plant. Fortunately enough, there are various facts about this plant, verifiable statements which are common ground between the manager and scientist. For example, the plant exists, it was put there 18 years ago, the manager's name is Ponsonby. On the face of it, one might write down all the facts and then pass to a list of opinions about this plant. It is efficient, it is too expensive, it is out of gear with the market, and so forth. But a little reflection shows that the dividing line between these two lists is not quite clear. We may best exemplify this by observing that some propositions would be entered as facts by one lot of observers and as opinions by another, and vice versa. Consider a simple illustration. Tests have been run in the works to see whether one kind of machine tool is better than another. The purchasing department says that A is better than B because it is cheaper to buy. The production engineers say that B is better than A because it produces a better job. The accountants prefer A because its product has the higher profit margin. The salespeople nonetheless argue for B because, although its product has the lower profitability, it is easier to sell. The task of a manager with a decision to reach is the task of rolling up all such small and isolated verdicts into a ball to produce a consolidated verdict about the relative merits of A and B on the whole, in the long run. All these viewpoints are really opinions, although those who express them probably call them facts because there is an allegedly factual basis for them. The basis of this 8th allegation will be considered later. Plenty of judgment is needed here, and the weighing of evidence, it is almost a juridical proceeding. But let us return to the scientist. What has he to say about or to contribute to the state of affairs? He might discover, by the use of statistics, that the various advantages of B over A and A over B are in no case big enough, when compared with the number of trials, for any conclusion to be validly drawn at all. That is, given the amount of experience so far accumulated, all the results could have been due to chance. In this way all the little facts, and especially the big composite fact, dissolve away. The only fact relevant to a decision available in this story is the fact that there is no logical basis for reaching one. Of course, a manager might think that if he submits to this kind of scientific advice, he will never be allowed to do anything. As situations become more complicated, so the problem of establishing an adequate scientific basis for decision becomes greater. But here comes the scientist again, this time trying, in view of all this, to organize the experiments in more subtle and sophisticated ways so that a decision may after all be reached on logical grounds. Then, if we are determined to get rid of the scientist fellow somehow, let us declare that the answer has to be given by this evening and that the proposed tests will take 3 months. Surely that is the end of scientific advice in this problem? Not so. The scientist is not the dedicated maniac that so many take him for, he lives in a real world of pressures like everyone else. And if time will not permit him to reach concrete scientific conclusions, he must use whatever information there is in an attempt to establish the probabilities that one is better than another. This is not unscientific. The whole truth about a matter is never known. Scientific answers are always relative, they hold under certain conditions. The condition now being introduced is a constraint of time. Now suppose that the probabilities are equal, as they would be if, for example, the A's and the B's had exactly the same characteristics over the run of tests made. The manager at this point may be thinking of tossing a coin to decide between the two, and the scientist observes in passing that this is a very scientific outlook. For where there is no evidence, it is best to acknowledge the fact candidly, rather than invent reasons for choosing A above B. However, there is more to come. If there is nothing within the A/B situation to indicate which is the better choice, then we should look outside the situation. This means attending to the question of vulnerability. To put it simply, where there is nothing to choose between machine tool A and machine tool B in any of the ways relevant to the product, it may be that A is made by a firm with a better reputation for delivering its products on time than the firm producing B. And so on. 9. This example should not mislead anyone to imagine, this early in the story, that scientific inquiry is appropriate to production decisions alone. Indeed, when an argument of this kind is deployed in connection with a board-level problem, it is even more cogent. For the facts that are passed around the table are in this case even more suspect, because they are really verdicts built out of many less important verdicts themselves masquerading as facts. At this level, decisions are based on assurances made by people one trusts, which are in turn based on opinions expressed by subordinates one trusts, who are in turn assumed to have trustworthy information. If opinions, verdicts, and assurances are loosely regarded as facts, and if the processes by which they are propagated and accepted are loosely regarded as rational, it is no wonder that the best decisions are not always taken. Management scientists have much advice to give about all this, but to understand it, one must first acknowledge that the present methods of decision-taking are precarious. The picture now emerging seems to be this. The brain of the manager is capable of taking into account a large number of considerations, some of which may ramify a long way from the apparent situation. It is capable of weighting these considerations according to their importance and to the degree of reliability of the facts which measure them. The manager knows he does all this, and when someone says to him that science can help him in his job, he at once imagines that a decision procedure of a much simpler kind is going to replace his own brain processes, a procedure that will be no good. Why he should think this, I do not know, unless it be because what most people are taught about science is badly done, and an oversimplified notion of the philosophy of science has been generally accepted. This is perhaps the case, for even when operational research is being used, one frequently hears it said, "Whatever you chaps may say, there are many other factors that I will have to take into account in reaching a decision." Now the whole point about doing science in the managerial sphere is that it should be good science. And what kind of science is it that omits to take account of all the relevant factors which encompass a problem? At the least, science can certainly take account of as many factors as anyone can think of, and ought to find a few more that have escaped notice too. 3. The manager and science. No, the capability of science when applied in this area is not a diminished one. Scientists are people who have been trained in ways of examining the world which offer the best known means of making our 10. beliefs about the way that world behaves correspond to the facts. This may sound an odd description of science to someone who thinks of it in terms of Boyle's law and the Wheatstone bridge, but such is the real nature of the subject. Then let us go back to the criticism with which we started. There is no question of trying to reduce the process of management to a science. The intention is simply to augment by scientific method the processes of which brains are capable in making judgments and taking decisions. In this way, it is hoped to lift various decisions which might otherwise have to be considered by hunch out of the arena of argument. The more we can measure, the more we can quantify, the more we can establish genuine fact, the more we can demonstrate what follows and what does not follow, the more we can calculate chance and risk, the less vulnerable need the ultimate decision be. The first insight to be attained, it seems, is that to say whether management is a science or an art is not to the point. What matters is that every relevant skill should be turned to the task of producing good decisions and more effective strategies. Science by its very nature is adequate to aid the manager in this. For science is not a thing done by physicists, nor a thing done by chemists, it is the establishment of knowledge about the world. And that part of the world in which the operational research scientist operates is the area of management decision. It has to be accepted, however, that the scientist works with true scientific comprehensiveness, he is not a peddler of techniques. If this is not acknowledged, the manager will never make the scientist a true partner because he will not be able to see how he can. In parenthesis, it should particularly be acknowledged that certain scientists themselves are often slow to understand this point. In an age of ever-increasing specialization, comprehensiveness in scientists is as much frowned upon in academic circles as it is unexpected by businessmen. But the mark of the true scientist is precisely his breadth of outlook. Consider this comment by Sir Herbert Reed, writing about the death of the very great Swiss psychologist, C.G. Jung. Reed remarks that Jung's comprehensiveness was not only the distinctive mark of his genius, but also the explanation of the skepticism with which his work was sometimes received in academic circles. Reed goes on to justify Jung as follows: but just as there are certain distortions of science which we call historicism, or certain distortions of artistic style which we call mannerism, so there is a distortion of science which we may call scientism, and it is so far removed from the true spirit of science, which 11. As Bacon said, takes all knowledge to be its province, that it has become the real obscurantism of our time, turning a blind eye on all phenomena that cannot be accommodated to its own myopic vision. There are some managers, and some scientists, who share myopia of exactly this kind where operational research is concerned. If this book is to be understood at all, the reader must start with a willingness to grapple with the real nature of science. To set down the undoubtedly controversial point at once, neither the manager nor the scientist can prejudge the best approach to a particular decision. If science is to be applied, then a scientific attack must be used from the start. This prohibits the manager from saying 90% of the things he customarily does say in briefing the scientist. To take a thoroughly basic example, the manager will speak of the facts, those that are known, those that are required, those that he proposes to make available. Rude things were said about facts in the last section, and it is time to consider what this criticism really amounts to. In books on the philosophy of science, it is usual to take an example from the most basic kind of scientific fact, a measurement. How do we know that this thing weighs a gram? A little reflection will show how the fact that it does weigh a gram must depend on a chain of comparisons linking this gram's worth with some ultimately standard gram, and how the concept of a standard must in turn be hedged in with many qualifications about how it is to be measured, to what accuracy, and in what conditions. But all this, though interesting, sounds like metaphysical speculation to a practical man. He is therefore invited to try his hand at uncovering a simple fact from the following account of a real-life situation. A section of a machine shop contains 6 roughly similar but not identical machines. The output from these machines for a succession of 12 identical periods of time is given at Table 1. The double line dividing periods 1 to 6 from periods 7 to 12 is the moment at which an Table 1. Number of items produced per period on 6 machines. 12. Important change was introduced. The question is, was the change a good one or not? Here is a possible approach to this question. There was a uniform level of activity in this place in each of the epochs 1 to 6 and 7 to 12. Namely, there were 26 productive and 10 unproductive periods. So there is no need for any confusing details. Kindly extend the table to show the total output before and after the change, and strike the averages in each case. The manager's clerks are competent, and extend the table as in Table 1a. Well, the answer is clear, production has. Table 1a. To complete Table 1. Total output before. Total output after. Equals 14,816. Equals 14,707. Average equals 569.8. Average equals 565.7. Fallen. Certainly, then, the change was a mistake. Whether the man who suggested the change should be sacked or not is a matter of opinion, a question for the manager's judgment. But the outcome itself is a fact. But wait a minute. Here is another manager, who argues like this. There is no need, he says, for any confusing details. Kindly extend the table to show the total output before and after the change, and strike the averages in each case. This manager's clerks are competent too, they just have a slightly different idea of what the manager means by these words. They extend the table as in Table LB. Again the answer is clear. Production has risen on every machine. So the change was certainly advantageous. The manager must decide whether to give the innovator a bonus, that is his prerogative. But no one can argue about the improvement itself. That is a fact. Table 1b. An alternative completion of Table 1. Machine. Average. Average. Before. After. A. 570.8. 571.5. B. 550.0. 552.0. C. 605.0. 612.3. D. 587.6. 590.0. E. 542.7. 554.3. F. 544.2. 545.6. 13. The odd thing is that we cannot even say which, if either, of these conclusions is correct. Of course it is possible to see why the two answers are different. But the machine differences taken into account in the second case may not be relevant. The change of practice on which judgment is required may itself have induced the particular apportionment of unproductive time to each machine that makes the first case bad. Secondly, as in the earlier example, a statistician might determine that whatever has been happening here does not matter, in that the changes could all be accounted for by chance. So much, then, for the sacred fact. It would be interesting to hear these two managers arguing the outcome at a management meeting. But it would be better, surely, to let the scientist concerned with the problem in which the situation figured find out the facts himself. That kind of judgment is his business. By the way, it is to be hoped that no one will discard this example on the ground that he would inevitably see through the dilemma. Perhaps he would if he had access to the original table. But the odds are that some clerk will have opted for one of these forms of presentation, and used it. In this way, the manager thinks he has taken a decision on the basis of a fact. In reality, the manager of this example was a non-entity. The sacking or promotion was a decision made by the clerk. For the degradation of science. Well, it may be said, the point that it is the province of science to investigate the world is taken. It will not be supposed that a scientist operating in the managerial situation is a man committed in advance to timing jobs with a stopwatch, or a man dedicated to the hopeless task of transforming the manager's personal thinking into the language of electronic computers, or a man who is given the facts and told to analyze them. Is that not insight enough to be going on with? The answer is yes, subject to one further proviso: it should not be imagined that any piece of coherent or useful thinking is inevitably scientific thinking. The mistaken idea that must be dispatched at this point is almost the opposite fallacy to the one already discussed. Just as there are people who believe that the scientist is a man with a gimmick, so there are people who think that science is no more than a synonym for coherence. This is really to use science as an okay word, meaning roughly the opposite of superstition. It is one of 14. Life's dear ironies that these two extremely different views are often held by the same person, but we will deal with the second outlook as if it were entirely distinct from the first. A senior industrialist was once heard to say, "All our conclusions are scientific, the only question is whether operational research can make the science more sophisticated, and the conclusions therefore yet more exact." If one could take an entirely rigorous and objective view of this apparently innocuous statement, it would surely seem to be insane. It is not really so, of course, because the speaker is trying to say something which in his own eyes seems eminently sensible. Man is a rational animal, he is saying, and so long as he is in control of himself his behavior must be scientifically sound. Irrational behavior is the mark of half-wits, drunkards, and delinquents. Now, to that speaker, it is evident that rational behavior is something that necessarily follows scientific investigation and follows it alone. But to adopt this use of words and the ideas behind them debases the notion of science, and degrades the meaning of the word. In fact, scientific reasoning is extremely rare, is not very often indulged in by anyone who is not a trained scientist, and is a very difficult subject demanding lengthy study. The processes by which man the rational animal normally thinks and comes to conclusions are not scientific, and this is not said disparagingly. The way man normally thinks is determined by the physiology of his brain. We know a good deal about the way the process works, and ought to admire it for the reason that nature has produced machinery which is competent to survive in a hostile and competitive world. But unless we clearly comprehend that science is entirely distinct from rationality in the sense of coherent and useful behavior, this book will be meaningless. There is, unfortunately, a considerable background of nonsense to be plowed up before the word science acquires its proper meaning in the vocabulary of managers. 60 years ago, men such as Taylor and Gilbert began to attack production and other physical processes by a basically scientific method. They set out to measure and to record, to analyze and to improve. Measuring, recording and analyzing are certainly acts that belong to scientific activity, and the contemporary topics of method study and work measurement are scientific. But the other legacy inherited from these pioneers was the term scientific management, which has had a less felicitous development. People have come to believe that any sort of thinking that incorporates facts and figures can 15. Statutes some phase of the scientific management that starts on the shop floor with work study. But this is not true. The techniques of the stopwatch, the micromotion camera and the chronocyclograph are of little use in the boardroom. They cannot be focused on management decision. What techniques should replace them? The arithmetic average and the simple chart? Certainly not. A more sophisticated kind of science is needed to aid the decision processes of top management than is necessary on the shop floor, not a total collapse into the trivial. Anyone who wishes to live up to the ideals of scientific management set by the pioneers at the turn of the century, and hopefully embraced by many young managers in the 20s and 30s, must today understand operational research. A first step that must be advocated is to forswear attitudes that degrade the idea of science. We have already seen how the basic building block of science, the fact, has been degraded to mean a verdict. We have noted how the word scientific is abused in the context of management. In between the basic, particular, and the generic terms is an assortment of pseudo-scientific phrases that people use to comfort themselves. In a scientific age, a masquerade of scientific terms keeps up the spirits. And so there is a law of averages, a term used to imply that probabilities continuously adjust themselves to converge on a target balance of frequencies, which they do not. There is the calculated risk, a term used to mean that a risk is recognized but has not been calculated. Perhaps the real nature of science, and the capabilities it has to offer in the service of management, will only be understood when the masquerade is over, and the scientific-seeming masks are dropped to reveal the intuitions underneath. Real science in the 1960s is complicated and demanding, as we see it in atomic physics, in genetics, or in space research. When science is applied to management, the complication and the demands are no less severe. The manager cannot be fobbed off with methods that were, scientifically speaking, old hat when Archimedes did the first operational research by advising the king of Syracuse on his combat strategy. If he wants more than this, and there is a great deal more for the taking, the manager needs to start again. He needs to survey present advanced management methods, which have been labeled scientific either falsely or trivially, to evaluate the processes by which decisions today are actually reached and in which scientific method has no part, and he 16. Needs then to consider what it would be like to use the methods of modern science that are in fact available. If any sort of perspective is to be achieved in mastering these aims, some time must be devoted to considering what the rational processes of the brain are really like. In what ways are these natural processes effective, in what ways unhelpful, and in what ways are they distinguished from scientific processes? In the first place, the whole topic of discussion here is not deduction, nor proof, nor the application of facts. When we speak of management and its decisions, we are really speaking of the settling of opinion or belief. This is not a process to be oversimplified. As has just been said, it is not true that belief is settled either by rigorously scientific method on the one hand, or by erratic and emotional caprice on the other. To study what really happens, we need to consider the account given of the process by men who have made a special study of how it works, philosophers and psychologists. Any such account is divided more or less arbitrarily insofar as there are many ways of analyzing thought processes. For present purposes, it does not matter much which analytic scheme is used, so long as it gives something like the right proportion of importance to the scientific method of fixing belief, which is not a very large proportion at all. The particular set of categories chosen comes from the analysis made by the American philosopher Charles Peirce, who distinguished four main methods, the last of which alone is the scientific. Not only is this in roughly the right proportion, but his account of the other three modes of thinking will be found extremely relevant to the modern industrial situation. In the next chapter, then, are set out Peirce's four basic methods of settling belief, with a discussion about each from the point of view of contemporary society. 17. 2. On fixing belief. Just the place for a snark. I have said it twice, that alone should encourage the crew. Just the place for a snark. I have said it thrice, what I tell you 3 times is true. Lewis Carroll. In the hunting of the snark. 1. The method of tenacity. The first method of fixing belief isolated by Peirce might be called the method of tenacity. It begins with a viewpoint, capriciously formed. Perhaps this was something learned at mother's knee, it might have been revealed by a sailor in a pub, or it is an idea culled from this morning's newspaper. Typically, it is what they are saying. At this stage, the viewpoint has no special merit for the man who expresses it, for its casual origins are understood. It is not a belief. However, it is brought out and increasingly brought out to be aired. Gradually it becomes inculcated as a habit of thought, eventually it is indeed fixed as a belief. Be it noted at once that this is not emotional, random, or quixotic behavior, it is opinion that is steadily and systematically evolved, although not in a strictly rational fashion. In fact, we know a good deal about the mechanisms that underlie this way of thinking. They are biologically, if not logically, valid. They come about in the following way. Biologically speaking, organisms manage to adapt and to survive by sifting their experience and learning from it. This is most notably what happens in the case of the brain. Every time a particular pathway is traced through a set of nerve cells, it seems, it becomes easier to trace that pathway again in future. This is rather like the situation on a network of snowbound roads. Every vehicle that passes makes it easier for the next to pass, until certain routes through the network of roads must 18. Obviously be preferred to others. The brain acquires maturity in exactly this way. If it were not so, we should be incapable of coherent behavior at all. Unfortunately, there is a snag. For this is the very conditioning process by which men are indoctrinated, for political ends, with beliefs that would otherwise be unwholesome to them. And of course, if this result can be achieved by cunning in an authoritarian state, it can also be achieved by accident in the normal social environment. For everyone knows how cliché-ridden is most of our small talk, how we repeat ourselves from one conversation to another, how we confirm and even embellish an anecdote as the literal truth which may simply have started as an amusing fabrication. It is this kind of thing that goes on, according to Peirce, when the method of tenacity is being employed. It is not a scientific mode of thinking. But it is not the irrationality of a madman either, for there certainly is a scientific basis for saying why we think in this way, how we think in this way, and also for saying that it is a sensible way for a creature whose survival depends upon his ability to profit by experience to think. But, after that apologia, it is still fair to point out the dangers surrounding this method of fixing belief. It is likely to deaden the facility for entertaining new ideas and to produce the reaction, "I could not believe the contrary, because I should be so wretched if I did." New thinking means broaching a new pathway, risking a snow-covered road when alternative routes have already been cleared. We say then that people prefer the familiar. In fact, their brains are constructed as machines for reinforcing successful combinations of neural events, and reducing the probabilities that alternative combinations will be tried. Incidentally, this is surely one of the reasons why people so readily claim that their judgments are more or less scientific. For if I count it wretched to be unscientific within the scientific milieu of these progressive days, then I am likely to allege that whatever belief I have come to hold must count as a scientific opinion. But let us go on exploring the nature of the method of tenacity itself, observing how it actually operates in our lives, so that we may more readily recognize what a threat it constitutes to the development of new ideas. The best use of the whole process is indeed that of intellectual conditioning, but only in its more constructive sense. We may teach a child that 7 times 8 equals 56, so that he becomes conditioned to feel wretched if someone should propose an alternative answer. But if we use the same process to facilitate the wrong pathways in the brain, we shall produce aberrant behavior. If we 19. Teach a child that la chaise means the roof, he will feel confounded in France when invited to sit on a chair. The status of these propositions, the one arithmetic and the other linguistic, is quite different in science. The first is true, the second false, and the scientific approach to the validation of either proposition is quite different from that which must be used in the case of the other. But the status of the two propositions in nature, considered as contents of the mind, is the same. Each uses the brain as a learning machine to produce a conditioned response to a repeated stimulus. Thus subjectively, and no wonder, they appear equally valid. So if we now apply the label scientific conclusion to the first example, it is likely to become attached to the other, for the subjective experience of the trainee is identical. Let us take as an example what is happening in British industry about the use of operational research. How is it that operational research began as a tool for devising important strategies, but is now mostly used in industry at the merely tactical level? Well, when we began we were advised to go carefully, to make as few demands as possible, and to get the work started at all costs. Therefore we did not worry very much about pitching the work at its most effective and relevant level. How does a scientist find words to say to a managing director that he needs a scientific plan for his whole capital development program, or a scientifically designed control system to contain the company's vast and rapidly expanding expenditure on stocks? No, we allowed ourselves to think it the path of wisdom to move slowly, and to encourage our work to grow from small beginnings. We said, let us install scientific planning on the third bit of plant on the right as you go in number 6 gate. We said, let us calculate the right number of items to stock in the sample stock bin, thereby demonstrating in principle how to clap scientific controls on stocks that must be replenished continually. Whether this was the path of wisdom after all, or not, is still not clear. At any rate, it was all that we could do. How have managers responded? They began by wondering precisely what sort of activity they were nurturing. They took up a consciously open-minded position about this work, and said to each other that it was their duty to find out exactly what it does. As study succeeded study, it became increasingly clear that what operational research does is whatever it happened to be doing. It is almost a pity that those early jobs succeeded so well, for managers discussed them among themselves and gradually built up, by the method of tenacity, an account of what operational research really is. It is what it has repeatedly demonstrated itself to be. How could it be anything else? This is a good example of a piece of genuine, physiologically sound 20. Irrational thinking. It belongs to non-science in management. It cannot be technically dismissed as absurd, nor called a species of scientific conclusion that has slightly misfired. When the man eventually comes to his management and proposes to undertake a study of a really advanced kind, the sort of thing he is trained and fitted to do, the very people who began by acknowledging their own ignorance and an earnest desire to learn about the nature of this activity, turn round and tell the man that this kind of work is not his province. They proceed to explain to him what his own subject is about. This is of course the reason for the existence of this book. There is a solemn need at this point in time to start again, and to ask what are the real purposes and capabilities of operational research. It must by now be clear why this early chapter of the book is devoted to so odd a topic as a discussion of the way in which we all think, instead of plunging straight into the nature and origins of operational research. Unless we confront ourselves with what has been going on, we shall be completely incapable of assimilating a fresh exposition, even if it were twice as clear, and twice as convincing, as I shall be able to make it. We must warn ourselves first of all about the method of tenacity. Useful as it normally is, it will not serve our purposes now. As a footnote, let it be said that this admonition applies just as strongly to scientists themselves as to managers, for scientists are only human too. Once he has been employed on a number of trivial and more or less irrelevant projects, the scientist gets used to it. The method of tenacity conditions him to believe that he is not the sort of creature he is. That endearing trait of the scientist, a due humility in the face of the infinitely complex and marvelous nature of the world, leads him to interpret his own conditioning wrongly. He may think that the degraded form of operational research often met with today is no more than the original conception of the subject shorn of its more grandiose delusions. Up to a point, this is the sober truth, but let us more constructively agree to entertain the opposite view, so that if indeed the national operational research capability is not being properly exploited, there will be more chance of recognizing the fact. The point of this section is to argue that the method of tenacity is illogical, but not a process that should be vehemently decried. To say that a belief has been fixed in this way is not rude, nor is it an accusation of sheer prejudice, since this is the way the machinery in the cranium actually works. But the device that works so well in adapting the animal to its environment is no blessing when an intellectual breakthrough is required. The need for this in man the animal is rare, but man the 21. Manager, man the conceiver of change, must needs disrupt the pattern and alter the rhythm of his brain. It is surely predictable that, in his animal role, he will be cautious about doing this. The system rebels, but in so doing there is also a predictable outcome to his failure. When an animal species is confronted with a slowly changing environment that suits it well, it becomes specialized. Giraffes have acquired long necks, and zebras stripes, fish have gills, and cannot breathe the air. This is what is meant by specialization in biology. The process is the genetic equivalent of the adaptation processes of the individual brain. Strong preferred patterns are formed that neatly match the environment. Now suppose that environment changes radically and rather fast. An animal species that cannot change itself quickly enough to cope is overwhelmed. Specialization has become over-specialized. This is what happened to the dinosaurs. Man as a species has developed a large brain to meet this threat of extinction. With this weapon, mankind has acquired a faculty for forecasting the threat, and for changing its capacity to cope artificially. For instance, man can forecast that if he ventures to the South Pole he will be too cold to survive, and he makes provision to keep warm. He does not wait for his species, or the explorer subspecies, to grow fur. Even so, the brain is not always equal to the task. When a man is brainwashed, the technique is precisely to confuse his ability to forecast events and to be prepared to meet them. This is done by making a random, instead of a systematic, connection between stimuli and responses. A species confronted suddenly with a new environment, alternating between a polar and a tropical climate, would not adapt to it sufficiently quickly to survive. A brain confronted suddenly with brainwashing techniques is beaten. The moral of all this is to suggest that so long as the social, economic, and industrial environments change slowly, the method of tenacity that our brains employ works well. We adapt. Today, however, these environments are changing rapidly. The method of tenacity produces too slow an adaptation to cope with the revolutions that the world is undergoing in every sphere. Unless those responsible for policy making abandon this method, and turn to other ways of exploiting their cerebral equipment, our society will not adapt sufficiently quickly, and we shall become economically extinct. Manifestly, the nation is moving towards this fate. Governments are selected by the method of tenacity, they operate by this method too. Industry is managed by the method of tenacity. New thinking everywhere is blocked by the method of tenacity. 22. Conversely, when new ideas about management and control have been discussed for a sufficiently long time, they too will be generally adopted, not by logic, but by the method of tenacity. But this time, perhaps, it will be too late. 2. The method of authority. The second way of settling opinion without being scientific is by appeal to authority. In today's society, this mode of thinking is possibly the most important in fixing belief. It is the will of the institution. On the face of it, this is a simple matter, with no subtle undertones. After all, people usually know when they are playing politics. But the question is really much more complicated and insidious than this. First of all, Charles Peirce put the naive point of view with some charm. When complete agreement could not otherwise be reached, a general massacre of all who have not thought in a certain way has proved a very effective means of settling opinion. That was written later than Machiavelli, but long before the emergence of the organization man. However highly placed he may be organizationally, An individual is part of the social system which gives life to the institution of which he is a member. The question of the extent to which he will conform to accepted ideas and values is by no means simply a matter of his own strength of character on the one hand nor of his ability to compromise on the other. He is aware of a number of pressures which work upon him, but unaware of a great many more which operate in less obvious ways. These are the natural laws which govern the behavior of any large system, and we can go some way towards offering a scientific explanation of the way in which they work. Let us start by picturing a system, any kind of system, in which the interesting feature is the distribution of heat. One small zone of the system is hotter than the rest. Now we know full well that if the system is left alone for a time, without any further input of energy or contact with the outside world, the hot zone will certainly not get any hotter. In fact, the hot zone will gradually get colder. The heat which has been concentrated in the one small zone will gradually dissipate right through the system, until the distribution of heat is uniform throughout. This state of affairs is an example of the second law of thermodynamics. We have learned enough from experience to recognize intuitively that the picture just painted is correct, but it takes a lot more thinking and research and mathematical insight to develop all the consequences for 23. Systems in general. However, scientists do know how to describe the general case of this natural phenomenon. They know, for example, that any system will gradually run down if cut off from a source of outside energy, because the energy internally available for useful work will gradually even out until there is none left. A system in this state is best regarded, perhaps, as dead. They also know that any flow of information in the system is related to these energy changes. In fact, it is easiest to think of information as being news about the states of energy in the different zones of the system, news which is carried about by the energy shifts themselves. Now as the system runs down, there is ever less energy available to carry ever less information about ever less important differences in internal states. When the system has finally stopped operating, because there is no internal energy potential left, there is nothing to know about the system anymore. Thus high information levels are exactly correlated with high differentials in internal energies. This connection, by the way, is not fanciful or literary. The mathematical equations describing these two aspects of a self-contained system turn out to be the same as each other. By these self-same equations it is possible to see how the high energy associated with a particular individual or group inside an institution tends to be absorbed and assimilated by the remainder, because the system is struggling by its very nature to even things out. If it succeeds, then it becomes defunct, it runs down, in the language of the example given. When the heat is evenly distributed, there is no potential left for doing useful work. Of course, this application of thermodynamic principles to social systems is made by analogy, and the conditions do not hold perfectly. The system is supposed to be entirely self-contained, sealed off from the rest of the world, and no human institution, such as a firm, is entirely isolated managerially. Yet this fact, interestingly enough, does not so much invalidate the analogy as indicate the precise way in which real-life organizations alone manage to survive. This is by an interchange of managerial energy with the world outside the system. Here is another conclusion to be drawn from the picture that is emerging. If the system cannot, or at any rate does not, disseminate its pockets of high energy in the way described, there is one other alternative open to it which will still conform to the natural laws of thermodynamics. The system may declare the high energy pocket contained within it to be an independent subsystem. A heat-proof shell can be built around the high energy zone which will then stabilize 24. Itself within the shell, while the main part of the system stabilizes itself regardless of the special zone. Perhaps this is a sensible way for a social system to deal with its awkward components, and surely we have all seen this happen. It certainly can happen to our groups. Scientists are to be on tap, but not on top, isolated in a special box. But note what thermodynamics teaches about this. Observe the inevitable consequence. If no energy is permitted to flow, no information can flow either. The two apparent aspects of the system are two ways of talking about the same thing. So the common notion that highly qualified, lowly paid boffins can be kept at arm's length and used to give advice without making any organizational impact at all is not feasible. There are plenty of managers who honestly believe that specialist advice should be handled in this way. They shrug off suggestions that the treatment is immoral or unfair or even unworkable. How will they cope with a demonstration that their scheme is fundamentally impossible? The analysis that has been undertaken here is an attempt to explain the mechanism underlying the method of authority. It is worth reading again, for it is not a piece of ingenious argument or special case pleading. It could all be set out coldly, scientifically, with its equations, in a passage that would very properly be skipped. Instead, let us see how the mechanism produces the settling of opinion. Sociologists and other perceptive observers have detected, simply by going around, a phenomenon named by William White the organization man. He is a man in the big organization who conforms, often without knowing it, to the will of the institution. He thinks by the method of authority. The thermodynamic model sorts out the laws of systems that operate him. The organization man is a component of a large system which, corporately, knows that it must even out its energy. Information about other components of the system and their energies continually reaches this man, comparisons are drawn and adjustments made. The system itself intends, basically, neither to expel energy nor to acquire energy from outside itself. Its mores, its institutional conventions and acceptable ways of behaving, become adapted to this end. Thus other benefits in a firm are arranged as ways of dissipating energy to components of low energy. The equivalent information that comes with this energy constitutes a pressure, for the components must accept the benefits, and do nothing to resist the evening outflow. That is, they must not generate original. 25. Information, their capacity for doing which is in any case being steadily diminished. This is fairly obvious. The other aspect of the matter is more interesting. What happens to the aberrant component, the non-organization man? He, of course, is not conforming to the rules, apparently the institutional rules, in fact the rules of closed systems. Well, the system cannot acknowledge his existence. Remembering that a social system consists of human relationships rather than mere bodies, it is possible to decreate, to extinguish, a component man, although he still goes about his work. This is done by ignoring him. Extinction, not opposition, is the point. The sheer power of the remark, "He is not a blogs man," as made by the blogs organization, is otherwise hard to understand. Clearly this is an argument from authority, clearly damaging, clearly non-analytic. The mechanism we have traced adds to this an explanation why the nonetheless unemotional, almost amiable, comment in fact involves the general massacre of all who have not thought in the blogs way. For a man who is not a blogs man is not just irritating or lacking in value to the blogs organization, he simply does not exist. To deny a man existence in this way is the ultimate form of censorship. And so we reach the final end of the method of authoritarian irrational process, and one that already partly controls our advanced civilization. Attempts by well-meaning managements to thwart the running down process in their own large firms are thwarted. Look at any management course, any foreign visit, any internal conference. The organization men are there, sent by managements who instinctively know that they must break down the isolation of their systems, and begin to import and export information and energy. But it may be too late. Their men may be physically outside the system, organizationally they are still part of it. They explain with civility and conviction to the management course that all these nice new ideas have either been used in their companies for years, or been shown appropriate to every type of business but their own, which is a special case. They report on their foreign visits that they saw nothing of value, but that the trip was worthwhile, since a famous company owes it to society to share its insights with others. At internal conferences they say nothing. This is by far the best way to get on. He is a blogs man, one of us. There is no thermodynamic fault in any of this. The symptom to be on the watch for is acquiescence, the sign that the energy flows are all working as the system requires towards a cessation of activity. It is irrelevant to these purposes whether the firm is flourishing as a commercial enterprise. It may do this for many years by sheer 26. Weight. Even a charging rhinoceros would drop dead in its tracks if its internal arrangements could succeed in spreading all its energy and information evenly. And when you and I are dead, the pathologist will find our bodies in exactly that state. No, men are endowed with individual minds, acquire different experience, erect idiosyncratic prejudices and beliefs. They therefore squabble, disagree and push each other around. Civilization teaches us to do all these things with due decorum, the social graces can still be observed. But when men actually stop doing these things, use civilization as a rationalization of sheer inanition, and absorb their energy in artificial battles ranging from overmuch golf to petty personal politics that have nothing to do with the company's real business, look out. These are organization men. The institution has cancer. No space is devoted to prescribing remedies. That is not the problem at this stage. The difficulties are, to recognize the disease, to acknowledge it, to understand its basic nature. We have discussed these matters. The therapy itself is not difficult. 3. The method of a priority. Recall that this chapter set out to examine the context of human thinking in which the method of science is set. To understand what is distinctive about scientific method, it is essential to give formal recognition to the existence of other ways of settling belief, two of which have so far been examined. It has already been urged that these strictly irrational ways of thinking are far from being stupid. They are intelligent in so far as they have an experimental validity, they fit in with the way nature in general operates. In fact, there is a biological justification here for the taking, since the whole point of these irrational methods is that they are evolutionary, competent to adaptation, and hence to survival. Now the third and last category of non-science proposed by Charles Peirce is particularly susceptible to misunderstanding. In a society where any kind of thinking is alleged to be more or less scientific, the category that is now to be discussed is particularly likely to be confused with science itself, especially, as it happens, by scientists themselves. This is the method of a priority. First of all, however, we must explain the use of this fairly unusual word. An a priori argument in logic is one which begins from a set of axioms which are assumed to be true, rather than from experiences that have been undergone. Some philosophers have argued that such axioms are innate in the mind, that they existed prior to experience. The practice of this kind of reasoning is called a priority. An example of one such axiom with which it is very hard to argue is Aristotle's principle of non-contradiction: a thing cannot be both itself and not itself at the same time. One may doubt whether one did know this from birth, and suspect that it was indeed a conclusion based on experience gained when one began learning how to use words as names of things. But whatever the philosophic issues, it is certainly the case that people do in real life produce all kinds of arguments which begin with unexpressed assumptions that they take to be self-evident. Now, why should any proposition appeal to us as self-evident? The answer is clear: it is, as we would say, agreeable to reason. What we really mean is that it fits in with all our experience, whereas to contradict it would make our whole way of thinking about the world quite absurd. So again we find a basically biological justification for the method of a priority: it works. Unfortunately, of course, people often adopt assumptions that seem self-evident to them, but which are by no means so to other people. Then the trouble starts, because it is characteristic of this kind of discussion that the assumptions are not clearly stated and agreed in advance. But this is not a discussion of logic. The case is much more interesting where people do tacitly agree on a set of axioms, which are common to the whole society which uses them unthinkingly, but which are nevertheless just plain wrong. People drawn together into one political party, for example, express views which are often genuinely incomprehensible to their opponents for precisely this reason. How does a closely knit society with such an agreed set of axioms behave in the face of a contradiction to one of them? That is to say, a view is to be expressed which is not agreeable to reason as far as these people are concerned. The answer is that such a denial is simply taboo, it must not be mentioned. Pierce says, let it be known that you seriously hold a tabooed belief, and you may be perfectly sure of being treated with a cruelty less brutal but more refined than hunting you like a wolf. In other words, people who give expression to the tabooed belief are due to be run out of the society by invoking the method of authority. Examples of this irrational method of fixing belief, the method of a priority, are legion and very scientific they look to. The reason for this particular susceptibility to confusion which was mentioned earlier, is that the most powerful language of science, mathematics, also proceeds on sets of axioms. Euclidean geometry, to take a familiar example, only works because of the a priority built into its fundamental definitions. 28. For instance, the parallel lines which never meet in a space according to Euclid, may be described as eventually meeting in a space according to Einstein. In other words, it is possible in science to deny a set of axioms and to replace it with another set, in which case a new way of describing the world emerges. For example, non-Euclidean geometries have been constructed, and very useful they are too. Philosophers and scientists, who are professional thinkers, are in principle distinguished by their readiness to deny the assumptions of their arguments and to see what happens. In practice, of course, since they are human like everyone else, they cannot always rise to the psychological challenge involved in this procedure. Human argument, in general and in short, is in the clutch of a priority as a method of fixing belief. It is a shortcut, on the whole it works, and above all it is psychologically satisfying because the axiom is by definition something agreeable to reason. But look what happens. Our stocks are rising fast, but they are rising in proportion to our turnover, so that's all right. This managerial remark is no trumped-up example, it is often heard. It sounds utterly rational. But the implicit axiom that stocks are things that ought to vary proportionally with turnover is simply not verifiable in most cases. Let us look at the scientific reasons for this. The point to be made is fundamentally a mathematical one, but an attempt has to be made to express it in ordinary English if the agreement not to use algebra in this book is to be honored. So consider the elements that go to make up a stock holding cost and the way they are arranged. Material that arrives in stock always has a batch size, a dozen of these, a gross of those, 57 of something else, even a solitary straggler has a batch size of 1. The cost of holding stock must reflect actual batch sizes, for the reason that part of this cost is invariant with the number of items. That is, when a batch of identical items comes into a store it has to be transported, recorded, and so on. There are many procedures which occur at a uniform cost, regardless of whether the batch contains 7, 17, or 70 items. The turnover of items in the stock will also affect the cost of stock holding. In fact, if we try to write down some kind of formula for the cost of holding stock, it is most likely to contain, among other things, an expression of the rate of turnover divided by an expression for the sizes of batches. This allegation is not put forward as an axiom, but reflection surely shows that it expresses one aspect of stock holding cost that has to be considered in the equation. If we have such an equation and ask a mathematician to determine the size of stock that will minimize cost, he will. 29. Use the differential calculus. His procedure is to differentiate with respect to the ordered batch size, an absolutely necessary mathematical trick for the purposes in mind. In carrying this out, he will be compelled to square the expression for batch size. This is because that expression is in the denominator, as we saw. The squaring is then inescapable because of basic mathematical laws. Next, when he is asked to turn the formula round so as to express everything else in terms of the best batch size, which is the figure management would like to know, he cannot help getting the square of the batch size instead. So, to quote the required figure, he has to take the square root of his answer. It was agreed earlier that the turnover would have to be a factor in the numerator, and the mathematical rules being followed will not square this figure. In the upshot, the batch size of stock goes up as the square root of the turnover. So much for the managerial a priority argument, which said that the stock should increase directly as the turnover. None of this is advanced as offering a universally valid law about stock holding. To assert that would be to be guilty of scientific a priority, for an operational research answer to this kind of question would certainly not be advanced without examining particular experience. Nevertheless, something fairly fundamental has emerged which is at least enough to justify our denouncing the original contention as quite possibly wrong, and gravely wrong at that. There is reason here, that is to say, to beg management to recognize its use of the method of a priority, and to try the method of science instead. For the method of science. It is only now that we reach Peirce's fourth method of settling opinion, the method of science. And firstly we ought to ask whether or not this differs in kind from the three modes of thinking we have already discussed. It is tempting, perhaps, to say that the method of science is rational, whereas irrationality characterizes most human thinking, and yet one can be rational without being scientific. It is better to attend to a special feature of the method of science, which might be called rigor. Rigor is a precise formulation of method, something clear and definite, testable and repeatable. If we want to use words carefully, in fact, the method of science is method. It follows from this that we ought not to have called the three modes of thinking already described methods at all. They are habits of thinking, and the most flattering word we can use to describe them is procedures. Such is our confidence in our usual 30 way of thinking, however, that it may be doubted whether anyone who is not a specialist will already have revolted at the use of the word method to describe these habits of thought. Moreover, this same careful person may have wondered whether Peirce's classification is itself a scientific or methodical classification. In fact, it is not because it has no rigor. Its terms are neither exclusive nor exhaustive. It was used because it offered a convenient set of pegs on which to hang some thoughts. Now that attention has been drawn to these matters, the reader's thinking about the method of science may have got into its stride, and indeed have been leaping ahead. Yes, he may be saying, I realize what the author is expecting me to acknowledge now. After all, I do know what science is about. But stop. How do we know what science is about? We were taught about it in our formal education and we therefore accept a basic orientation from authority. We assume that we know, and this is a priority. Our views have often been reiterate an argument from tenacity. It is not good enough. And yet this is no place for a formal treatise on scientific method, which it is instead intended to exemplify during the rest of this book. At this point, and in the context of discussion of the way people actually think, we can do no more than pinpoint the method of science in terms of the way people seem to regard it. Try reading the next two paragraphs against the criterion of your own beliefs about the nature of science. People think of scientists as remote and dedicated men who follow an inexorable chain of discovery. Their work is regarded as abstract, for the apparently good reason that it picks out coherent and objective facts from life. All this makes it seem remote from biological necessity, remote from social utility, remote from the satisfaction of psychological drives, and remote indeed from life itself. Yet people recognize that it is the most powerful way of thinking that mankind has yet evolved, possibly just because of these characteristics, which seem to disentangle it from emotion and ambition. So people may think, but they are wrong. The way that science works is much admired too, but also for reasons which are just not valid. It is thought to begin with the collection of objective facts, and to sift these logically. It is known to set up hypotheses about the way things work, to test these hypotheses exhaustively, and to try and formulate laws, which is to say propositions about the way things behave in general that turn out to be useful in predicting particular consequences. These approaches to problems are seen to be wholesome and good and likely to succeed. Hence people try to imitate them. They dress up arguments derived from mental procedures, which 31. Are no more than habits of thought, to look like scientific arguments. Yet science does not in fact follow this serial development. Although the practicing scientist can recognize in these last two paragraphs scientific-sounding descriptions, he would be likely to quarrel with every single statement proposed. The method of science is not really much like this at all. So the degree to which anyone thinks that science is like this is a measure of his incapacity to understand the relevance of science to management. The arguments of this section are negative, and may therefore seem unconstructive. But the point they seek to make is tremendously important. Managers do in practice offer scientists strangely irrelevant reasons for thinking that there cannot be such a topic as management science. Careful reflection suggests that this is because their view of science is based on oversimplifications of the kind just exemplified. The appeal for the moment, then, has to be simply this. Let us equate the method of science with a kind of rigor which our ordinary modes of thinking do not have. And let us beware of a bogus rigor, deriving from an admiration of the achievements of science, which cuts improvised footholds for our leaps of intuition. A succinct recapitulation of the arguments of this chapter will provide a reasonable perspective for the next. The mechanics of fixing belief by three commonly used mental procedures have been examined. The method of tenacity uses the process of conditioning, first carefully investigated by Pavlov, in the most advanced and sophisticated kinds of thinking. The method of authority hinges on the fact that the believer finds himself inside a system of which he is an indivisible part, so that his behavior is inescapably affected by the gross behavior of the system itself. The method of a priority uses the fact that all communication, even with oneself, requires a language in which to communicate, and assumes its ostensibly scientific conclusions in the premises which underlie the axioms of that language. At these three levels, the biological, the anthropological, and the semantic man is almost powerless to exert his free will in rigorous choice. Such rational arguments as are used to justify these procedures are based on their practical effectiveness. The choices that people make are usually fairly successful, for reasons other than the method of science itself could underwrite. Thus the sort of validity these arguments enjoy is pragmatic, that is, they provide solutions which fit into our experience, which therefore work, and which therefore comfort the opinion holder, be he manager or scientist. They may all have genuine survival value in the evolutionary sense. After all, organisms using comparable strategies, 32, which are in fact quite irrational, do survive, from the mighty business enterprise to the coelacanth it sometimes resembles. But we ought to note that adaptation by methods which, though justifiably called rational, rely not at all on rigor also leads on occasions to going out of business, or to becoming extinct. So it is that at the very point when a man becomes distinguished from other beasts, he perceives and admires not only the rational but the rigorous. Thus it comes about that the common procedures for settling opinion among men rarely remain strictly irrational, even when they are not fully rational, but they rarely become rigorous. We acknowledge a process called rationalization, a word that is clearly in place in this present context, and a word that is significantly enough a technical term in the vocabulary of psychiatrists. And if we can make the transition from irrational processes to apparently rational ones, which is what this term means, we may well deceive ourselves about the next stage by calling them rigorous too. Very well, the method of science is intended to import rigor into the rationality of managers. Managers sometimes use irrational procedures for settling opinions that will determine decisions in their problems, sometimes they use rational procedures, sometimes they jump the gap between the two by rationalization. Scientists do exactly the same thing, all too often, in settling opinions that will determine their own decisions, for scientists are men. But in their professional capacity, scientists bring to managerial problems the expertise of rigor. This book says why and how. 33. 3. Some dangerous precedents. The principle of the dangerous precedent is that you should not now do an admittedly right action for fear you, or your equally timid successors, should not have the courage to do right in some future case. Every public action which is not customary either is wrong, or, if it is right, is a dangerous precedent. It follows that nothing should ever be done for the first time. F. M. Cornford in Microcosmographia Academica. 1. A history of contemporary relevance. In order to find out why operational research is of any use, it is as well to recapitulate the reasons why it came into existence in the first place. If these can be made clear, the highly tendentious questions that are often asked about the subject nowadays could not possibly arise. Now, to make such a survey, it is necessary to go back to the early days of the Second World War. This will rile some readers. Many people seem to feel that Hitler's war has nothing whatever to do with contemporary problems. They suspect that mention of it exemplifies no more than a sentimental attachment to a spirit of comradeship in long past days of high excitement, and to forgotten glories. But this is the way the history of the subject was written, and we cannot change it if we would. Even so, in deference to these reactions, we shall not harp on bellicose matters. This is not a history of operational research, but a search for its meaning in its origin and early days. It quotes some dangerous precedents, for in war some things actually do get done for the first time, and inquires whether they seem sensible enough and profitable enough to be emulated today. 34. Any group of managers at any given time has some sort of corporate outlook, it has a morale, it has pet theories and aversions, and it has a climate of opinion. Perhaps it is not too difficult to enter into the state of mind of the community of military managers in Britain during the early days of the war. First of all, a large number of sacred cows had laid down and died. There had been no immediate air raids, no gas attacks, the invincible Maginot Line had collapsed and the continent of Europe had been occupied by the enemy. Perhaps this situation is paralleled today in terms of the government of this country, and of its industrial management problems. If the facts are squarely faced, the most cherished political beliefs about the way in which the economy should be controlled are seen to be ineffectual in practice. If so, then it is unfortunate that the kinds of pressure exerted on a nation at peace do not have the psychological impact of threatened defeat in war. The possibility of kidding oneself, the electorate, the employees, remains open today, but this possibility was not open when the country's enemies sat on the other side of the channel and we knew ourselves to be virtually defenseless. Secondly, there were then whole areas of military management in which circumstances compelled those in command to acknowledge freely that they were guessing. When aeroplanes do not return to their bases, when convoys do not get through, and when armies are routed from impregnable positions, the commander who declares that all this is according to plan and fully understood is asking for his bowler hat. And so there were vulnerable areas of management in which people were guessing, in which they knew they were guessing, and in which they had to acknowledge they were guessing. A generation later in this insecure peace the fact of guesswork remains, the knowledge is buried perhaps a little deeper, and the admission is largely unknown naturally enough, for there seems to be no ready excuse that a man can offer himself, never mind his critics. Why should this vulnerability exist, and what is its peculiar nature? This question can be answered by eliminating firstly those aspects of management that are not prone to criticism. There is, for example, the area within a manager's responsibility in which his knowledge and experience are complete and adequate. No one in his right mind can deny that a good manager is basically capable of managing affairs which are thus defined. The point is simply tautologous. I ask my chaps to do nothing that I cannot do myself is an old cry, heard in civilian as well as in military life. Yet the cry, in this highly technological age, is somewhat out of date, although nobody minds that either. A military commander can and does consult, without loss of face, specialist advice. If 35. He wants to fire a gun, he will use ballistics experts, chemists will advise him on the use of gas, psychologists on the state of the enemy's morale, engineers on his equipment, and so on. In these matters, the excellence of the good manager resides in knowing when and how to use the scientists and other specialist advisors that are on call, and to be able to judge what credence to place in them. Similarly, in industry and in government, the manager may call on accountants to install and interpret his financial and cost controls, on engineers to design his plant, on physicists, chemists, and biologists to examine the quality of his product and its purity, on economists to assess the movements of his market, on statisticians to handle his data in a sophisticated way, and so on. Here, you might argue, is the complete manager, competent and assured, knowing a great deal about his own affairs, selecting and applying scientific advice with wisdom whenever necessary. What is left? The answer to this question is all too simple when one thinks about it. Firstly, although a large number of problems will yield to the formula just expressed, there is likely to be a residue in which a conscientious manager is not at all sure what he ought to do. He has run out of knowledge, experience, and advice. Yet he has to decide. Secondly, it may be borne in upon him that the situation with which he is trying to deal is hopelessly obscured by factors right outside his own jurisdiction. He may consider that, although he has to take a decision, the right policy can be determined only after taking into account the judgments of everyone else in the managerial community of which he is a part. In a well-run organization, he will know the motions to go through to ensure that this second class of problem is treated at a higher level. But in this case, the general management organization itself may be in the first situation at the limit of its knowledge, with no particularly relevant experience, and having taken all the specialist advice that it can think of seeking. These are the vulnerable areas of management. The first is tactical, the second is strategic. Now history, disguised in the form of publications by Her Majesty's Stationery Office, relates how the armed forces tackled this problem in the early 1940s. It is interesting that no formal and general decision was taken. It seems that the answer was a natural one, which naturally emerged. It was to call in some of the country's best scientific intellects and ask them to help. This solution can be distinguished rapidly and clearly from the technique of using scientific advice in the ways enumerated above. For the men now called upon were not asked to apply their own limited expertise to problems already labeled with the words inscribed over their university chairs. 36. The respectable and generally acknowledged use of the scientist is to say to him, "You are a paleontologist, here is a fossil, tell me what you can about it." The challenge now being issued is of this form: you are a scientist, which means that you have a mind trained to investigate natural phenomena, logically to take them apart with a whole set of highly sophisticated techniques, to reassemble them and to declare what makes them tick. I have here an operation which is certainly a natural phenomenon, go ahead. And so the manager is not asking the physicist to research into the atomic structure of uranium in order to make a bomb, nor the chemist to analyze a new poison gas, nor the biologist to investigate fatigue on the battlefield. He is asking the scientist to research into operations. And this, not surprisingly, is operational research. It should at once be clear, and it is certainly most important to appreciate, that this is not the same sort of activity as is traditionally allocated to scientists. This is what is new about operational research. If there were such a scientific discipline as operationalics, then there would be an operationalist. He could investigate tactical and strategic problems as belonging to his own specialism, and he would fall into the pattern of advice with which we are most familiar. But there is no such science. To which particular branch of science, then, should the manager have recourse? The question is unanswerable. The intention is not to use the man's expert knowledge of a branch of science, but to use the fact that he is a scientist. But if the kind of science this man practices is irrelevant to the present matter, there is still one judgment the prudent manager can make. If he has to form a team to tackle his tactical and strategic problems, then he does not want the whole team to consist of physicists, nor of neurophysiologists, nor of specialists in any other single aspect of scientific inquiry. For obviously the specialist is a victim of his own training. He may be asked to forget it and to operate as a scientist pure and simple, but how completely can he do so? In short, if the whole team consists of the same sorts of people, a bias that has nothing to do with the work in hand will become evident. So that is how and why operational research came traditionally, powerfully, and perhaps necessarily, to be interdisciplinary. A few paragraphs ago it was said that the emergence of operational research was natural and informal. But it is worth taking a quick look at what actually happened. The movement began embryonically before the war, insofar as a number of civilian scientists had been helping the military to evaluate the operational implications of a new discover radiolocation. The collaboration of the people who were to become the 37 first or scientists with the people who were to make such effective use of them was thus mediated by a technical innovation. There existed an informal arrangement that on the outbreak of war this group should be attached to the headquarters of Fighter Command. There the members of the group won a quick and great success, a success achieved by junior scientists who had not yet received academic distinction or organizational recognition, but were men of high talent, zeal, initiative, and imagination, working under the guidance of experienced scientists. This is still the character of operational research. Obviously, their success could not have been achieved without support, and the personal interest of the commander-in-chief is recorded from the same period. The next move, in 1940, derived from another technical innovation. Radar equipment at gun sights gave the slant range and bearing of an attacking bomber. New apparatus was devised for providing a reading for the bomber's elevation, but it did not perform in service as it did under test. So here was another operational problem, a matter involving both science and management, but lying outside the capabilities both of the specialists who built the equipment and of the commanders trying to coordinate its use. This seems to have been the first occasion when a noted scientist was asked to apply himself to operational research. As is well known, the man concerned was an eminent physicist, Professor Blackett. And again the character of war as an interdisciplinary activity becomes clear. For Blackett's circus, which eventually became the Army Operational Research Group, included another physicist, 2 mathematicians, 3 physiologists, a surveyor, 2 mathematical physicists, an army officer and an astrophysicist. Again, too, is found the personal interest of the Commander-in-Chief of Anti-Aircraft Command this time. Thus, when highly successful operational research comes to be done in a context of change, and when the mixed scientific teams formed by or are attended to at the highest level of management, results accrue. Small wonder, then, that the work took such a hold so quickly in military affairs. 2 years after the war began there were formally established operational research groups in each of the 3 armed services. To the strategic issue. There may seem little enough to learn from all this for the Enlightenment of the 1960s. Yet, in a fundamental sense, the story reveals everything. Suppose that a large industrial undertaking has a 38 plant it proposes to expand. Capital is available to finance this expansion, and the management has a good idea of what it wants to do. Consider how this situation has come about. The company's business is based on a technology of long-standing effectiveness, but over the years many improvements have been made. Most of these improvements have been incorporated, or at least tested, in works practice. The time is coming when, partly because of the obsolescence of plant and partly because of an expanding market, a new plant must be built. Those who see this most clearly form a lobby within the management group, gradually they carry their colleagues with them. Eventually the climate of opinion is right for a decision, in which all concur, to go ahead. The lobby has not been idle. The latest techniques and machinery have been studied, the advice of engineers has been obtained. There is already a clear idea of what this plant should be like. Technical experts of every kind have been called in to discuss every facet of performance, and to estimate possible output. With this brief, accountants have been asked to prepare costings which they have based on those from previous experience, modifying the existing data intelligently to predict the effects of whatever changes are contemplated. Market research has reviewed the state of demand, and considered the conditions in which a new element of the market can be captured. Advertising has been planned. The key problem of where to site the new factory has been examined by a committee on which all these interests were represented. Everything is ready, the decision is taken, the expenditure is approved, and construction begins. All this is highly reminiscent of the preparations for war. For in war, much the same issues arise and they are handled in much the same way. What happens when operations begin? In war, it turns out that nothing happens exactly as was expected. Intelligence was defective and conditions are not quite those anticipated. Planning goes slightly awry and the unfolding of the strategy gets out of joint, causing serious delays. On the technical side, rather too many equipments that worked perfectly well on their trials misfire in the field. On the human side, people mysteriously let down the management, they do not always do as they are told, they misunderstand instructions, they even refuse to operate some of the equipment. Because of all these differences between intentions and fulfillments, the costs that were envisaged are all wrong, far too many factors have changed. And the enemy? Well, he is the last of our worries, we have not even encountered him yet. There are plenty of battles to fight against nature and the cussedness of things first. Soon. 39. The commanders are wondering whether they have chosen the wrong battlefield even. Is this a description of what happens in where in that industrial undertaking? The situation is exactly the same. As soon as it starts operating, the new plant makes a loss. Teething troubles, they say, which will be overcome. But there are some beautiful new plants that are still being subsidized 10 years later by the old plants they were meant to replace. This must be the equivalent of losing the battle, although in civil life the hard facts can often be dodged. One is not called upon to bury the dead and depart. On the contrary, one can usually gloss over the disaster. By changing the internal costing conventions, for example, the loss can be assimilated into the profits of other departments. The manager down the line who finds himself paying more than the market price for his raw material, as the result of internal transfers from the new plant at cost, will be upset. But when he is replaced, his successor will know that there were originally policy reasons for this which no one quite remembers. If the plant is sufficiently big, moreover, there are still smoother ways out of the difficulty. Disasters of sufficient magnitude can, like the charge of the Light Brigade, be turned into victories. For example, the new plant which contributes massively to the national output of the product must be a success. Everyone knows that it is the latest and best of its kind, therefore its costs are realistic, therefore its prices are generally regarded as a proper basis for computing nationally acceptable prices, therefore, after a time, it makes a profit. Prices have gone up, of course, the increases are blamed on dearer coal, electricity, or transport, on the weather, on demarcation disputes it does not matter much. The nation, knowing nothing about it, pays the bill for bad management. This illustration is not a fantasy. Examples of such procedures do occur and have been studied. It ought to be appreciated, in particular, that any organization which tends to monopoly might be conducting itself, on occasion and possibly unconsciously, in this way. The risk that such things will happen extends from large public companies, through national corporations and nationalized undertakings, to the services and other government departments. But that is a digression, the real point is to say where operational research fits into this picture. The root cause of the troubles that have been described, whether civil or military, is a failure to predict the manifold interactions of many variables in practice. In the two examples quoted, there is much experience. 40. On which to draw, much theoretical work and plenty of realistic testing. Yet the new situation will be compounded of all these things, and it is the mode of synthesis that is at fault. To illustrate this simply, if 10 small uncorrelated supply lines feed into one large supply line, it is not economic to fix the capacity of the main flow as the sum of the maximal flows of all 10 tributaries. In theory, all 10 supplies might achieve their top rate of flow together. In practice, this never happens. Conversely, it is no good specifying a completion date as calculated from a day when all of 10 components are due to arrive. In practice, this never happens either. No, new techniques are required in order to measure, compare, and predict the practical outcomes of strategic plans. These techniques necessitate work which is beyond the best that a committee of all the interested parties can achieve. This work is operational research. By now, it is used all over the world to help validate military defense strategies in advance of actual war. But industry very often disregards this lesson. Industrial ore is not often called in until all the plans are fixed. It is then asked to assist at the tactical level by making parts of the intended system more efficient. This again is one of those misapprehensions and misapplications of science, for presumably the management does not intend the result. This is the use of science for ensuring the ruthlessly efficient implementation of thoroughly bad plans. The risk of doing just this is implicit in any large-scale activity. To consider each part of a large system separately, to find a perfect solution to the problems of each part, and then to add the solution together and call the result a strategy, does not necessarily work. Almost certainly, it does not yield the best of the available strategies. This assertion can be examined in a small way on the rugby field. The individual trying to play a superb game from his own point of view, on the theory that if each player does this the side will win, may be a spectacular wing three-quarter, but he is dropped from the team because he is selfish. The strong pack of forwards playing in perfect harmony may nevertheless be stopped. The game is lost before the outsides are ever given an opportunity to open it up. The same is true on the battlefield and in industry. But it is the function of the football captain, the military commander and the managing director to see that these things do not happen. These are the leaders who must see in the whole an entity greater than the sum of the parts. The point is that the leader has no mechanism for doing this once the system he controls grows to larger dimensions than can be comprehended in one man's brain. To preside over a meeting of junior managers, each 41 of whom commands a section of the system, and to add up and reconcile their recommendations, must fall short of the best that can be done. This is what was wrong with the industrial development plan just described. The same outcome, for the same reasons, is obtrusive in national policy as for transport, fuel, education, and so on. Prediction of the effects of change in one department considered in vacuo is fairly accurate, but the interaction of these effects with the effects of change in other departments creates a totally new kind of system out of the whole. And the reason why no one man can cope with the prediction of the macro behavior of the new system is not just lack of vision. It is, to be quite precise, that the kinds of measurements he has been using change their nature and let him down. These are the circumstances in which operational research is most useful. It was argued in an earlier chapter that the scientist is not an analyst of facts, but a man who first of all determines what the facts really are. His is the responsibility for creating new measures of the system that will still be adequate to its changing state. He has to predict the macro behavior of the evolving and organic whole. He does this, essentially, as a service for the leader who is responsible for that whole. No one else is in a position to do so. It may now be clear why emphasis was placed on the role of major technical change in the excerpt from military history, for if there is a major breakthrough in any technology that is relevant to an enterprise, this changes the character of the whole system. It does not merely have far-reaching effects but actually turns the old enterprise into a new one in which the old thinking, the old costings, the old methods of control may well have no place whatever. The scientific description of the whole situation has to be rewritten, which is a job for operational research. There is a ready example to hand, one that affects every kind of activity today. This is the breakthrough in automation and computation. Given that these new facilities and capabilities exist, it is not an exaggeration to say that no enterprise is the same as it was 10 years ago. For if it is using these facilities to the full, its mode of working is radically different, its limitations are different, its opportunities are different and its entire management problem is different. If it has ignored the new facilities, its productivity has fallen, its costs have gone up, its employment policy has changed, and so on. This proposition is not philosophical skullduggery but a fact. 42. It is very widely said, and fairly widely accepted, that there has been a mysterious lag in the exploitation of these technological advances. People mumble about the slow but sure ways of practical evolution, they hope this explains the lag, and excuses it too. but the reason is different in kind from this. Automation in the 1960s is like radiolocation in the 1940s. Once it exists, the situation is new. To set up a managerial committee, advised by technical experts, inevitably has little effect. This organization is committed by its structure to an attempt to dress up the old system in modern clothes. But the old system is no longer required, in the dress of any period. The first plan for using radar was to automate the observer corps. Fortunately, those responsible quickly saw that this would not provide much of an advance but would simply build the limitations of men into the machines, and hold them back. So those responsible invented operational research, made it study the new situation scientifically as a radically different whole, and doubled the effectiveness of radar as a strategic tool. This is the recommended treatment for automation and computation today. Instead, the technical breakthrough is used precisely to automate men, the payroll application, the stock control application, the costing application, the programmed lathe, and so forth. All these developments are good enough in themselves, but the new, higher-order strategic plan that is now possible has been largely overlooked. It is a job for operational research. Perhaps there is now less impatience with the out-of-date military history of this chapter. It has much to tell about the meaning of or which has not been transferred to civil life after a quarter of a century. What the work is really like, how it emerges, what it can do, are all made clear by the evidence of past events. Contrast the understanding that has now been reached with the following statement, made 21 years later, by a senior industrialist in charge of a large civil war effort: there is nothing fundamentally new in operational research, but it does make available modern mathematical methods for analyzing facts. Every phrase, every notion, almost every word, is wrong. The remark betokens total incomprehension of the nature of this work. We have considered the emergence of operational research in a general way, and at its strategic level. But it is time to get down to brass tacks and to gain some insight into how this work is done. It is tempting to discuss a large and complex strategic problem in detail, yet this would be a massive undertaking at this stage. It is proposed instead to describe and discuss a small tactical study which, 43, has certainly become very famous in the annals of operational research. Let us adhere to the military history that has served the discussion well, and quote a last example from the war. 3. A famous tactical or problem. By the spring of 1941, the difficulty experienced by Coastal Command of the Royal Air Force in sinking enemy submarines was becoming far too obvious. The search for submarines in the coastal waters around the islands of Great Britain was successful, and depth charges were being dropped from the aircraft at a low height. Unfortunately, little success was obtained in sinking them, and it will not have been forgotten that vital supplies of food were seriously threatened as a result. What was the policy by which the attacks were being made? A depth charge was exploded by a hydrostatic firing pistol, a device which responds to the pressure of water and detonates the charge at a given depth. The depth setting on these charges began at 35 feet, and the detonation could be arranged for any depth below this. Now the theory was as follows. When a submarine is attacked from the air, it will see the approaching aircraft and dive. By the time the attacker has had time to catch up with the submarine, it will have reached a depth of between 50 and 150 feet. A calculation made by computing the speed of approach, the rate of a crash dive and the trajectory of the falling depth charge. A setting of 100 feet was therefore the recommended practice, based on specialist advice. The typical problem in operational research has indeed this general appearance. There is a technical competence, a well-founded policy for applying that competence to achieve results, a practical state of affairs to which this capability and practice appear appropriately to apply, sane specialist advice on the mode of application, and there is failure. More than 20 years after the events now being described, this prescription for failure is being followed somewhere in every government department and in every factory. How does the operational research team that is called in set about its task? In the first place, it has to be recalled that this is not an exercise being carried out on a blackboard for a class studying ballistics. It is a practical operation of war, in which the actual facts can be investigated. They were. The facts uncovered revealed that the basic assumptions of the theory were being falsified. It is just not good enough to say that the submarine sees the aircraft coming. Perhaps it does, but at what stage? This depends on the weather, on the visibility, the position of the sun. 44. And the roughness of the sea. It depends too on the alertness of both crews, which will see the other's craft first, and how soon afterwards can they mobilize themselves for action. In short, if one considers the real-life problem, and not an idealized classroom version of it, one immediately sees the need for tactics which are robust in quite a large variety of circumstances. All sorts of variables begin to affect the situation which would not at first sight appear relevant, and let us remember that even the list of variables just enumerated supports sets of more complicated causal influences that lie behind each variable. Fatigue, state of morale, even whether the captain of the submarine enjoyed his breakfast, enter into the picture. So the whole problem, not just the real problem, must be studied not indeed by examining and measuring every factor, but by using an approach of sufficient flexibility to incorporate the full range of possible variation which might be encountered. What next emerges is the critical fact that if the submarine has indeed reached a depth of 100 feet when the depth charge explodes, it has had time to maneuver below the surface in a way which makes an accurate prediction of its whereabouts almost impossible. In this case, even if the policy for attack is right in theory, it is simultaneously wrong in practice, for it cannot actually work. When the idealized problem is enlarged to real-life dimensions, the probability of not hitting the point aimed at must be multiplied by the probability that the submarine will not be in that location, and the product, which is the probability that the submarine will not be killed, becomes very high. Thus the only feasible solution is to catch the submarine nearer the surface, which again the practical facts revealed was perfectly possible. For 3/4 of the time, the submarine simply did not manage to dive as quickly as had been expected. This is a very good example of how an attempt to contain the worst possible situation in fact invalidates the whole policy when this boundary condition is seldom met. Through this examination of the actual facts, the measurement of the actual operations and the computation of real-life probabilities, it was shown that a practical policy should concentrate on hitting submarines still at the surface or submerged for less than 15 seconds. The corresponding computation of the depth setting then showed that the charge should detonate at 25 feet. And here we have to note a remarkably characteristic feature of an operational research solution. It often lies outside the framework of possibilities ever contemplated by the managerial solution. This means that the mixture of experience, knowledge, and straight thinking by which the management's policy has been reached, has managed to delineate a range within which the answer is 45. Expected to lie, and the answer chosen is roughly in the middle of this range. The inexplicable failure of the management's policy, which is normally the signal for introducing operational research, often means that the best answer has unfortunately been excluded from the collection of plausible policies that management is prepared to believe offer solutions that really count. In this example, that state of affairs is exemplified for us by the scale on the side of the depth charge, which had a minimum value of 35 feet, and a range of plausible solutions between 50 and 150 feet. With this apparently flexible array of possible actions laid out, and in this case engraved on brass, how can anyone be blamed for not realizing that the answer is completely outside the possibilities envisaged? Returning to the history, we find the scientists advocating that, since it is impossible to set the charge at 25 feet, the minimum depth of 35 feet should be selected, a depth still much shallower than anything yet attempted. And we find the second recommendation being accepted: new gauges should be made to encompass the still shallower depth that is really required. The new policy is put into effect. At once the rate of sinkings rises dramatically, and, by the time the new gauge is in action, Coastal Command is recording a 700% rise in sinkings. Thus, without years of special research and development effort, but simply by breaking through a conceptual barrier in policy making and by studying the operational facts, a tremendous success is achieved. The whole picture is changed from everyone's point of view. Prisoners taken from sunken submarines now tell their interrogators that the amount of explosive in British depth charges has been doubled. Finally, life is also considerably changed for those whose job it is to advise management on the detailed methods of working within a particular managerial policy. Such specialists as accountants and engineers can fulfill their functions only within the ambience of the range of policies with which management has chosen to work, and their conclusions have no relevance to other policies which have never been formally envisaged. This point is exemplified in the present story by the engineers responsible for the hydrostatic firing pistol that detonated the depth charges. When they were asked to change the gauge so that it could be set at 25 feet, they were faced with a completely fresh problem. For this is not simply a matter of screwing on a new gauge to the side of the charge. As was said earlier, the firing mechanism is activated by water pressure. But, when a depth charge enters the water, an air cavity is created behind it and the firing pistol cannot be relied upon to come into contact with the water until the charge has been submerged to a depth greater than 25 feet. And 46. So a new research problem is created. Historically, the shape of the depth charge had to be altered, so that the part of its case carrying the firing pistol would slap against the water itself and not be within the air cavity. There is a simple and straightforward operational research story, a famous one too. The setting is not grandiose, but the results were of huge importance. It might be worthwhile to read the story through again, for in the next chapter 6 key thoughts about the nature and use of operational research will be developed at some length, and each one of them will be derived from the history of the submarines that would not sink. 47. 4. The Wedged Bear. Veen ergo mihi liberum sustinentem prelegira, ad ursum inter angusta arte in fixum consolendum idoneum. A Leonard in Winnie Ilpu. Or, in the original. Then would you read a sustaining book, such as would help and comfort a wedged bear in great tightness. A. Milne in Winnie the Pooh. 1. The first tightness, stereotyped scientists. The 3 chapters completed have doggedly pursued the theme that operational research is a radically new kind of activity which cannot be properly understood unless a radically new look is taken at both the scientific and the managerial functions. Most of us work, that is to say, on stereotyped notions of these things, notions held from tenacity, authority, or a priority. In general, as argued in Chapter 2, this is no bad thing, but in following the story of operational research that is also being unfolded, it is vital to escape from the grip of these stereotypes. The hero of this chapter, Winnie the Pooh, consumed all the honey he could find in the home of his friend Rabbit, and became firmly stuck in trying to emerge. We have just burrowed into the origins of ore and found some honey, but in climbing out of the past we may well become stuck in our stereotypes and misinterpret all that has been said. A wedged bear in great tightness, discovered Pooh, must be starved out, he should be sustained during this process by literature. Let us then pause for a while, and use this chapter as a sustaining book. The stereotype of the scientist as a man who does physics or knows. 48. Chemistry or reads biology has already been attacked. The scientist is, we saw, a man who investigates the nature of the world. His training, however, gives him a bias. For this reason, when a new area of study is being opened up, it is well to use an interdisciplinary team. The emergence of this sort of group in the early development of operational research has already been detected in the historical section. Now, in order to shake off the first attack of tightness, the matter is considered in more detail. In the first place, the brand of scientist who is already professionally concerned with the kind of problem that faces the management stands as little chance of escaping from the orthodox thinking of his own discipline as the manager stands of escaping from orthodox practice. The scientist, like those he seeks to advise, tends to be a prisoner within the accepted boundaries of the existing solution. In the case of the submarines that would not sink, there can be no doubt that plenty of scientific advice had been used before ever the OR team arrived on the scene. But that advice must have been stereotyped. It saw the problem as an abstraction on a blackboard, not as deriving from a real-life operation. The scientist too has been stereotyped, by the management and by himself. Often the research departments sponsored by industry and government house scientists of this kind. For example, if a firm makes a washing powder and its rivals claim to purvey a powder that washes whiter, the scientists in the first firm will be set to make a powder that washes whiter still. From a scientific point of view, this chase towards ultimate whiteness may be interesting. It may involve good science. For instance, it may be possible to detect by spectroscopic analysis that each generation of powders does in fact wash very slightly whiter than the last. But exactly where does this get the management? Will the consumer take note of the powder that washes whiter than white, and prefer it? No, the management has become trapped in an orthodoxy and in a stereotyped notion of scientific advice. Another example, the manager of a heavy steel mill may observe that when he rolls an ingot into a long product of small section, which has to be cut up into relatively short lengths, unsaleable pieces are left over and have to be scrapped. There is a tolerance on the lengths to be cut. If one knew the total length of product rolled from the ingot, and could do some calculations, it would be possible to make the cuts in places which would much reduce the amount of scrap. Unfortunately, the product must be cut very quickly, before it begins to cool. There is no time to measure the total length at all accurately, still less to make the calculations. Now scientists can do something with this problem. They can install automatic measuring devices, coupled to an electronic computer, which will announce where to make the cuts. Here is the expert advising the management, and making a worthwhile advance. But the expert advice is of the same persuasion as the management itself, a persuasion that says this job is to do with engineering and nothing else. In fact, however, the steel is being sold against an order for steel, and the order is part of a lengthy order book. If the computer had access to that order book, it could compare various ways of cutting the steel with the requirements of various customers, then there need be no short pieces left over at all. This solution is several times more profitable than the first solution. But in practice the production manager regards the order book as the province of the sales manager. It is no concern of his. The scientific advice he wants is engineering advice, and the engineer in turn thinks of the salesman as a smart fellow whose fortunate job it is to take people out to lunch. The scientific advisor of the sales manager is an econometrician who does not concern himself with works practice. The specialist advising the financial director is an accountant. He computes that a% saving in the yield of steel is worth so many £1,000 a year, and that the computer installation will pay for itself. Everyone is then satisfied with the wrong decision. An advance has been made. The orthodox divisions of management have all operated successfully. A number of experts have been used in a stereotyped way. The thinking has been shackled by the orthodoxy and the stereotypes, and a big opportunity has been lost. The interdisciplinary or team of scientists, properly led, should not make these mistakes. They do not play individually stereotyped roles. They do not owe special allegiance to one branch of the firm. This is why an operational research team is a different kind of entity from a committee, consisting of the same people, in which each man is there to represent the point of view of his boss's sectional interest. There is a second reason for making an operational research team interdisciplinary, and for escaping from the stereotype of scientific advice. If operational research is to lead management to a completely novel solution, it cannot be predicted in advance which branch of science will be most useful in suggesting the breakthrough. In the case of the submarines, for example, ballistic experts and explosives experts were not the people to help. Think of the actual operation and what happened. Scientists used to the theory of probability, scientists used to measuring the speeds of human response, scientists used to evaluating fatigue and 50 states of mind. These were the people actually required. Thus management replaces its familiar ballistics and explosives team with an OR team of statisticians, physiologists, and psychologists. It is easy, with hindsight, to recognize that these specialisms are relevant to the situation. It is not always so easy to see this before the problem is solved. So it is important for management to accept the advice of operational research people themselves, that or teams should indeed be interdisciplinary in character. This point is underlined because there is a strong tendency in industry today to accept for or work only the kind of scientist that one would expect to meet within the industry anyway. In metallurgical industries, management is accustomed by now to meeting engineers, physicists, chemists, and metallurgists. They are puzzled by the arrival in or teams of biologists and sociologists, for example. But these are the very people who will be of most use in solving managerial problems of tactics and strategy. They are neither stereotyped nor committed in advance to a point of view. To the second tightness, stereotyped problems. The wedged bear has lost one degree of tightness, its stereotype of the scientist. Now we turn to the question of the problem that has to be solved, for that has a stereotype too. This may be shortly described as the assumption that a problem really resides where its symptoms are first noticed. Thus a problem arising in the course of production is assumed to be a production problem, a problem arising in sales is assumed to be a commercial problem, and so on. A scientist set to work within the limitations of the stereotype of what the problem really is has little hope of success. The point to be made is this: operational research must encompass the whole of the problem situation, and management may not succeed in defining what this is. Given that the solution to the problem lies outside the accepted boundaries of existing solutions, it is more than likely that the problem area itself extends beyond its traditionally recognized limits. Only the operational research team, then, can be held responsible for defining the scope of the problem. This is perhaps a revolutionary point of view. Certainly it is one which management often resents as an abrogation of its prerogatives. But it is a rational attitude and one which management ought to embrace. It is worth recalling that many of the problems that most need to be solved, which are those very problems in which the solution has not only eluded management but has 51. Not even been envisaged, arise precisely because of the way in which a company is organized. For practical managerial reasons, a company is divided into clear-cut areas of responsibility, and the manager, whose authority derives from his position in one of these areas, is conditioned by the whole of his experience to seek solutions in which he can feel confident from personal knowledge, and over which he can exert personal authority. But problems are not respecters of the company organization, nor of the talents of the company servant who first meets a symptom of the problem. Of course, it is the custom to argue that good management ensures adequate consultation across the departmental barriers, and that good organization will even create an interdepartmental committee structure whereby permanent liaison is secured. The first sounds very well when attested to in the happy afterglow of a company dinner, the second looks very well when inscribed on an organization chart. But as people interested in real operations, we simply have to face a few facts. Reflect how people actually discuss their colleagues in other divisions of the company. They are not seen as men who have something to contribute to the problem, but as men who just do not understand it. Therefore they are people who, despite many pious expressions of goodwill, have to be outsmarted. Reflect too how committees of liaison actually work. A busy executive, who has in all honesty been intending to study a set of papers since the last meeting, suddenly has them thrust into his hand by a secretary who announces that the car is waiting and he must hurry or he will be late. He thumbs through the papers during the ride, wonders what they are all about, wonders what some of his esteemed colleagues are up to, decides that at all costs certain ideas that have been mooted must be scotched, and works out conventional explanations for not having done the things he said at the last meeting he would do. In fact, he has no real need to worry. The chairman of the meeting to which he is speeding has already written the minutes in his mind. Yes, this account is an oversimplification. Even so, where is the senior executive of a typical modern company who can really claim to believe that the large problems of tactical and strategic management with which his company is concerned are really studied on an interdepartmental and interspecialist basis so that the solution adopted is undeniably the best? Operational research has this to offer instead. If a committee of responsible people is formed, they can commission an or study of the problem before them. This will mean that a group of scientists, which is interdisciplinary, which has access to all the facts, which has permission. 52. To investigate difficulties wherever they may lie and to pursue ramifications of the problem wherever they may lead, is engaged full-time in objective scientific pursuit of the right answer. While this is going on, the members of the committee can happily go about their business. The OR report is then produced to the committee, and will have roughly the following form. The problem will be tentatively defined, possibly in terms rather different from those envisaged at the committee's first meeting, and an attempt will have been made to describe the whole of the newly discovered problem area in a systematic way. The facts bearing on the problem will have been collected and collated, and fitted into this description. Various scientific activities will have been undertaken with a view to examining suitable courses of action. In the end, a number of possible answers will have been formulated, which will be laid before the committee with an assessment of the probabilities, costs, risks and potential benefits of each. In short, the precise problem requiring managerial decision will have been pinpointed, and the area of uncertainty that surrounds it narrowed as far as possible. The committee may then have a meeting to discuss this report. Probably there will have been no time in which to read it, and therefore the meeting might well begin with an exposition of the OR findings by the man who led the OR team. He should then remain in attendance while the members of the committee discuss these findings, seeking further elucidation as they proceed. At the end of this meeting, the committee will know exactly what has to be agreed at the third and last meeting. In the interval before this occurs, there is no real need to do further detailed work, for which the committee members certainly have no time. During this period, it seems reasonable to rely upon the capacity of the human brain to incubate decision. When the third meeting assembles, if there is any substance in the company's claim to managerial teamwork at all, the proceedings should be plain sailing. For the results of incubation, coupled with some routine committee work, should produce an agreed decision. The importance of studying the problem as a whole, and not merely as a collection of local difficulties, emerges from the story of the submarines. As was said before, it is easy to view that problem as a matter of trajectories and explosives. It is only when a circle is drawn round the whole problem area that successful science can begin. In this example, there is no particular difficulty in detecting the boundaries of the whole problem. In other studies, this detection can be extremely difficult. The reason is fundamental, a point from philosophy. The philosopher Hegel noted that the relations by which terms are related are an integral part of the terms they relate. That is to say, the fact that a horse is bigger than a dog is part of dogginess and horsiness as well. If this dog were not smaller than a horse, it would not be the dog that it is, it would not, very probably, be a dog at all. This being so, everything in the universe is connected to everything else by a series of relations subsisting between everything in between, and if each relation helps to determine the nature of the thing that is related, then everything is what it is because everything else is what it is. This is perhaps rather confusing, and sounds metaphysical. But the resulting thought is important. The totality of what exists is an integrated system, and anything split off from the totality and considered separately is incomplete. In practice, we have to split things off and consider them separately, but we shall have to be extremely careful how we do it. An OR man who considers a suitable size for an inter-process stock would be mad if he failed to consider the cost of investing in it, or if he insisted on considering the relevance of the position of Venus. Somewhere he has to stop, somehow he must determine the boundaries of the problem. The point of this paragraph is to say that this is the most difficult problem in operational research. There is no standard technique for achieving the best answer. At least let us recognize that there is no such thing as a right answer. In practice, the scientist needs to enlarge the scope of his study in every dimension until the factors he is bringing in seem to make no tangible difference to the answers he is getting. Then he feels safe in stopping. At the very least, this process is going to take him outside the apparent problem area by one step in every direction. Most notably, if he is working for one of 5 managers all responsible to Jones, he will 54. Have to consider the problem as Jones sees it. If this makes a vast difference to the way the tentative answer looks, he had better go on to the organizational zone presided over by Jones' boss. This is a process dictated to the scientist by the interrelated nature of the world. The manager who commissioned the problem really must recognize this, and not take umbrage. Other managers, who have nothing to do with the remit and into whose preserves the or man trespasses, really must collaborate. More trouble is caused in the practice of or by this business than by any other aspect of the work. More potentiality for high profitability in the use of or is thrown away through failure to see this than through any other cause. The management problem has no stereotype. It is unique. It is malignant. It may involve all sorts of factors that no one imagines to be relevant. The job of the or man is to handle it. Do not tell him what the problem is, nor where his task may take him. Tell him what the trouble is, and send him to find the problem. That is the first step. To escape from the stereotyped problem is to lose another degree of tightness for the wedged bear. 3. The third tightness, stereotyped science. The third of the important lessons about operational research that can be drawn from the wartime example of the submarines has to do with the question of chance. This is the God-given uncertainty of the future for us humans, the likelihood that something unexpected will happen, the risk of failure and unforeseen difficulty, the so-called human element, and so forth. People often assert that science cannot cope with the questions of chance thus enumerated. Unless it can, indeed, operational research as a tool of management policy would be worthless. The process of unwedging that bear especially demands a right approach to this matter. It is as usual important that stereotyped opinions about modern science are not accepted uncritically. After all, the idea of scientific method that many senior people entertain is based on routine experiments through which they were conducted in the third form. Moreover, their beliefs about the nature of science and its outlook on the universe it studies may have been formulated somewhere between 20 and 50 years ago. Just how carefully has anyone had time to review this matter since? The new achievements of science are manifest to all, but this question of the underlying nature of the work and of the sort of universe in which modern science thinks we exist is rather more fundamental. 55. For example, nature consists of a collection of various kinds of system. Early attempts to describe these systems were undoubtedly conditioned by the ways in which men had so far learned to manipulate nature. That is to say, the engineering competence of mankind determined for centuries the pattern of thought about the universe which naturally arose. At the time of hydraulic engineering, people seriously contended that the human brain squirted thoughts around the body in pipes which, anatomically speaking, they imagined the nerves to be. In the great age of mechanical engineering, the brain was envisaged as a system of pulleys, cogs, and levers. And so, coming to our own era, the early discoveries of nuclear physics were pictured in highly concrete terms. Surely we have all met the billiard ball version of the atom in which hard, spherical electrons circulated like planets in orbit around a larger sphere that was the nucleus of an atom. Perhaps our physics masters had all misspent their youth in acquiring proficiency at billiards. At any rate, the picture had this form. That picture is laughable and almost useless today. In fact, the tremendous breakthrough of modern science in physics, in genetics, in biochemistry and many other subjects, is largely due to a realization that the universe is a collection of probabilities, and to the development of mathematical techniques capable of uttering descriptions of nature in these terms. The universe of hard solid separate things that collided with each other and bounced off, that rubbed against each other and lost energy, that became involved in sequences of events which could be neatly labeled causes and effects, may still be the universe of engineering, but as the universe of science it has gone forever. Each of the fundamental particles of matter is now pictured as being the size of the whole universe, and none has a definite location. Some locations are more probable than others, and matter is an agglomeration of these probabilities. But this is not in any sense at all an attempt to explain modern science. These points are made simply to emphasize that science is now supremely competent to handle probability, chance and mischance, risk and likelihood, and in general the vicissitudes of real life. Secondly, it is undoubtedly a mistake to think about situations in terms of a clearly understood and absolutely determined set of developments, into which nature wickedly imports errors, and within which sportive deities play dice. Here is a thought on which to reflect: everything that happens is grossly improbable anyway. For example, a hand dealt at bridge which produced a complete suit for each player would cause consternation. Assuming that the dealer were a personal friend, the occasion would be worthy of a letter to the Times. People would 56. Compute the very long odds against this occurrence. What they might not realize is that every other hand played that night, and indeed any hand at all that can be dealt, is exactly as improbable as the one that divides the suits evenly. All these hands convey no sense of wonder, because they just are not interesting, but the play of probability is just the same. Thus we argue that the behavior of any natural system, which of course includes an industrial operation, is best described as a system of interacting improbabilities. A modern scientist has a considerable armory of techniques with which to investigate that system and write it down. A real depth charge, one that is dropping from a real aeroplane in real weather and under real psychological conditions, will not arrive at a point in the sea with the precision that a dotted trajectory is drawn upon the blackboard. What is more, a real submarine that has already been submerged for 1 minute and has reached a depth of 100 feet will have begun to maneuver. It will not be where the chalk cross is either. So, the intersection of the trajectory and the path of the submarine, as drawn in the classical exposition by the old-time tactician, actually depicts a gross improbability, multiplicatively compounded of two independent improbabilities. And the outcome is, no sinkings. But talk about the system in the way of modern science, define the areas of action in terms of probability theory, select the tactics which will bring the shapes of the two zones of probability into some kind of conjunction, and the chances of the bomb and the submarine colliding are brought to a maximum. This is the best that science can do. It offers no certainty in a universe which is now formally regarded as uncertain. It does offer an optimal strategy on the strength of such information as is available. But if it results in a 700% increase in effectiveness, who shall complain? The industrial parallels to this situation are legion. One cannot hold enough stock to guarantee that it will not run out. One cannot maintain plant so well that it is certain not to break down. One cannot obviate the risk of losing the most treasured customer. And if one adopts a crude, deterministic concept of profitability, and sets out to maximize it forthwith, the likely result would be to sell the company's assets and distribute the money to the shareholders. Life, as we know, is more complicated than this. We deal essentially in the judgment of probability. Thus the third key feature of our work to which attention is here drawn, is a facility to discuss these probabilities in scientific terms, and to make the managerial leap in the dark a little more informed, a little less problematic. 57. Here we have considered one of the most disastrous aspects for management of the stereotype of science. Experience insists that this misunderstanding is widespread. It is one of the 6 powerful squeezes of tightness that can assail any wedged bear. We shake it off in one sentence: business operations are uncertain, and all future events are improbable, but these improbabilities can be measured and manipulated, and from them a strategy can be scientifically contrived. Note that this is not the right strategy, it cannot even be called the unqualified best strategy. It is the strategy that best matches the managerial policy and intention. For the fourth tightness, stereotyped solutions. The fourth of the points that emerge from a consideration of the submarine story is in many ways the most important. The idea involved is simple but powerful, and something of a challenge. To introduce it, a thought will be taken from mathematics and another from psychiatry, and a joke that is both funny and deadly will appear in cold print. The mathematical idea is that of a phase space. Now the tools developed by mathematics for handling quantities make it possible to enumerate an indefinitely large number of variables, to measure things that are indefinitely big, to ascribe numbers to processes that continue indefinitely, and to refine the scales of quantity indefinitely by slipping in a new number between any two existing numbers however close together they may be. So there is for the mathematician a great cosmos of quantity, reaching out into eternity and infinity. In the more subtle regions of mathematics, it is capable of considering even infinities of infinities. When mathematics comes to be used, however, statements about a situation that has to be described are written down. These statements may be, for example, equations, and as everyone knows the main variables in these equations are designated by letters. Now any particular set of equations limits the concept of quantity in general. It does not carve off a particular area of the universe of numbers as if one were to say between 5 and 17, because the numbers represented by the letters in the equation may be of any size at all. No, the universe of quantity is limited by these equations in that they select a particular kind of space and exclude other kinds. Plain Euclidean geometry chooses to talk about flat areas and forgets height and depth. A linear equation envisages the universe of quantity as a great mass of straight lines. One can imagine a prickly ball made up of an agglomeration of dressmakers' pins, inside which space is defined only by straight 58 lines pointing in all directions. Just as the inhabitant of a Euclidean space knows no height, the inhabitant of this ball would know no curvature. When a mathematician sits down to describe a real-life situation in mathematical terms, then, the kind of mathematics he begins to write selects a kind of space. As he continues to write equations down, he begins to define an area within that space. This is not because he is fixing actual numbers beyond which he is not prepared to go, it is because succeeding equations affect the earlier ones and limit their possible range. For example, my friend's house is roughly south of mine, it is not further west than southwest and not further east than southeast. So far no direct compass bearing has been put forward, no definite figures have been given. But the conditions laid down have successfully eliminated 270 of the 360 points of the compass from the search. The problem that is set to find the house now has a phase space, it is a particular, delimited chunk of plane space, with no numerical limit to the southward. This is a trivial use of the term concerned because we could quite easily describe all this in simpler ways. But recall that problem situations in real life have a large number of dimensions and not just two, and also that moving through the spaces generated by equations in many variables cannot be prescribed in terms of compass points. In these large circumstances, the concept of phase space becomes important because it picks out a useful and relevant framework of quantity from the vast cosmos of number. Within this framework, if it is properly selected, may be discovered the solution to the problem. The second special concept needed here is that of thought block. Earlier on, the method of tenacity was discussed as a mode of thinking and fixing belief. Remember the cars opening up a snowbound countryside, which by their passage facilitated particular pathways through it. This, it was said, is the mechanism by which the brain learns to find patterns in the world outside. The brain becomes conditioned. This process of conditioning, it was further said, is vital to survival, for in its absence the world would appear entirely incoherent and unpredictable. Now a human being faced with a problem has an infinite number of possible reactions that he could make, and this universe of decision is like the universe of quantity discussed just now. There are no limits, other than those prescribed by the basic laws of nature, to what the human response to any stimulus can be. Someone offered a cigarette could respond by jumping off Beachy Head. Experience has, however, taught the brain to make coherent patterns of social behavior as of everything else, and the range of suitable responses to the stimulus is 59. Fairly clear. In short, the problem presented by the cigarette offerer has an infinite set of possible solutions, within which a phase space has been marked out by the man at the receiving end as containing the solution he will actually give. Most civilized men have marked out roughly the same phase space for a simple social situation of this kind. Even so, the phase spaces of the cigarette offerer and of his friend may not quite overlap, and if the friend chooses a response from the edge of his phase space which is not shared by the other man, then he will be taken to have said something rude. For instance, "No thanks, I am trying to give them up" is likely to be acceptable, whereas the reply "Not likely, I shall enjoy watching you die of lung cancer" is not. Note, moreover, that a savage who has never seen a cigarette may classify the act of being offered one in some completely alien phase space. For instance, he may classify it as belonging to the class of hostile actions and punch the man on the nose. Collecting these ideas together, we now apply them to serious situations. The phase space for the solution of a managerial problem exists in the head of the man who contemplates it. It is therefore unique to that man. For a given problem, the phase spaces of the solutions envisaged by the production manager, the accountant, the engineer, and the salesman are far less likely to coincide exactly than they are in the case of the simple social situation. The experiences, and therefore the learning and adaptation, of these men are different. So what is the best solution for the company? The solution normally adopted quite obviously lies in the common phase space, that is, in the area of overlap between the phase spaces of the individuals who comprise the management team, but there is no guarantee that this gives the most appropriate answer. The company itself has no brain. It has a phase space within which it always operates, but this can only be interpreted by human beings who inevitably get the company's phase space confused with their own. But suppose the company had its own brain and was aware of its own phase space. The answer to a particular problem might then lie on the fringes of this space, in an area not belonging to the phase space of any one manager in the organization. The best answer to the problem would therefore be missed, because it would be strictly inaccessible to the management. The thoughts of a man concerned with this particular problem cannot break through the barriers of his own facilitated pathways to reach the goal. This situation is called thought block. Here is the joke. A man went to see a psychiatrist who asked him what was the matter. The man said that nothing was the matter but his friends. 60. And relations kept telling him he ought to see a psychiatrist, so he had come. The psychiatrist asked whether they had given the patient any clues as to why they thought he should make the visit. The man replied, "They seem to think it strange that I should be dead, but I cannot think what death, after all, is natural enough." The psychiatrist tried in vain to convince the man that he was not dead. The man would have none of it. And then came an idea. The psychiatrist secreted a pin in his hand. "Tell me," he asked, "do dead men bleed?" The patient laughed immoderately, "Of course not." With a sudden movement the psychiatrist scratched the patient's hand and blood flowed. "How about that then?" The patient looked incredulously at his hand. "Good heavens," he replied, "dead men do bleed." This story about thought block may be funny, but is it sufficiently deadly as promised? If not, consider the following actual experience. A famous company made slithy toves, and very little else. An operational research team working on a strategic development plan for the company had been evaluating the effects of a predicted collapse of the market for slithy toves, and a simultaneous increase in the national production capacity for them. The man was unfolding his prognostications about the future to a director who, not surprisingly, was looking rather grave. The director asked whether any ideas were emerging from the study as to what should be done. The man said yes, it certainly looked as though fairly large-scale investments planned for the improvement of slithy toe productivity should be switched to providing plant to manufacture alternative products. Gradually the director's brow cleared, and a smile spread over his face. He put his arm around the shoulder of the man. "You are a clever chapter," he said, "but I do not believe you will ever understand the facts of this business. Please try to keep your feet on the ground, my boy, and realize that we don't make alternative products here, we make slithy toves." And that happened. Because the submarine story, on which this chapter is a commentary, was primarily concerned with just one measurement of the total system, namely the depth at which the explosive charge should detonate. It provides a simple one-dimensional example of this thesis. In this particular dimension, the phase space of the set of acceptable solutions was marked on the side of the depth charge, very likely engraved in brass. 50 to 100 feet was the phase space in the minds of those most concerned, and, in taking the calibration of the gauge to a depth as shallow as 35 feet, the designers must have felt that they had allowed 61 for all possible contingencies. In doing so, they at once reflected and reinforced a thought block. No one working within this situation was at all likely to entertain the setting of 25 feet that actually worked. This is the reason why it takes an objective, scientific, interdisciplinary investigation to arrive at a solution outside the phase space, a study undertaken by men who are by definition not prone to this particular thought block. A fairly detailed exposition of all this has been given, because it seems most important to accept that the manager who has failed to find this kind of answer is not culpable. He should not be labeled as incompetent, for if managers allow themselves too readily to wander imaginatively outside the phase space set up for them by their own knowledge and experience, they become rather dangerous. To go back to wartime prototypes, a Wingate or a Popsky has his impressive uses, but he is not likely to emerge as the chief of the Imperial General Staff. A CIGS, however, who works within his acknowledged phase space and at the same time employs operational research teams to make scientific investigations outside it, is getting the best of both worlds, provided that he can sunder the thought block when it has been demonstrated that he should. Fortunately, there have sat in Whitehall men who have done precisely this. Unfortunately, senior British industrialists have not taught themselves to use or in this way. The few industrial parallels seem to have occurred in the United States. In general, the bear seems firmly wedged in the tightness of stereotyped solutions, and every experienced or scientist could give a dozen examples of particular problems mishandled as a result. The existing organization is likely to come very close to a good answer which does lie within its own phase space of solutions acceptable to all the managers, because there will be no thought block to prevent its so doing. Then the reason for employing operational research at all is to see whether there is a solution outside. If the report is then rejected on the ground that the proposed answer is outside the managerial phase space, while no one makes any effort to break through the associated thought block, this fourth degree of tightness will trap the bear forever. 5. The fifth tightness, stereotyped payoff. Next, and fifthly, it is worth remarking that the kind of activity in the service of management here discussed is perhaps the only kind in which very large benefits are possibly obtainable with a very small outlay of 62 effort. But to attain these benefits, another stereotype must be demolished. It is often said that an operational research study may go on for a very long time, may consume the effort of a number of rather senior scientists, and may therefore be rather expensive. All this is true. Scientists are not such fools as to pretend they can master the complexities of a really massive strategic exercise in a few minutes. The managers who are so quick to point out that this is the case, can hardly complain of the cost of the study that is made. The real point to seize on is the potential payoff. This was, in the submarine example being examined, a 700% increase in effectiveness. But can operational research, in proposing to make a study at a given and fairly high cost, really guarantee a payoff of this order? The answer is no. In the first place, there may not exist so lucrative a solution, and management must be prepared on occasion to pay the price of the investigation for the satisfaction of knowing that this is so. But, more usually, the reason why the scientist cannot guarantee such a high return is that he cannot tell in advance whether the manager will be able to cope with his solution in terms of thought block. All too often, the reaction to the or results will be we make slithy toves. This risk arises in particular because of the watertightness of executive and administrative divisions in industry and government. Often the best solution will require an organizational uncoupling, a rearrangement of responsibilities. Consider the classic example of inventories of spare parts. A company making elaborate machinery has to hold stocks of spares against the demands of its customers. As will be seen in a later chapter, operational research has developed many techniques for operating such a system of spares at a minimum cost. But if there is a very large number of parts involved, no amount of scientific effort can minimize the requisite amount of information about all these parts that has to circulate within the control system. Thus, typically, one can expect to find expensive computers handling all the data required. Yet how many of these spares are really necessary? Could the design of the machinery not be rationalized, so that there are more standard components? If so, the raw total of spare parts involved in this business could be cut down, and the inventory control problem is diminished in complexity by at least the square root of this reduction. So often, this fact is obvious to many within the organization. But design is the responsibility of some person who flatly refuses to accept that financial and commercial pressures ought to be allowed to influence his work. His professional amour propre is at stake, and he is able to defend it by specious talk of maintaining 63. Quality and so forth. General management itself, if it is aware of this problem lower down, tends to regard it as a human problem, a matter to be settled in due course by better selection of more amenable managers. They feel that the man concerned is so good at his job that this price will have to be paid in order to retain his services. But surely this is to misconceive the problem. If general management were to seize on the arguments advanced in the last section to justify their attitude, they would be misdirecting themselves. For the point is not that this design man has a thought block, but that the general management has its own thought block at a higher level of management. The organizational phase space within which they are working is the existing structure of their company. Problems of this kind may have to be handled by altering the organization. The human organizational structure may need adjustment as a problem-solving phase space, so also may the physical organization. That is to say, a factory is a system for turning raw materials into finished goods, and this system has to be uncoupled at various places for many reasons. Among these are the production engineering methods employed, the need for inspection, the dispersal or conflux of flow lines at certain points, and the sheer limitation of size of the facilities any one manager can control. But the particular uncouplings that exist in the factory are, after all, only one of an infinite set of possibilities. They exist only for historical reasons in the form they have now, and it could be that the newer technology, the improved methods, the change of personnel and the changing balance of products all demand a physical reorganization based on considerations supplied from a new organizational phase space. Very often in the metal industries, for example, material has to be cut up at a certain stage in order to ship it to customers who will use it as raw material for the next more finished product. This cutting up becomes standard practice. Subsequently, the company itself lays down production facilities for doing the next more finished job itself. But the established practice for cutting up material is continued. The fact that the next process involves sticking the pieces together again goes unremarked. Thought blocks, aided very powerfully by special languages, prevent our defining a process as anything other than it has always been. Whatever is involved in implementing an operational research solution, a consideration to which we shall turn next, the present point is that the payoff from an investment in an operational research investigation is more largely determined by the management than by the scientists involved. The management does not receive what it pays for, but what 64. It demands and can assimilate. Consider the present reputation of operational research in some of the companies that have had internal departments specializing in this work for some time. Possibly the results are unrecognizable as outcomes of or by the standards of this book. If so, who is to blame now? Managements are often loath to install new high-level activities in an established company because they create organizational difficulties and salary anomalies. Some monumental thought blocks are encountered here. Be that as it may, it is a fairly common practice to evade the difficulties by appointing some bright young mathematician, fresh out of the university, as an operational research officer. He presents no organizational difficulties here, of course, because of his juniority. He lunches quietly in a junior mess, he does not confront senior managers, and he is paid about the same as a first-rate shorthand typist. The theory is that he will grow, that is, he will develop gradually within the organization in a natural and satisfactory way. If this young man keeps fairly quiet, he will gradually be assimilated into the organization and we shall hear no more of him. If he begins to be difficult, however, and to discover what operational research is really all about, and to advocate its proper use in the company, there is certain to be trouble. Probably the young man will leave. At this point, the more complacent kind of manager can be heard to say that he was not much use anyway, and had never once proposed a fundamentally new policy that could have been laid before the board. All this is sad. What is, on the other hand, highly satisfactory is that operational research properly used can often increase effectiveness by an order of magnitude or more at no other cost than the money paid for the study. This compares favorably with the years of expenditure which may well be involved in achieving effects of comparable value by research into the product and its mode of manufacture and subsequent development. But it cannot be done while the tightness of the payoff stereotype holds management in its grip. This form of trouble is closely allied to that discussed in the previous section, for the unusual payoff cannot be dissociated from the unusual solution. Nevertheless, there are separate issues here. While management does not know in advance what could possibly count as a particularly remarkable solution, it does know what would count as a really impressive increase in profitability. Therefore it can aid the whole exercise by setting the or team a high aim in payoff terms. This puts the scientists on their mettle, demonstrates to them that the management means business and will not be put off by the occasional thought block, and above all prepares the management itself for the answer to lie outside its own phase space. 65. 6. The sixth tightness, stereotype success. The last of these half-dozen points of importance concerns the implementation of an operational research result. First of all, it will be as well to pick up the moral that the submarine story directly points out. Although, as has just been argued, years of research and development are not necessarily required to obtain a lucrative solution to a managerial problem, considerable development effort may need to follow in the wake of an operational research solution. By selecting a new solution outside the phase space of previously acceptable solutions, management is almost certain to find that particular features of the existing situation are no longer appropriate, or are inadequate, or are simply unworkable. Just as the hydrostatic trigger for the depth charge failed to work reliably at a depth of 25 feet until it was redesigned, so well-tried organizational and control techniques in an industrial situation may have to undergo change. However, the economics of this development program are likely to be highly satisfactory. For by definition there will be a definite end in sight, with a known reward with which to crown success. There are likely to be fewer blind alleys to investigate than is normally the case. Thirdly, the psychological tone of the development team ought to be very high. But management should not fail to pursue these necessary matters, which they sometimes do on the grounds that the answer can be made to work without this additional expense. It must be remembered that an OR solution which postulates certain changes in the existing situation, in order to facilitate a particular new policy, will have built those changes into the validation of its solution. Thus the extent of the dependence of success on the fulfilling of these conditions may be harder to estimate than the management imagines. This introduces the second facet of this topic of implementation, and one which does not emerge from the submarine story because of its unusual simplicity. To implement a portion of an OR solution may prove disastrous. When the depth setting of 35 feet was installed to replace existing practice of detonation at 100 feet, results substantially improved and at once. Certainly the full payoff did not come until the development people had solved the problem of detonation at the recommended 25 feet. But no harm was done in the meantime. In more complex problems, to adopt a 35 feet interim solution may well position a complicated business operation in a context that simply is not viable. If a submarine were a sort of vessel that could sink with extreme rapidity through the 35 feet zone, then this interim solution could have resulted. 66. in fewer, not more, sinkings. This state of affairs often exists in industry, and, one suspects, even more often in government problems. Half measures may make the confusion even worse. At the best, if a given or solution proposes a benefit of £50,000, to impose half that solution is most unlikely to result in a benefit of £25,000. The three remarks made so far under this sixth heading may appear disenchanting, but the final point is much more hopeful. A typical breakthrough in the more familiar kinds of scientific research frequently raises more problems than it solves. A train of new difficulties will often arise. From what was said above, it might be imagined that the same is true of operational research, for have we not said that there will be consequential development matters to attend to when the typical or solution has been applied? But the situation is in reality very different. It cannot be too strongly emphasized that an operational research project must take account of all the factors bearing on a situation. If it does not do this, then the work may solve some relevant problem, but not the actual management problem. For management, a solution only counts as a solution when it can be implemented without more ado. It is the function of an orthodox specialist advisor to say, from the point of view of my specialism, the best thing for you to do is so and so, but of course you will have difficulties with the unions, or you will have to face this or that consequential problem. If the advisor is a chemist advising about chemistry, or an economist advising about economics, this is perfectly legitimate advice to give. But the operational research scientist specializes only in managerial tactics and strategy itself, therefore there can be no loose ends labeled your problem, chum. This point was made earlier, but it has to be mentioned again because of its bearing on the implementation of results. The stereotype of success in a piece of orthodox research stops short of managerial action. If the scientist can win a PhD with his work, or even have it published in a learned journal, then the stereotype says he has succeeded. Where or is concerned, managers and scientists alike may become wedged bears through this idea, and forget the whole point of the activity. An operational research solution should propose a complete answer, and insofar as this includes a demand that certain consequential matters be settled, it does at least specify what these matters are and how to settle them. It is perfectly all right for an accountant to put forward a new costing scheme, and to tell the management that the flow of data at some point is so great that a computer will be needed to handle it. But the management knows full well that completely fresh studies of computer feasibility and of detailed application will have to be made if the 67 machine is to be installed successfully. In the case of operational research, on the contrary, the recommendation that a computer be bought will be rooted in the nature of the controls devised by the study. Thus, the OR solution that includes the installation of a computer is its own feasibility study. Incidentally, the reason why an operational research team must have complete freedom to study whatever facets of a situation it regards as relevant again emerges from this sixth point, as it did explicitly or implicitly from the other five. If the managerial answer to an OR proposal can possibly be of the form, "This is a good suggestion, but this is not the time to use it," or "There is no money," or "Such and such a condition should be fulfilled first," then something is missing from the operational research. At this the manager might well say that OR is trying to arrogate to itself a managerial function and prerogative. If there is no factor known to the manager that was unknown to the scientists, then what decision is there left for the manager to take? The answer to this is really quite simple. Operational research exists to try and eliminate, or at least reduce, guesswork. Sometimes it succeeds, and when it does so entirely, there is no managerial decision left to take. No one should be more pleased about this than the manager. Suppose that he began by recognizing courses A and B, and by having no idea as to which would prove the better. Suppose the following to be the OR advice. Course A is likely to pay a high return for the next 3 months, but then to lose money steadily for 2 years, at which time the company has a 90% chance of going bankrupt. Course B on the other hand will be slow in starting but stands a good chance of doubling the profits in 3 years. How would the manager like the or report to continue? By saying, however, this is no more than a scientific evaluation of the facts, it is now for you as manager to take a decision? That would be merely offensive. On the other hand, it is far more usual for an or result to indicate that there is a number of possibilities which are equally valuable from the scientific point of view. Typically, for example, courses A and B may have an equal expectation of an equal financial return, but course A may reach this expectation more quickly than B, whereas B will involve less vigorous effort on the part of all concerned. Value judgments of this kind are the decisions that management really has to take. Once it has fully specified its set of values, a unique scientific solution should become possible. Sometimes the values can be quantified in advance and built into the study. In this case, the manager has exercised his prerogatives before. 68. The work begins, and can stand by to await a unique solution in the knowledge that he has already done his job. At other times, it takes an or investigation to isolate clearly the value judgments that have to be made, and in this case the manager is left with a decision at the end. So let there be no confusion about the nature of success, either for the manager or the scientist, or for the institution they both serve. The stereotypes of success for these two men may conflict, and each serves to nullify the other. The stereotype of success for the institution may itself be confused with theirs. There remains a good deal to be said about this point much later on. For the moment, it is enough to insist that as the novel solution is not an end in itself, so the novel payoff is not achievable by itself, the novel concept of success is a necessary mediator. Above all, that concept involves a thoroughgoing technique of implementation. And so, having eased off the tightness of 6 stereotypes, the wedged bear becomes free. He may put down this sustaining book, and set off in search of more honey. 69. 5. The new look. Now it is for data collectors to know all the details, and for mathematicians to establish the reasons. For they can demonstrate causes, often without knowing all the details, just as people can entertain a generalization without knowing each instance of it singly which they have not examined. Mathematical science is about pattern, not the specific things that form its subject. Aristotle in Posterior Analytics. 1 Whichsoever and whatsoever. Some authors suffer cruelly in the public esteem, for instance Aristotle, and those who write government reports. People go around saying that their writings are stuffy and irrelevant. Such people do not actually read these authors. Non-readers of Aristotle who are most familiar with his works may find the passage selected to head this chapter irrelevant to the management topics of this book, but it repays a little thought. In the first place, it is true that managements these days have acquired a respect for facts. Accountancy deserves most of the credit for this. It has taught people that they cannot make sound judgments, although they may make inspired guesses, without a lot of detailed information. Admittedly, this 70 has led to some confusion, for a fact is that which is the case, whereas a good deal of information supplied to management is not the case, or is the case only in very special circumstances that have to be understood. Even the word fact is monstrously abused. Witness this sentence from a letter sent to a customer by a well-known British company: "We should not like you to believe the fact that we have disregarded your wishes, rather not." However, the difficulties surrounding the notion of fact have been sufficiently well ventilated in a previous chapter. Presuming that there is plenty of information, and that it is factual, to know the details is still not enough. Facts propose necessary, but not sufficient, reasons for decision. The movement towards scientific management begins properly with a demand for facts, but it customarily stops short at this point. One has to know what the facts mean and why they fit together as they do. This entails uncovering the mechanism which underlies them. There is nothing in the routine of the accountant, the industrial engineer, the work-study specialist or the O&M man which could possibly do this. Of course these people often do comprehend reasons in practice, as do managers themselves, that is because they are intelligent. But the words of the last sentence were chosen with care. There is nothing in the routine of. As Aristotle said, the routine for uncovering reasons is a job for science. In fact, Aristotle was very pithy on this point. In rendering the Greek into decent English, I have lost the economy of his opening thrust. His actual words run more like this: now it is for data collectors to know the whichsoever, and for mathematicians the whatsoever. Our modern collectors of data do know the whichsoever. It is stacked in the cellars on punched cards, it pours out of computers on magnetic tape, it is tabulated most beautifully onto clean white paper at a rate of 600 lines a minute, it appears on managers' desks in great wads that they are too busy to read, it is published by government departments in mammoth yearbooks. For this is the age of automatic data processing. Yet all this tells us nothing about the reasons why things are as they are. It takes some operational research to discover that. But, answers the manager, the or scientist works on a limited assignment. He cannot possibly assimilate all the knowledge the organization has accumulated about the whichsoever. Perhaps it is all locked away in people's heads, the data are just not there. Perhaps it is all locked away in the cellars on cards, the scientist will never get through it all. Aristotle had the answer to this one too. Consult the quotation. The scientist can assert that the three angles of a triangle add up to 180 degrees because he knows. 71. The whatsoever. He has uncovered the fact from examining a few triangles, he does not need to examine them all. This proposition, however, is deductive. Most propositions about real-life situations depend on inductive inference. But again the scientist can say, kettles of boiling water have got like this through the application of heat. He establishes this whatsoever by a judicious sampling of experience, there is no need to test every kettle. What is more, the modern scientist can go one better than Aristotle on this matter. He understands the mathematical statistical whatsoever of the sampling process itself, and can achieve a higher degree of reliability in his establishment of reasons, from less data, than the Greeks knew how. But this sort of work is a scientific job. It is worth remembering above all that facts are no use without a specification of why they are needed. It is obvious that they are not worth accumulating unless there is a purpose behind their collection. That is a tautology, but its triteness does not obscure the truth that a high proportion of facts actually collected has indeed no purpose. Secondly, and this is a far more sophisticated point, the purpose behind data collection alters the facts that are collected. This particularly affects the standard of accuracy. The distance from A to B is 10 miles is a fact for a car driver who does not care whether it is a mile or so more or less. It may not be a fact for the man calculating how much white paint he needs to inscribe a line down the middle of the road. Other aspects of decision-making are also affected, particularly where problems of classification are concerned. Why do you ask whether this expenditure is chargeable to capital or revenue account, is a relevant question, so is what is the profit. For reasons of this kind, the or scientist seeking the whatsoever of a management's whichsoever must be responsible for the collection of his own data. Of course, he may well use institutional information once he has fully investigated its nature. Again, he may not. But it is especially noteworthy that the absence of information in a business is never a good reason for not doing operational research. Many managers seem to think that it is, that the scientist wants to be spoon-fed with predigested victuals. He does not. Nor need the manager fear that the scientist's hunger for facts which are not yet available will necessarily involve huge delays and vast expenditure. Good or scientists are proficient in specifying the purposes for which they need facts, therefore their precise nature and also their minimum quantity. For they can demonstrate causes, often without knowing all the details. They should be told to get on with it. This admonition may result in the scientist's getting himself rather 72. Dirty. He has to involve himself in the operations that he is studying, otherwise he will never begin to understand what it is that he is really trying to measure. The point was obvious to all in wartime or. Scientists with cameras hung out of aeroplanes, they sat up to their ears in mud. Today, perhaps, we take our fact-finding too easily, relying too heavily on others to tell us the whichsoever. The excitement and the difficulties and the dangers of war are missing. However, a scientist can get as bespattered and torn finding out what really happens on a night shift in a steel works, as he once did by falling off a motorcycle into a paddy field when trying to develop a way of measuring difficult terrain. Similarly, the risks run in interrogating the works director about his reasons for backing the purchase of an electronic computer that neither sales nor accounts will be able to use, feel comparable to those run in seeking information in an Indian bazaar about the massing of hostile elements in outlying villages. The man who has done both experiences much the same emotion on seeing a hand glide unobtrusively into the folds of its owner's clothing, whether to produce a knife or a cigarette. To be entirely serious, the facts that are collected within a business clearly do not tell everything about the business. It is very possible that they suppress precisely what it is most necessary to know in handling a particular problem. Especially, the official quantitative information never contains the facts about the value judgments and other so-called imponderables that are involved. The scientist has to find ways of measuring these factors if they turn out to be relevant. For example, a system of priorities within a production control scheme based on a first-come first-served rule is observed not to work. There are two reasons. The production people are grouping orders together, splitting them up, holding them back, accelerating them and regrouping them differently in order to get the most out of the plant. Everyone knows they do this and realizes that the habit saves money. But nobody, not even the foreman and charge hands concerned, knows how they do it. So the scientist has to analyze what they do, and find out. Lie may then be able to express the whatsoever formally, and to embody the technique as a set of rules within the planning operation. If he does this effectively, it will save yet more money. The second reason is that the sales office awards special privileges to favored customers, probably with good reason, and by import unity causes production to give these customers priority. This tendency can be measured by ranking the importance of customers according to the judgments of the policy makers, and then testing the ranking for consistency with its operation in practice. Much light may thereby be shed on the real importance of each customer. Moreover, it may again be possible to incorporate special rules in the planning scheme, this time awarding weights that reflect importance, thereby saving much trouble and temper all round. In fact, while the manager is preoccupied with the content of his strategy, the scientist is studying its form. He is seeking the pattern behind the behavior, trying to formalize it, testing its coherence and relevance. If he succeeds, he makes explicit what the strategy really is. Sometimes this is a blow to the manager. For example, if one asked the manager of an airline what price he put on each of his passengers' heads, he might be shocked. Yet, as Professor C. West Churchman has neatly shown, that managers' policy towards safety and the cost of buying it does indeed determine what a passenger's life is worth in the opinion of the management, the actual figure can be deduced. For the existing risk of killing a passenger could be reduced by spending more money, which the management does not in fact spend, or the risk could be increased by saving money, which the management does not in fact save. So Aristotle had this final point, too, in his last quoted sentence. Perhaps the most important aspect of this is that it tells us why our experience is versatile in its future application. Managers are heard to complain that an consultant has no knowledge whatever of his particular industry, let alone of his particular company. But the scientist is concerned with the pattern of the strategy, not with its adventitious contents, and he has seen this before. Whatsoever an investment in stock should and can be controlled, for example, does not depend on whichsoever items are held in stock. These remarks apply to the whatsoever of operational research itself. The lengthy Chapter 4 was concerned entirely with a discussion of the briefly told story in the previous chapter about sinking submarines. The men who undertook that job were concerned with finding a strategy for improving the rate of sinkings, not with investigating the nature of ore as we have been. With hindsight, more is perhaps clear now to the perceptive observer about their own strategy than was apparent to the scientists involved at the time. Any single or job concerns the managerial whatsoever, but deals in the whichsoever of or itself. At the least, however, those men were aware of a scientific challenge, and were not obsessed with the techniques of their craft, for there were none. Today, with more than 20 years' experience of how to undertake managerial studies by scientific method behind them, typical or 74. Approaches may be somewhat stereotyped. The freshness, the special virtues of a new look at any particular problem, are sometimes lost. The senior management scientist may become as stale in his own realm as the manager does in his, and the managers served by this newly emergent advisor may foster the stereotype of or because it is easier to live with than the truth. In the next section, a second case history of or will be unfolded. 20 years have passed. Or is now active in industry. It has acquired a corpus of knowledge and technique gained in the management service. The or man sets to work on a problem to which the manager has no answer, and of which the scientist himself is totally ignorant. A new look must be taken. This time, however, the scientist begins by nearly falling victim to his own stereotype. His thinking is initially trapped in the methods of tenacity, authority, and a priority that have grown into his own discipline and experience. But the method of science eventually wins through and the job reaches a successful conclusion. Thinking it over now as commentators on or, we may observe the characteristic pattern that Aristotle would have the scientists seek. And we shall have occasion to remark on all 6 modes of tightness that can wedge the most well-intentioned bear to a modern industrial or problem. In the generally rural area lay a large industrial town. This town was dominated by a large and important industrial concern. A high proportion of the town's inhabitants worked for this company, and its own sense of involvement with the local community was highly developed. The company was a heavy user of electricity. As is well known, there arises in the winter a particularly heavy demand for this source of energy, especially at peak periods of the day. In consequence, an industrial concern has to agree with the electricity undertaking on a maximum demand. That is to say, the company undertakes not to exceed this agreed call for electric power during periods of peak demand, and in return a pricing system is agreed under which the electricity authority can be assured of a proper return on the proportion of its total load committed to this company. More significantly, the authority is assured that no load greater than that agreed as a maximum demand will be exerted on its supply system. But the company, which is fully connected to the grid, can fail to observe the agreed limit. What happens then? Such a situation is fraught with great difficulty for the authority, and 75. So a penal charge is imposed for all usage over the agreed figure. This forfeit will encourage the company to shed load as it reaches the level of maximum demand. But it can do this only if it is continuously aware of its demand from moment to moment, if it can forecast its fluctuating demand for the moments next ahead, and if a sudden decision to shed load would not entail disastrous consequences to production. It is by no means easy to satisfy this complicated set of conditions in a large works. At the end of one severe winter, the company discovered that it had exceeded its maximum demand level more than once. On each occasion, the period involved was roughly half an hour, after which time the situation had been appreciated, and load shedding was efficiently organized to bring the consumption down below the MD figure. But under the agreement the damage had already been done. Extra costs of the order of £20,000 were incurred for each mistake. This situation was raised with operational research, although the difficulty appears at first sight to be open to solution by a combination of electrical engineering and accountancy. The managing director had, however, appreciated that a control strategy was required, and that this must involve many aspects of the business, for instance, its attitude to product quality and its production policies. He had also noted that routine methods had not in fact solved the problem, since the company had incurred undue expense, and he considered this was due to the probabilistic aspects of the case. The man was first confronted with this question at a management meeting, and had to make a quick appreciation. It is relevant to understand exactly what was going on in the mind of the scientist at the time. It was obvious, the investigator thought, that if all possible demands were assumed to occur together, and the total load aggregated, the maximum demand would be enormously and uneconomically high. The company had not done this, knowing from experience that only a proportion of the possible load would be likely to be in demand simultaneously. Nevertheless, the MD figure had evidently been fixed at too low a level. Clearly, then, this was a problem of probabilities. Certainty that any agreed maximum demand would not be exceeded by the actual demand at any given moment in the peak period, could not, of necessity, be reached. The following argument then emerged. As the maximum demand ceiling is lowered from a level equivalent to the sum of all possible demands, the probability that it may be exceeded must steadily increase, though not as a linear function, because the expectations that each piece of electrically driven plant needs to 76 come into service at a given moment are not equal, nor are they independent of each other. Doubtless, however, these probabilities could be computed, a curve could be established showing how the risk of needing to exceed the maximum demand diminishes as the agreed level increases. But, as the agreed level increases, the costs of the scheme will go up again, non-linearly. An optimal balance is required, a point at which there is so little gain in the probability of not running into trouble for the added cost of ensuring this improvement that it is not worth paying the extra money. Judging by last year's experience, for the maximum demand then operating, the curve must still be rising steeply, that is, it must surely pay to increase the maximum demand substantially. But to what level? The scientist hoped that when the curves of probability and cost had been computed and plotted jointly against the level of MD, they would turn out to have points of inflection. He hoped, that is, that the curves would suddenly and mutually flatten, thereby suggesting that the maximum demand should be fixed at the point where the curves changed over from a steep to a gentle descent. He went so far as to draw a picture of this possibility, as in Figure 1, which he showed to the managing director. Figure 1. Preliminary econometric formulation of the maximum demand problem. Now the real work had to begin. The scientist, as manager of an group, set up a small team to begin the study. As a first step, the team was briefed to examine both the facilities for the works control 77 of maximum demand and the legal contract with the electricity authority, and to produce a succinct statement on these matters as an internal document. After this, the manager met with the two senior scientists who would be concerned, one as directing the project, and the other as leading it on site. The three men formed an interdisciplinary team, and none of them knew more of the really technical aspects of the problem that lay before them than had by this time been compiled in their colleagues' notes. Discussion soon revealed some very interesting questions, to which no one present knew the answers. Following this meeting, then, the manager went back for a talk with the senior management about a number of matters. As far as the electricity demand problem was concerned, he was now intent on obtaining an answer to the following questions. When it looked as though the danger limit were being approached, the grid load would be shed. The first move in this direction was to switch on the company's private electrical generators. In order to use these generators, steam was required, and this could be obtained by burning oil or by using one of two separate sources of gas supply, both of them originating in the works. The question therefore was, under what tactical control did these alternative fuels become used, what happened to the processes they were otherwise concerned in energizing, and who was responsible for the overall control of the many forms of energy that were apparently interacting in supplying the plant? Answers to these questions were soon obtained. The accountants knew, as apparently absolute facts, the order of cheapness of the whole range of fuels employed in the works, that is, they knew the cost of each as procuring a standard number of BTUs. It had therefore been ruled that any actions taken which would involve substituting one fuel for another should, as a matter of course, invoke the use of the absolutely cheapest available alternative. As to the last part of the question, it was judged that, since this policy was so simple to comprehend, no one person need be charged with seeing that it was implemented. Everyone concerned knew the rules and obeyed them. The man was by this time becoming excited. How could anyone say what the relative costs of the fuels were for a given situation on the basis of some average costings? The costs actually incurred by a variety of alternative fuel policies at any one moment must surely depend on the opportunities available at that one moment to contrive some especially ingenious pattern of consumption to match some especially unusual 78 set of demands. At this point the appropriate officials, controllers of the electrical generating station, the gas controller, the man in charge of the steam boilers were called into the meeting. These people contended vigorously that their preoccupations had nothing whatever to do with the problem of trying to fix the maximum demand from the grid. The man was impatient of these arguments, because he had been unable to complete his concept of the double probability curves without knowing what the peripheral conditions actually were. And it was in trying to convince these departmental managers of the motes in their eyes that he suddenly became aware of the beam in his own. The phase space of the problem as he had conceived it was entirely at fault. These peripheral arrangements were not only relevant, they were an intrinsic part of the management's difficulty. When the senior meeting resumed, the tack was entirely changed. Had the management in fact ever considered setting up a general control for energy consumption of every kind? The answer was that they had often thought about this, but they had discarded the idea, on the grounds that they knew of no similar works anywhere in the world in which a genuinely integrated energy control system operated. This bore out, they thought, their own intuition that the total problem was much too complex to be solved from moment to moment on such a broad front. As was remarked earlier, a manager is not culpable for fixing his phase spaces according to his own knowledge and experience. This is a necessary maneuver, and is often correct. But no harm would be done in trying to devise such a control, since new scientific methods would be used in formulating the problem, and there would be a possibility of destroying many of the traditional difficulties within a completely new framework. This thought was based on the consideration that most of the problems arose from a failure to communicate between the different sorts of fuel controllers. Such information flow problems tend to disappear, however, if the centers between which the flow is supposed, and fails, to flow are in some way coalesced. So permission to alter the entire terms of reference of the investigation was sought. This was not a problem of determining the maximum demand for grid electricity, but a problem of discovering a company's strategy for energy control. The new proposal was strongly opposed on the grounds that such ideas, even if successfully developed, simply could not be implemented in view of the company's organizational structure. The control principle adumbrated cut right across the established lines of managerial responsibility. Thought blocks began to rise like monuments all round the table, but the managing director was willing to give the idea a trial. The 79. Manager returned to base with what was, in company terms, a new commission but which was, in his own mind, simply a new phase space. The construction of a scientific account of the whole energy consumption of this company was a long and difficult task. It should be appreciated that to build into the scientific program every source of fuel, together with the appropriate constraints and controls on its use, was an undertaking of a different order of magnitude from the original task. For although the electricity demand problem itself could only be solved by taking account of the alternatives which could be fed into the system, it had at first been understood that this would happen according to a set of simple and invariable rules. To allow for it in a situation where every fuel had a right to equal consideration as a poser of its own problems of profitability, made the problem perhaps 10 times as great. Gradually the scientific picture emerged. All the interactions of the fuels and the production situations that could occur were stated in terms of mathematical and logical equations. Few of the fuel relationships turned out to be symmetrical. That is, for example, the price paid for electricity imported from the national grid was different from the price received for works electricity exported to the grid. There were many practical constraints on the apparent possibilities. Some of these constraints were not absolute, but themselves matters of probability. The most important of these, for instance, concerned a contract to supply the local township with gas. The company treated this commitment very seriously, with the result that gas holding capacity, which the OR scientists had originally regarded as a buffer in the system, turned out to have a restricted availability in that role. How far it was restricted would depend on the day of the week, because this determined both the probable level of the townspeople's demand, and separately the probable level of gas in the holder. Figure 2 gives a general view of the total energy system which was now under study. Every entry in this diagram represents an activity that has some effect on every other entry. Moreover, no activity can be prescribed in exact terms, the whole system is a dynamic interaction of probabilities. Somehow a formal scientific account of this whole system had to be created, and this was done by a mixture of theoretical and practical work. The logic of the theory of sets was used to express the basic relationships, mathematical statistics expressed the probabilities, actual data were pumped into the formalizations to quantify the picture. In some cases, the data recorded were quite inadequate and more had to be collected. In some cases again, the data were insufficiently precise and 80. Figure 2. Diagram of the major interactions affecting the maximum demand problem. 81. Could not be made more so. Mathematical tricks were then used to estimate what more frequent readings would have recorded had the instrumentation been available. Many details of the system turned out to be unknown, and became the subject of special investigations. For example, the optimal number of oil burners inside the boiler had to be calculated. The generation rate of the private electrical substation had to be assessed in terms of the maximum output of 5 different turbo alternator sets under different loads. This was done for available steam pressures representing residual energy available after intermittent and very heavy demands for steam had been met from the production plant. Lest the acquisition of these data makes the work sound like a straightforward engineering study, let it be noted that the object was not to find some theoretical best state for the system, but a control strategy that would actually work. Throughout, therefore, the interdisciplinary team was concerned not so much with the measurements quoted here, as with their representation in the system. The fact that counts is not that a meter registers somewhere, but that someone knows it has registered after what delay, with what accuracy, with what reliability, and so on, and above all with what capacity to react to the information thereby conveyed. In short, the scientific account of affairs involved the formalization of interactions between men, machines, materials, and money, all spread over the complex system depicted in Figure 2. It took about 9 months to complete the scientific appraisal, to evolve an optimal overall strategy for operating the total system, to test it adequately, and to present it in a form that would be usable in the works. For it is of course useless to present works operatives with set theoretic formulae. The rules for conducting the strategy must be translated into the practical language of simple charts and simple operations, such as pulling levers. In the end, however, the job was done. The company was then informed of these developments, and told that the problems arising in creating a generalized control for energy had been overcome. Not surprisingly, the management immediately asked for an answer to the original problem: at what level should the maximum demand be fixed in future? The answer, assuming that the new controls were instituted, was that the figure could be reduced to less than half its previous level. Inevitably, this conclusion caused consternation, and the arguments that followed showed clearly how important it is that management should really understand the nature of operational research. If the basic features of OR work which have been explained in these chapters had 82. Been comprehended, all might have been well. As it was, some of the people concerned had this familiar view of OR, that it is an impracticable attempt to beat a manager at his own game by theoretical mathematics. Apart from the total misconception of the subject thus indicated, this is a way of expressing things which, by its pejorative tone, is clearly intended to mean that such an approach cannot possibly succeed. It is high time to note, then, that a management group intending to obtain the advice of operational research should first provide it with a platform from which to explain its objects and methods to everybody who will be concerned. Everybody, moreover, means what it says. In particular, representatives of trade unions should be admitted to early confidence. A scientist has every prospect of obtaining first-rate collaboration from union men, provided he has an opportunity to explain his motives, for the scientist is interested in reality without a gloss, and the man on the shop floor is interested in this too. There must of course be every opportunity for those attending explanatory meetings, at any level, to argue. Senior management should not seek to protect or from open assault. Difficulties will be cleared up which otherwise would result in covert obstruction. Besides, these experiences are good for the man, who is thereby reminded that he intervenes in real life, a reality in which people stand to be hurt, or to be degraded, or to be exposed. In the case of the MD job, permission to hold such meetings had been refused, but some time after the experiences here related, the company made generous amends. It sponsored a whole-day conference on or for all managers, and a half-day conference for union representatives. Thereafter, it is worth saying, the work people cheerfully permitted men to time their operations electronically to a fifth of a second accuracy in those same locations. This was because the men had by this time earned the right to be trusted to negotiate the arrangements and suitable safeguards by themselves, which they did. Despite the difficulties caused by the failure in communications, however, the new control system was eventually installed. The operatives had to be taught the use of the practical tools which interpreted the scientific straight-gun operation, in which the team leader, a professional psychologist, as well as an scientist, proved invaluable. Here was the new whichsoever of the job. The strategy itself, which had been prepared under the supervision of the project director, was expressed in a symbolism that many who have studied mathematics at degree level would find hard to understand. It was therefore hidden away, labeled the whatsoever. And Aristotle was right to 83. Say that mathematical science is about pattern, rather than the specific things that form its subject matter, for 3 years later the strategy was taken out and used, to even more imposing effect, on another management problem of energy control. The situation was different, the very firm was different, but the whatsoever of the whichsoever was the same. 3. Final appearance of the wedged bear. There is no need to write a lengthy commentary on this case history, but the plan of these first 5 chapters calls for an explicit understanding of the managerial philosophy that is fundamental to the use of operational research. In particular, what was true of the nature, application, and meaning of when it devised a method for sinking submarines during the war, remains true 20 years later in the creation of a strategy for controlling the use of energy in an industrial company. The last chapter tried to explain it, by considering 6 ways in which a manager can misunderstand. All these stereotypes were militating against success in this MD study, too, but we should be able to unwedge the bear with alacrity this time. Firstly, the damaging notion of the stereotyped scientist was much in evidence. Here was a job apparently exposed to science already, an accepted set of experts had been handling it for years. What did these people know about it? Here are some of the disciplines represented, at various times, on the job: mathematics and psychology, philosophy, computer expertise, lubrication engineering, logic, economics. Before the follow-up work had been completed, servomechanics and biology had been added to the list. This was indeed an interdisciplinary team, although it did make use of an electrical engineer who happened to be on the staff. These were the people who broke with tradition and found a new way into the situation. Secondly, there was the stereotyped problem. And here the manager was himself a bear firmly wedged alongside the man he was trying to help. The problem, we have said, may not be as it appears, determine the whole of the situation, and forget the departmental barriers. But the manager went doggedly on, and got stuck. Fortunately, he fell out of the tree because of a fluke, certainly, but also because in his ignorance of the proper way of handling a question of electricity supply, his tightness was not too severe. What really trapped him was in fact his too thorough knowledge of the company organization. Perhaps his less knowledgeable colleagues pushed At any rate, the real need, 84, was to consider the whole of the energy supply arrangements, and not just those of an electrical nature. Again, with hindsight, this trick may be regarded as frightfully obvious. One can only say that it had not often been envisaged before and never attempted in a similar firm. Thirdly, comes the role of chance in the situation, a formal treatment of the subject, battling with the stereotype of science itself. Almost the whole of the quantification of these strategies, policies, and rules had to be stated in terms of probabilities rather than clear-cut facts. This is a matter not just of knowing some statistics, but also of understanding science. Remember that people customarily use what the statistician would call an estimate as if it were a cast-iron fact. There were those absolute cost figures, alleged to measure the cheapness of fuels regardless of the circumstances. There were maxima for wholes, computed as the sums of the maxima of parts, which simply could not occur in any universe governed by any degree of chance. And so on. It is the scientist who can handle these probabilities and risks, not the accountant and the engineer who tell him he cannot. Next comes the question of phase spaces and thought blocks, which insist on a stereotyped solution. It is so important to realize that the treatment given to these matters in this book is not merely a gilding of the lily that everyone has in a vase on his mantelpiece. It is easy enough to say that people should be prepared to consider solutions that they have not considered before, or that a good manager is imaginative. But what do such exhortations really amount to in real life? In practice, they are devoid of content. The exposition that was developed at considerable length in Chapter 4 was intended to throw a genuinely helpful light on the difficulty. Managers and scientists alike need to understand fully the real mechanisms at work, and the limitations of the human mind as they apply to this matter. It is not a question of the scientist being cleverer than the manager, nor of the manager being obstinate and old-fashioned. The two men have quite different roles to play in their quite different jobs. The idea of culpability must be completely abandoned. In many ways it is possible to argue that the old solution was the right one, for without the change in conceptual framework the scientist could probably not have improved on it. It is not a manager's job to change his own conceptual framework, but to get on with the responsibilities he exercises within it. The onus on general management to consider such changes is, however, much heavier. Perhaps this kind of decision is their most important task. Just how difficult it is to avoid the question of blame is well illustrated in the present case. The OR team itself had, it can truthfully be said, 85. Introduced no note of slander. They handled this question with tact. But the managerial hierarchy itself was not so understanding. Wedged firmly among his stereotypes, the top man hurled the OR report like a bomb at his subordinates. The shrapnel ricocheted. Various people were told by various others that they must have been losing the firm money for years. If a crew of eggheads, including philosophers and biologists who did not know Ohm's law from an act of parliament, could do the job better than the array of responsible officials, the latter had better pack up. Two of them did. Their resignations possibly had nothing to do with this rumpus, but it can be imagined what effect that outcome had on the reputation of OR in the company and its associate firms. So much for the 4 points concerned with the tackling of an operational research study. The fifth point concerns payoff. Again, in this case history, the rewards were really quite large. Not only were there the decreased cost of the agreement with the electricity undertaking, the reduced cost of consumption itself and the elimination of the fines previously incurred, but there was an overall gain in the efficiency of energy usage throughout the works. If all these savings are brought into the computation, the annual saving was certainly a six-figure one. The stereotyped outcome of a small and respectable gain from operational research is in fact a comfortable notion for management. It carries with it the implication that everything was just about right. With the enlightened use of high-powered brains, suitably directed, a little more finesse can be achieved. But this is not the way to use OR. Where the work is used in that way, it deserves to be defined as the application of big minds to small problems. And who should bear the onus for that kind of prostitution? Truly the scientists concerned are to blame, for they ought not to acquiesce, but they may be defended on at least two counts. In the first place, many scientists are a great deal more diffident than managers imagine. The stereotype of scientific arrogance derives from a failure to understand science. A good scientist is never arrogant, although he may be conceited, may be a good historian, or a good manager. Thus many men are actually doing work that is well beneath their powers, simply because they do not realize it. Secondly, however keen the man may be, and should be, about getting results that are managerially effective, the scientist in him has to be concerned about something else too. He wants to do good science, and this is an end in itself. Hence the prostituted man, balked in the search for the 86 big company payoff, will become more and more engrossed in the search for professional satisfaction. He may well achieve this in doing elegant and original science on assignments that are managerially fatuous. No, the onus for this state of affairs rests largely with management itself. It can hardly be too much stressed that the sponsor of operational research is likely to get the payoff he expects. But this is a topic locked up in the mode of fitting or effort into the organization, which will be discussed at the end of the book. The sixth of the stereotypes that wedged our bear was the stereotype of success. Agreement on what counts as success is sometimes hard to reach, and agreement on exactly what has to be done to achieve it harder still. The general discussion of this point in the last chapter concluded that the whole solution has to be implemented. Parts of the total recommendation cannot be amputated because they are somewhat inconvenient. This, it was said, may entail consequential research and development. As with the depth charge gauge, so with the MD control. The prospect of automating the whole of the energy control system had been investigated during the study. In principle, the idea was attractive, it is in most work. The reason for this is simple. Once a strategy has been examined scientifically, properly formalized, rigorously optimized, it is definite and precise. The rules for working it are, and must be, quite clear, even if the circumstances covered by the rules are not. This means that the strategy can not only be automated, but readily automated because the basic work has been done. Nonetheless, as in this case, full-scale automation is often just not economical. Some partial automation was, however, included in the energy control plan. It had been realized that some links in the control sequence could not be reliably undertaken by human resources. The information that had to be passed would be too complicated to compute with sufficient speed, too long in transmission and too unreliably interpreted at the other end. In order to get the quick results that were so urgently needed, a plan was evolved to implement the strategy with human links. Inevitably this included simplifications to evade the troubles mentioned, thereby decreasing the effectiveness of the strategy and incurring a greater risk of error. The recommendations included the specification of certain automatic linkages to deal with these problems, and these called for the design of a small special-purpose computer. It was tempting for the management to forget about this part of the solution. The simplified plan was adopted and worked successfully throughout its first winter. Why bother with these extras? The fact 87. However, was that these were not extras, but an intrinsic part of the whole solution. To cut them out of the scheme would be uneconomical, or they would not have been in the scheme in the first place. This means that to save money on this development meant running a risk for which the long-run expectation of loss was greater than the cost of the proposed automation. Happily, the point was agreed. Designing the computer was a research and development task unsuited to an OR group, but the logical specification of the system derived from the original work. Thus a new, though smaller, OR project was mounted to complete the detailed logical design, and to collaborate with the electronic engineers elsewhere who carried out the circuit design and built the equipment. Thus this commentary is completed. The bear, at his final appearance, has been unwedged again. This time the 6 stereotypes have been observed in action, as they actually impinged on a particular OR job. There is much to learn from the story, for both managers and scientists. Here is a final lesson from this experience for them both. Although the stereotypes were gradually eliminated and the job was successfully commissioned, successfully undertaken, successfully completed, and successfully implemented, the management did not know how to take the credit. They felt rather silly. Now this is absurd. A management which handles all this successful work should be very pleased with itself. It should declare that while others may fumble and misuse or, it at least has discovered how to exploit the facility. Since it did not take this line and the credit it most certainly deserved, other managements within the group misread the situation. All who had been concerned were ill-served by this development. It should not be thought that the OR people were gratified to gain a reputation for having put them right. For one thing, this is not the OR task. For another, it makes other people very nervous. Operational research is in this respect like musical chairs. If you're left holding the credit when the music stops, you're out. For Humpty Dumpty rides again. What then is operational research? There are roughly as many definitions of the subject as there are OR scientists. For these are thoughtful people, and if any one of them lacks the temerity to formulate a definition, his place is taken by bolder colleagues who have a range of definitions to spare. The need for a definite set of words to express what the subject is must be real, because OR scientists are always being asked for one. On 88. The other hand, it should be recognized that definitions refer strictly to the meaning of terms, not to the activities which the terms name. A straight line is the shortest distance between 2 points says what the term straight line should be taken to mean in a particular context. We could rewrite plane geometry using a different definition of straight line altogether, something that we usually call a curve, for instance, tiresome, but perfectly correct. But if we adopt a new convention for a term that names an activity, the position is not so simple. In this article, the word physics means the art of cookery is a convention easily, and again correctly, maintained within the boundaries of the article. Yet if the reader were to imagine that this gastronomic article told him anything about what physicists do, he would be misled. Humpty Dumpty paid words extra and made them mean what he chose, but he could not thereby change the behavior of the things they named. So it is with OR. OR is research into operations is a definition of the term, and one which few people could possibly reject. But it says nothing about what OR men do, it defines a term, not an activity. Now of course activities themselves are not to be defined, as are the terms which name them. Activities are to be described. The first part of this book, which is now complete, has been devoted to description. 5 chapters have been used up in saying what OR men do, why and in what context. If it is convenient to have a definite set of words to cover the meaning of OR, we must look for a compressed description, rather than for what could properly be called a definition. The description had better start with the topic handled by OR. It is clear enough what this is, the complex problems faced by managers. Unless there were managers, and unless they had complex problems, operational research would not exist. Managers themselves, and most of their consultants, tackle these problems from knowledge and experience of the job. Specialist advisors, such as accountants, have a battery of highly developed techniques ready for use in this sphere. OR, however, as has been seen, investigates the situation without a preconceived idea of what it is like. Its approach is that of research. That means taking a new look at the state of affairs. The method of investigation is the scientific method, and OR man attacks the problem as a scientist, using the ways of operating that he would use in any other investigation. These are, for instance, logical analysis, the identification and measurement of facts, the erection and testing of hypotheses, experiment, verification and so on. Ultimately, the discovery of whatsoever. But more than this, OR science imports into the investigation an interdisciplinary knowledge of the sciences themselves, of their formal languages and 89. Techniques, of their most advanced insights into the way the world works. All this must be compressed for the description. Operational research is the attack of modern science on complex problems arising in the direction and management of what, exactly? Of enterprises, the answer would seem to be, for these are the things that managers manage and direct. And yet that term is rather vague, although everyone understands it. What really is an enterprise, as seen from the scientist's viewpoint? It is something that uses a collection of resources to meet a need. There is no point in being vague about the nature of the resources, either. To illiterate, men, machines, materials, and money are the four specific lots of resources required to make an enterprise. And if four such radically different kinds of input are involved, they must be interlocked in the most intimate fashion. In fact they interpenetrate to create a large, organic system. This is itself what makes the enterprise amenable to scientific examination. It is a system of which the internal mechanism can be discovered. Nor does or care very much to what purposes this four-dimensional system is directed. Originally, as was shown, the systems studied were military, the defense enterprise remains a field of war. Next came industry, the production and marketing system, and business, too, breeds enterprises that fit the pattern stated. Above all, government is an enterprise that calls for operational research. To compress all this is difficult enough. Not every enterprise can be identified by name. Schools, for example, and universities, hospitals, and doctors' waiting rooms, all these and many other managed systems fit the bill. We shall have to hope that they occur to readers of the description as being covered by one of the terms used in this continuation. In the direction and management of large systems of men, machines, materials, and money in industry, business, government and defense. So far the description briefly recounts the purposes, the topic, and the fields of application covered by operational research. But the attack of modern science says little about the methods it has developed since 1941. As will be seen in Part 2, or has in the meantime created its own armory of special techniques. Although a short description cannot list these, some attempt should perhaps be made to crystallize the distinctive approach of the scientist. Now, in trying to account for the behavior of a complicated system, the scientist has first to represent it in the formal terms he knows how to manipulate. This stage of the work was clearly identified in each of the jobs so far discussed in detail. Looking over the scientist's shoulder at his working papers, one might see a whole series of boxes joined by arrows, and a whole lot of mathematics. R. 90. These organization charts and formulae. Perhaps they are, but they are also more than this. They are attempts to get inside the system under study, to grapple with its intimate workings. The scientist is trying to recreate the system itself, not merely to describe some of its features, he intends to model it. The formal representation of the system that he builds is called a model. This model is something different from the diagrams that are drawn, different from the equations which inform their structure, different from the data which quantify the equations, and something more than the sum of all of these. The model is like looking at the real system through a filter, not a filter that polarizes light, not one that turns the picture red or blue, but one that turns it scientific. All the major features of the system, suitably transformed, will be found in the model of the system. And these must include the so-called imponderables. In particular, representation must be made within the model of such factors as chance and risk. We have already seen something of what this means. And so, the distinctive approach is to develop a scientific model of the system, incorporating measurements of factors such as chance and risk. A deeper understanding of the nature of models must be sought later, meanwhile it is as well to make the reason for creating them fairly specific. The essence of a model is to be predictive. The scientist, it was said before, cannot foretell the future. But, if he is armed with an effective model of the system, he should be able to say a good deal about the way the system may be expected to operate in a variety of circumstances. By testing the model's reactions to different sets of possible eventualities, the scientist begins to evaluate the system's vulnerability. What can the manager do about the vulnerability of the system he manages? He uses his normal method, which might be divided into three categories. He can take a decision which could be defined as a switch that sets at least some part of the enterprise on a new course. He can adopt a strategy which could be defined as a coherent decision-making plan. He can install a control which in turn could be defined as a routine that implements a strategy and generates decisions. When the manager sets out to apply one of these remedies to a complex problem, he will certainly attempt to foresee the outcome. In fact, various alternative courses of action will be open to him. Before choosing one, he will want to predict and compare these outcomes to know, in a word, which is the least vulnerable to a malignant future. This is what the OR model is for. So we may add to the sentence last formulated for the description of OR, an explanation of the model's purposes, with which to predict and compare the outcomes of alternative decisions, strategies, or controls. 91. Finally, it should be made abundantly clear that the whole purpose of OR, of doing the things just described, is to aid the manager. People sometimes seem to fear that the aims of scientists in the managerial sphere are vainglorious. Some go so far as to imagine that the scientist wishes to establish dominance. Possibly a few scientists feel like this. If so, they are on the same footing as the historian or the classicist who feels the same way. Such men are either psychotics or potential managers and entrepreneurs. The scientist qua scientist seeks only to do science. But the OR scientist has a special motivation towards science in management, usually because he cannot bear to look on quietly while decisions are taken, strategies adopted, and controls instituted in important enterprises on the basis of guesswork. Though even this is not the worst, for guesswork can be inspired and the brain with flair is still the best computing machine we have. What really riles the scientist is that a course of action should be adopted for feeble reasons that masquerade as being scientific. For example, some cheap and nasty opinion poll is held in which too few people representing a biased section of the community are asked loaded questions which they do not understand, their answers being misinterpreted by unskilled interviewers for inadequate processing to demonstrate a preordained answer. In fact, managers do often take advice which they honestly believe to have been established by proper study, but which will not stand up to 5 minutes of scientific scrutiny. They then assure their shareholders, customers, workpeople, or constituents that the matter has been properly investigated and these people have even less chance of knowing the truth. Or sets out to give proper advice, after proper study, that management can trust. It asks managers to investigate its claim to be organized and competent to do this. Then management can get peacefully on with the yobizzing or as an extra, scientific, lobe of its own brain. The purpose is to help management determine its policy and actions scientifically. And so the description is complete. For those who really want a form of words, it will do. It is certainly not unique, but it is not entirely arbitrary, either. It was prepared for the Operational Research Society of Great Britain, after consultation with many leading British OR scientists, and the Council of the Society has underwritten it. The full statement is as follows. 92. Operational research is the attack of modern science on complex problems arising in the direction and management of large systems of men, machines, materials, and money in industry, business, government and defense. Its distinctive approach is to develop a scientific model of the system, incorporating measurements of factors such as chance and risk, with which to predict and compare the outcomes of alternative decisions, strategies, or controls. The purpose is to help management determine its policy and actions scientifically. 93. Part 2. The activity of operational research. Connective summary. Having considered in part I the origin and nature of operational research, how it came about and what it really tries to do, we pass to the exposition of how it really does what it tries to do. Chapter 6 investigates the way in which managers solve problems, and contrasts this, in a rather formal analysis, with the way in which OR would tackle a similar situation. It shows how the predictive quality of the thinking is critical to a successful decision or policy, and expounds the concept of a model as the basis of insight and prediction. The theoretical nature of models is examined, with the aid of really detailed explanation and practical illustrations. These examples are augmented in Chapter 7, and the methodology of OR is more fully brought out. But scientific models have to be described in rigorous terms before they can be competently tested and used for predictive purposes. Chapter 8 explains how this is done. It specifies the role of mathematics as handling quantity, of mathematical statistics as handling probability, of symbolic logic as handling qualitative relationships. The basic vocabulary of these formal languages of science is explained in ordinary English, and case studies are quoted at length to illustrate their value. Armed now with both a methodology and a set of languages for doing operational research, we begin to probe the real nature of the problem situation which it is the OR task to penetrate. In every case the manager is responsible for the 94. Control of some kind of system, and Chapter 9 considers how these systems may be described and analyzed scientifically. Examples of almost every sort of management problem are discussed in this light. Specifically, solving the problem of prediction within these systems is the nub of the management task. Chapter 10 goes into the nature of forecasting, and of the techniques used by operational research to help. Again, many problem situations are quoted, and it clearly emerges that OR can aid the manager through the identification and description of the mechanism which informs the system the manager controls. The model of this mechanism is the tool of OR which enables alternative decisions, policies, and controls to be evaluated and compared in quantitative terms. And although the scientist cannot predict the future any more than the manager can, he is able to narrow the area of uncertainty and pinpoint the vital issues. 95. 6. About models. Reason is the thing without which our state would be the state of wild beasts, of children, and lunatics. It is the thing whereby we picture our intellectual acts before they become manifest to the senses, so that we see them exactly as though we had sensed them. Then we represent these pictures in our sensual acts so that they correspond exactly with what we have represented and imagined. Raises in spiritual physics. 1. Too many variables. A great deal has by now been said about the nature of operational research, its origins, its key features and its general relationship to the task of management. Hints have been thrown out about all sorts of applications, and 2 actual studies have been analyzed in some detail. We have even essayed a definition. It is now time to discuss more systematically what operational research can do, and precisely how it does it. Scientific method has already been talked about in a discursive kind of way, and most people can formulate some idea of how a scientist would go about investigating, for example, a plant or a mouse or a lump of lead. Physical objects such as these must be carefully examined, pieces are cut off them and scrutinized under microscopes, they are prodded, probed, and in general analyzed. One can see that, having obtained a great deal of information about a physical object, a scientist is in a position to begin to formulate his well-known hypotheses about structure and behavior, to invent theories about how these objects would respond to certain treatments and perhaps to formulate possible laws which might inexorably govern these phenomena. All this could obviously be the subject of experiment and verification. As a matter of fact, how? 96. Ever, modern philosophers of science are very critical of these traditional ways of describing scientific activity. The simple-minded notion of objective measurement collapses under close examination. It turns out that measurements are themselves based on theory, since there must be a purpose in mind when the measuring instruments are devised. It turns out that what is already regarded as natural law preconditions the design of experiments intended to verify hypotheses about natural law, because our idea of what constitutes proof is a late developer in our family of logical notions. And so on. In short, linguistic analysis shows that it is not possible to set the classical procedures of science in chronological order, so it is not particularly profitable to try and separate these procedures one from another at all. Moreover, the situation becomes still more confused when one stops thinking about physical objects and considers systems instead. The mouse and the plant may be physical objects, but they can be understood only as systems. Moreover, the boundaries of these systems are not the same as the boundaries of the physical objects themselves. If they could be entirely isolated from their environments, they would no longer be the things that they are. To the atomic physicist, even the lump of lead is a system, and of course almost all the functions of management are concerned with systems rather than entities. At this point the scientist joins the philosopher in his assault on the classical notion of science, to measure aspects of a system to observe it evenness to alter the system so measured and observed. This result is entailed by quantum theory. For these and other reasons which there is no need to explore fully, we shall need a new kind of description of the scientific method in order to discover what is the fundamental approach of operational research. It has to be conceded that our scientists themselves have not given much attention to this problem. Underlying most of their work is the classical philosophy of science, and they continue to get reasonable results in practice for the same reason that their scientific forebears were able to reach useful conclusions a century ago with the same philosophical equipment. The reason is that a cohesive collection of fundamental methods, which may be called a methodology, provides a framework for research which is neither right nor wrong, but only more or less useful. It is only at the limits of its usefulness, at the point where its concepts begin to disintegrate, that a methodology need be called in question. For example, the concept of the objective observer worked well enough for Newtonian physics, but is useless when it comes to relativity. Likewise, a methodology based on the measurement of simultaneous events, which has been found perfectly sound and valuable in mechanics, in optics, in astronomy, and in psychology, is totally useless to the modern physicist. For the term simultaneous denotes nothing whatever in an Einsteinian universe. Similarly, it may be argued, the analytic scientific methodology most familiar to educated people today begins to disintegrate when it is applied to the consideration of large and complicated systems such as armies, businesses, industries, and economies. There are several very definite reasons for this accusation, which managers have been quicker than scientists to recognize. Traditionally, the scientist conducted an experiment by holding all the variables of the experimental situation constant except two. He then manipulated one of these variables and observed the results on the other. This maneuver is quite impossible outside the laboratory, because there is no means of holding all conditions but two constant in a real-life situation. The immediate answer was provided by developments in mathematical statistics, which enabled conclusions to be drawn validly when a considerable number of variables were all changing together. The tool of multivariate analysis was invented. From that epoch onwards, the scientist could in principle afford to laugh at the manager who cried in despair, "There are too many variables." He knew that his statistical theory was competent to handle an indefinitely large number of them. But in practice his triumph was short-lived, because the theory demanded an ever-increasing amount of computation for every new variable that was added. Thus, although it was now possible to carry out valid scientific experimentation outside the laboratory, it was still not feasible to keep scientific control of a real-life situation having the dimensions of, say, an industrial enterprise. But then electronic computers arrived on the scene. Today it is once again possible in principle to laugh at the manager who complains, "There are too many variables." The theory of statistical computation has been matched by a practical computing facility. The only limit to the size of the problem that can be solved is set by the size of the computer's storage. Yet managers continue to say, "There are too many variables," and scientists are prone to claim that managers are not up to date in their knowledge of scientific theory and practice. I think these managers have been right all the time, although they might express themselves a little more precisely. The point really is much more fundamental than the arguments of the last paragraph supposed, for the prerequisite in handling a large number of variables is that they can be identified. Now the kinds of system under discussion exhibit 98. Literally billions of variables. There is no rigorous means of knowing which matter. Indeed, the importance of a particular variable in such a system is a question of degree, a question of judgment, a question of convention. Moreover, the importance it has by any of these criteria will change from moment to moment. This does not mean merely that the numerical value assumed by the variable is changing. That is in the nature of variables, and one of the things about the system that we know how to handle. No, it means more, the structural relevance of the variable inside the system is changing with time. One class of variable in managerial systems is so notoriously difficult to identify that it has drawn considerable attention from scientists. This is the value judgment. In brief, the criteria of success adopted by the management of an enterprise must be represented in the analytical account of the system given by the scientist. This is absolutely unavoidable. Yet what manager can give a completely unambiguous account of his criteria of success? He cannot say that he wishes to increase profit or reduce cost and leave it at that. For if he does, and that simple-minded notion of success is built into the mathematics of an analytical treatment of the problem, then the solution may well generate all sorts of unexpected side effects. One can imagine, for example, a situation in which the manager who has asked for maximum profit is told that the solution is to raise all his prices and to soak his customers. But what about my goodwill, he will say. And what about next year's business, when all my customers have gone bankrupt? But the analytical scientist could reply that he should have mentioned these things earlier on. The point, of course, is that however many desiderata the manager may mention, there may be others which he takes for granted and will not mention. Secondly, the longer the list becomes, the more likely it is that the manager's objectives will not be consistent with each other. Indeed, it is quite obvious that his objectives may actually be contradictory. He wants, for example, to maximize his profit, and also to be a good employer. But if he spends a penny on amenities, his profits are reduced by that penny. And by the same token, every penny he retains as profit he might have dispersed to his work people in some kind of benefit scheme. The analytical scientist is potentially at a loss. For it is in the nature of the optimizing techniques of mathematics, which the scientist most familiarly employs, that only one variable can be maximized or minimized at a time. Should the scientist then complain that the manager is muddle-headed? Not at all, it is this particular scientific methodology that is limited. For as every biological scientist knows, the primary characteristic of viable systems is that they try to optimize a 99 whole set of conflicting objective functions at once. They cannot do this so far the mathematical analysis is correct, but they try to do it. The result is that their method of control is essentially one of contriving a stable balance, and not of seeking some unique maximum. In practice, a great many operational research jobs escape this difficulty by limiting the scope of their inquiry. The study says, in effect, assuming that such and such conditions hold, and that the object is to maximize profit, then the correct strategy is given below. With this approach, operational research leaves it to the manager to interpret the results, and to strike his own balance with other factors which the study has not considered. But, as was forcibly argued in Part I of this book, this is not the kind of help which the management really seeks. It wants to know what is the best strategy having regard to all the circumstances. And so people concerned with scientists and managers alike, need to think out the implications of these facts, and to contemplate a methodology which will satisfy all the circumstances. So far but one solution has been put forward. This is, in brief, to say that in practice there is indeed only one scale on which value judgments, or managerial desiderata, or criteria of success, need be measured. This is the scale of preference. One can, the argument says, propose a finite number of distinguishable managerial policies and compute their complicated outcomes. One can then isolate a pair of such policies, show the respective outcomes to management, and ask which of the two outcomes is preferred. By repeating this exercise many times, one can eventually rank all the policies in order of preference. This position is vulnerable from many points of view. The scientific procedures which must be undertaken in order to arrive at a result are possibly defective. At the other end of the scale, it is fairly obvious that what is meant to be a scientific solution will in fact depend upon an arbitrarily subjective evaluation after all. Admittedly, this conclusion is obvious only because I have expressed the methodology in a way which makes it inevitable. Proponents of the methodology go to lengths which cannot be reproduced here to expound further scientific procedures intended to evade this difficulty. I do not think they succeed, and the point has been argued elsewhere. At any rate, the arguments of this section have perhaps sufficiently shown that a new methodology of operational research ought to be propounded, and it is one of the purposes of this book to do just that. 100. 2 Experiments with experience. Let us begin by highlighting a particular aspect of man's reasoning faculty. It is the ability to make a forecast, and indeed it is precisely this capability in man which seems most clearly to distinguish him from other animals. There is no doubt that we all prognosticate, we can entertain possible consequences of the alternative policies which we might adopt. Unfortunately, there is also no doubt that these prognostications are often inaccurate, but the point remains that man has a facility to envisage the future. It is a fascinating and most difficult question to ask what is the mechanism whereby this act is accomplished, and whether it differs in kind or only in degree from the mechanisms available to other animals. But this need not concern us here. It is necessary to ask not how we have this faculty, but how we use it. The quotation standing at the head of this chapter is an ancient statement of the process now under review. Rhazes was a Persian physician, who lived just over 1,000 years ago and worked in Baghdad. His quoted account of reason concentrates on its faculty of adumbration. He says that before we do something, we contemplate doing it. Thus we visualize what actually happens when we do this thing, and then we try to copy what we have visualized in what we actually do. When the thing is now done in reality, our senses tell us what is actually happening, and we are able to compare this with our prior visualization. This mechanism will of course enable us to improve on the prognostications which we make in the future. In other words, rational conduct depends not only upon knowing what is really happening and being able to interpret it, but on having present in our minds a representation of what is going to happen next. This representation is not an account of what is the case, but a continuous prognosis of what is about to be reported to us as being the case. It is a prognosis continuously corrected by feedback. Let us call this mental representation of the world that is not direct perception of the world a model of the world. The term is appropriate. Models of things may be more or less accurate, and thereby better or worse able to predict the behavior of what is modeled. Just because they are predictive, models are open to experimentation as a means of evaluating the likely performance of the thing modeled. In this mental representation too, experimentation goes briskly on, for, when we are about to do something, do we not rapidly explore various ways of doing it, selecting one of the ways for action? If we slow this process down, we can imagine ourselves contemplating a succession of representations. 101. Each depicting ourselves doing what is to be done in a different way, and systematically discarding the least convenient until only one is left. Now science is a carefully thought out, professional, version of this rigorously rational behavior. Compare the procedure just examined with the scientific methodology discussed in section 1. Can the model be equated with a scientific hypothesis? Clearly not. The model does not postulate the causal mechanisms that underlie events, it simply represents the pattern of the events themselves in advance by extrapolation. Is the model like a scientific theory then? Again, it is not, it has no explanatory content. A model is simply a reflection of whatever is the case, which is explicitly made available for experimentation. It is this which distinguishes it from perception. We can, in a very limited way, experiment with perception itself. For example, try to see a cow in the room. If you have the faculty of visual imagery strongly developed, you may momentarily succeed in seeing the cow. Typically, however, the mind which is accustomed to experiment with incoming perceptual patterns is diseased. Hearing voices is a classical symptom of schizophrenia, and the brain of the man who is aware of pungent smells which no one else can smell is deteriorating. The normal, Healthy person can however distinguish clearly between his sensations of reality, with which he must not tinker, and the spare copy of this perceptual pattern which he takes off to use for experiment. There is no difficulty about envisaging the appearance of a cow in a recollection of the room that is clearly labeled imaginary. Moreover, he can classify his experimentation. Most of it he uses for short-run decision-taking, some he may use for long-run decision-taking, and some he uses for other and stranger purposes to do with relieving tensions and resolving conflicts. The scientist can certainly be described, as he was before, within this classification. He uses the short-run procedure continually in his work to guide his most mundane steps. The longer-run procedures underlie all his attempts at verification and all his assessments of outcomes. The daydreaming procedures are in high demand by the scientist when he is in the process of inventing. The only difference between his handling of the model, and the use made of the model by the ordinary citizen, is that the scientist is professional about its use. He is self-conscious about the model he uses, he deliberates about it, he tries to make it richer and therefore a better replica of reality, he examines how it hangs together and may therefore try to express it in the rigorous language of science. 102. This way of talking about the business of science is now quite common among scientists themselves, in that the use of the term model is familiar. It seems doubtful, however, whether many scientists have thought very hard about the connotation of this term. Many of them are prepared to say that the word has itself been imported as a neologism which really does mean either theory or hypothesis. In fairness to them, it must be clearly stated here that this account of scientific methodology is my own, and must not be taken to be an agreed account of the matter. Mention of this fact makes this the right moment to dispose of a further point of usage. In scientific circles, the noun model is very frequently qualified by the adjective mathematical. According to the viewpoint offered here, a mathematical model is an algebraic statement of the representation already discussed. It is not simply an equation purporting to relate one set of variables existing in the world's situation with another. And this is the very much debased sense in which the term mathematical model seems often to be used. Returning now to the exposition of scientific methodology, the question that remains to be answered asks how scientists set about handling the model that everyone has in a professional way. And, since we are talking about the uses of science within enterprises, we might well ask the parallel question as to how the manager handles the model in a way appropriate to his profession. To answer the second question first, it seems that the manager contemplates his model, and compares it with models of other and similar situations that have been known to him. This is a way of saying formally that he brings his experience to bear. Supposing, for argument's sake, that the manager has been in precisely the same situation before that he finds himself in now. If his memory is good, he can retrieve the model of the previous occasion, he will find that it corresponds point for point with the model at present in his mind. The process of prognostication is now trivial, because he also knows the outcome of the historical situation. In practice, of course, no situation is ever exactly repeated, so the status of the prognostications he makes now cannot possibly be dignified as certain. How probable, in fact, is it that his prognostications will be right in the language of this methodology? This probability will reflect the extent to which the remembered models do correspond point for point with the existing model. This is the formal way of asking, how relevant is the manager's experience to this situation? It may be noted that this account of the matter is consonant with our feelings about it. For the degree of confidence with which a manager will assert that a particular course of action is correct, correlates 103. In some way with the extent to which he regards himself as being on familiar ground. If the situation in which he finds himself is utterly novel, he will assuredly feel rather unhappy about any decision that he may reach because there is nothing to guide him. In formal terms, the translation of the model into reality requires that it undergo certain changes, and in the case considered the rules for making these changes are quite unknown. When, on the other hand, the situation is entirely familiar, we may say that the rules for making the changes are well specified. The prognosis from the model is therefore made with a high degree of confidence, and the transformed model will be a most accurate predictor of the eventual facts. It now becomes very clear that the scientist who tackles a management problem is in a totally different situation, for he declares hopefully that he comes upon the situation with a fresh mind. He believes this to be a good thing, but our explanation of his approach must begin with the alarming acknowledgement that he has by definition no historical models of the situation with which to set up correspondences to the present model, and that again by definition he cannot possibly know any of the rules for changing this model to make it fit tomorrow's reality. It is noted in passing, then, that insofar as the scientist can ever achieve success in solving a management problem, he is in no way imitating the manager. This decisively disposes of a view often expressed in management circles that an operational research team is best regarded as a group made up of men who have the time to undertake some detailed thinking about a problem which the manager would undertake himself if he were not too busy. This interpretation of or is typical of the contemporary degradation of the word science which was commented upon earlier. Then how do we account within this methodology for the approach of operational research? The answer is that although the scientist has no historical models of the situation with which to compare his present model, he has other sorts of model which he can use. It must be remembered that the managerial task is concerned with the control of large and complicated systems. The scientist, quite apart from any relationship he may have had with enterprises, has inevitably been trained to understand the structure and control of some large and complicated systems. For example, he may be an expert in thermodynamics, in which case his memory will contain a richly endowed and profoundly understood model of the behavior of systems whose activity is characterized by changes in entropy, and such systems range from heat engines, through communication systems, to the operation of the entire cosmos. 104. Then suppose the thermodynamicist seeks to make a detailed and formal comparison of the correspondences between this model and the model of the system which represents the enterprise. As was noted earlier, the model of any one system stands in some sort of correspondence with the model of any other system. The question is only whether the correspondence is great or small and therefore more useful or less useful. If it is useful to a sufficient extent, and useful in the right way, the scientist will solve the manager's problem. The reason is this. If it is possible, by effecting this correspondence, to discuss the enterprise as if it were a heat engine, many benefits at once accrue. For the whole of the insight which the scientist has into thermodynamic systems becomes, again within the limits specified by the methodology, an equivalent insight into the behavior of the enterprise. Moreover, all the techniques of description and experimentation and in general of handling models, which the scientist has acquired in thermodynamics, will now be available to him for dealing with the manager's problem. The parenthetical reservations continually made in this passage about the validity of the correspondences, and the limitations of the methodology, will be examined properly in the next section. In the meantime, however, it will be well to complete the picture of an operational research team in action. It was explained some time ago, and at some length, that it is of the essence of operational research to be an interdisciplinary undertaking. The team approach was found, for quite practical reasons, to be vital. It is now possible to comprehend the formal basis of this requirement. Although we have not yet specified the methodological justification for the procedure just outlined, we have already seen that this is not a matter of searching for a perfect correspondence between two models, and of discarding all those potential models which are at all imperfect. The matter is, we said, one of degree. Confidence in prognosis derives from some measure of the extent to which the two representations can be matched point for point. So the thermodynamic insight which has been considered is fairly useful, that is to say, it is certainly not useless, and almost certainly not ideal. But the next member of the OR group is a neurophysiologist. The model he really understands, is trained to manipulate, and so on, concerns the nervous system and particularly the brain. Now there are obvious resemblances between the controls used in an enterprise and those used in the human body. For example, both are hierarchical, both are redundant and both incorporate subsystems of greater and lesser. 105. Autonomy. Very well then, this scientist too can contribute to the matter in hand under the same limitations and provisos as the thermodynamicist. And so the argument continues for any number of scientists and any kind of science. It is not perhaps difficult to see that a case of this kind can be made out to show how insight into any branch of science might be relevant to any kind of managerial situation. If there is any doubt about this contention, consider the limiting case. In the last resort, any physical system resembles any other to the extent that each endures. Admittedly, if this is the only point of correspondence which can be demonstrated, the attempt to enrich the managerial model by the scientific one will not be very efficacious. But it is really rather important to understand that the procedure is never totally irrelevant, never completely inapplicable. Now comes the final point. If an or team consists of a group of scientists, trained in different disciplines, and each capable of transferring his own scientific insights to the enterprise, the or team as a whole is focusing spotlights from a number of different directions on the point at issue. The understanding of each, and the value of the contribution that can be made by any, may be defective and partial. But the insights supplement each other, supposing only that the scientists have learned to communicate among themselves. The whole process may be compared, by a simile, with the process of triangulation in a survey of terrain. A point may be identified with great accuracy, given that approaches are made to it with fair accuracy from several directions at once. 3. Some terms explained. What has been said so far can hardly carry conviction, because of the vagueness of the sense in which the comparison between managerial and scientific models was drawn. As so far described, the methodology seems to depend on the examination of similes, which is well known to be dangerous and highly suspect. It is all very well to say that the control system of an industrial company is like the central nervous system in the human body, but what does this mean? At the worst, this is a glib literary metaphor. At the best, perhaps, the analogy will hold a certain amount of water, but even then it may be of no real use. Everyone knows, in particular, that even when a comparison is basically sound, it is all too easy to employ it illegitimately. You are carrying the analogy too far, we customarily say. It is fully agreed that if nothing 106 better than this can be done, the developing methodology is futile. If the grandiose claim to he expounding a new account of the scientific process is to be substantiated, a far more rigorous attempt must be made to specify what is going on. In order to discuss this critical point with any precision, it will be necessary to use a few strange terms. The vocabulary of ordinary English is simply not adequate to the task with which we are now confronted, and a few new words will have to be introduced. Perhaps this calls for apology. On the other hand, the terms now to be explained are really extremely useful in discussing management systems. It is very possible to argue that one of the reasons why our thinking about the theory of management has been so thin and so ineffectual is because the only concepts available for which we have names are so trivial. In fact, the ideas to be discussed in this section are derived from 3 branches of modern mathematics, all of which use these words. They are group theory, set theory, and algebraic topology. Of course, no attempt can be made here to discuss the mathematical issues, but they are irrelevant to these purposes. First, we shall often refer to a set of things. A set is no more than a properly specified collection of items, called elements of the set. Thus the whole of the plant in an industrial company may be thought of as a set, the elements of which are machines. Or the elements could be components of machines. A set is described, that is to say, by nominating its elements, and whoever is doing the talking is at liberty to choose what elements he intends to discuss. So there is a set of machines which exhausts the company's plant, a set of employees which exhausts the company's payroll, and so on. These are finite sets, they are exhaustible. There are also infinite sets, however, and these are the most important because they facilitate the discussion of collections of things which can be precisely nominated, but not exhaustively enumerated. The set of the natural numbers 1, 2, 3, 4 belongs to this class. And of course it is also most convenient to use this terminology to refer to finite sets, the elements of which could be exhaustively enumerated, without bothering to enumerate them. This means being able to speak of the set of the company's present customers, for example, and knowing they are all included, without having to list them in an appendix. Next comes the idea of the partition of sets. Obviously, sets can have subsets. The commonest form of partition in ordinary life, and particularly in the company organization, is to define a set of subsets which exhaust the set and do not overlap. An organization chart tries to do this. The set of commercial responsibilities is partitioned, for example, into 107. Home sales, and export sales. The idea is that any element of the set should also be an element of one, and only one, subset. Then the commercial manager can go home. This is the delegation of responsibility. In practice, of course, the rules which govern the partitioning are not always clear, the subsets may intersect, and there may be elements of the set which turn out not to belong to any subset after all. Because of the last point, it is often useful to nominate a complementary set, which is the totality minus all the subsets. This will account for anything left over from the major classification. If that classification is well made, however, nothing will be left over. This does not matter, it simply means that the complementary set has no elements and this is called a null set. The utility of the complementary set may be noticed in many large business organizations in which a manager can often be identified whose responsibilities are those that arise from time to time and yet do not clearly belong to someone else. Now it will be remembered that in speaking of models of managerial and scientific situations the idea of correspondences between them was brought forward. To convey the idea of good correspondence, we spoke of models corresponding point for point. See what this means formally. There is a finite set whose elements are the letters of the English alphabet. There is also a finite set of the natural numbers 1 to 26 inclusive. It is perfectly obvious that these two sets can be placed in correspondence with each other, and that if they are there is one number for each letter. This is called a 1-1 correspondence. And the process of making that correspondence is called a mapping. In this case, then, the set of 26 letters may be mapped onto the set of 26 numbers. This operation could still be carried out if we used the infinite set of natural numbers. The 26 letters could be mapped, by 1-1 correspondence, onto any nominated subset of 26 numbers. This is the more general case of a mapping. We say that the alphabetic set is mapped into the set of natural numbers. When a mapping is being made, an element in the target set onto which an element of the original set maps is called the image of that element. Suppose, then, that we wish to undertake a mapping. For example, a sentence could be encoded into a row of numbers by turning A into 1, B into 2, and so on. We establish our sets, we demonstrate the 1-1 correspondence. We now need the rules for changing the elements of one set into those of the other. Note that it is not enough to say change, for A could become 1, 3, or 25. It is necessary to specify a transformation. That is to say, one needs a code if something is to be encoded. So if, for 108 example, the set 1, 2, 3, 4, 5 is to be mapped into the set 2, 4, 6, 8, 10. The mapping is specified by the transformation B equals 2A. This defines a 1-1 correspondence. The transformation B equals A plus defines a many-one correspondence. A mapping from the set 1, 2, 3, 4, 5. Now takes 5 as the image of every element. So far nothing at all has been said about the internal relationship between the elements of a set. If the set is in fact identified with a system whose parts are the elements of the set, then each element is defined by its function. Consider an internal combustion engine, and break it down to its ultimate parts. These are the elements of the set of components, and each can be defined by its function, which is to say its relationship to some subset of other elements. So there is also a set of the functions of components. Now take another engine off the same assembly line. Here are two sets of components, and they can be mapped onto each other. Not only is there a 1-1 correspondence between the elements of the sets of components, but between the elements of the sets of functions. In other words, if the first engine works, so will the second. There is a special name for a mapping which not only involves a 1-1 correspondence of elements, but which also preserves operational characteristics in this way. It is called an isomorphism. The Greek derivation throws light on the denotation of this term. Isomorph means having the same form. Of course, all this ought really to be explained with mathematical notation, then the preservation of operational characteristics could be precisely observed, and the formal rules for establishing isomorphism could be explicitly stated. But here the concern is with borrowing the term, and therefore with its basic, not algebraic, description. The final notion that we need is a little more difficult to grasp, but it is very important. Suppose the alphabetic set AZ is taken, and divided into halves, the subsets AM and NZ. These are then mapped into the set of numbers 1 and 2. There is a 1-1 correspondence here, if the subsets are regarded as single-valued elements of the total set. Alternatively, the original elements may still be used. A mapping is defined whereby the transformation of each letter AM is to the image 1, and of each letter NZ is to the image 2. This mapping involves a many-one correspondence, and it is not isomorphic. Even so, the transformation can be arranged so that certain operational characteristics concerning the relationship of elements are preserved. When this is done, the result is a homomorphism. This is the end of the quest for useful new terms, and, since homomorphic transformations play a key part in what follows. 109. Lows, some attempt must be made to illustrate the point about the preservation of certain operational characteristics, this being the aspect that is hard to understand. As many people know nowadays, decimal arithmetic is a pure convention, computers use binary arithmetic, and the octal scale may be of more use to people in future than the decimal scale. Suppose we want to work in an arithmetic with a scale of, say, 5 using only the numbers 0, 1, 2, 3, 4. Now it is possible to specify a transformation that will map the infinite set of natural numbers onto this other finite set. It could be written down as in Table 2. Clearly this transformation involves. Table 2. Specification of transformation. A many-one correspondence. To illustrate this forcibly, the table might be rewritten as in Table 3. Table 3. The many-one correspondence of Table 2. In the new arithmetic, there will have to be new rules of addition. For 4 plus 3 equals 7 cannot be written this way since 7 does not exist in the vocabulary. Accordingly, a rule for adding numbers must be provided. The rule is set out in Table 4. To find out what is the sum of two new numbers, 110. Table 4. Addition rule for 5-valued arithmetic. Of them is entered in a row, the other in a column, the intersection of row and column gives the sum. So 4 plus 3 equals 2. Is the transformation we have made homomorphic? Certainly it is many-one. To test for homomorphism, the mathematician would demand that certain operational characteristics of the arithmetic are preserved. It is now possible to exemplify this test, and thereby to give an indication of what is meant by the preservation of these operational characteristics. For this illustration, we shall add the numbers 11 and 19. As we know, the answer is 30. Here is the test. Consider these numbers as elements of the first set, add them and transform the answer. Then transform these same numbers into elements of the second set, and add them. The answer should be the same. It is worth going through the mechanics of this simple test to understand exactly what is happening. In the first half of the test, the addition is done in ordinary arithmetic, thus, 11 plus 19 equals 30. Transforming 30 by the given rule, which is read off either Table 2 or Table 3, the answer is 0. This is the image in the second set of the element 30 of the first set. The second half of the test requires that the mapping be effected separately, in advance, for each of the elements to be added. Thus, transform 11 by this rule answer, 1, transform 19 by this rule answer, 4. We now add these two answers, using the addition rule given by Table 3, and the answer is 1 plus 4 equals 0. The two methods yield the same result, so we are dealing with a homomorphism. And we have seen how certain relationships are transferable between the two sets. We say in fact that in the new arithmetic the operations of the old arithmetic are preserved with respect to addition. 111. For the homomorphic model. Returning now to the general argument about the nature of operational research, it should be possible to make clear what the formal scientific processes really are. The discussion so far is summed up in Figure 3. Here is the managerial situation, of which a conceptual model has been formulated. This means that we have taken a spare copy of our direct perception of the facts. No doubt we have incorporated into this conceptual model all the insights that we have obtained into the way the Figure 3. The process of scientific analogizing system really works. Similarly, the operational research team has selected from its scientific situation a conceptual model, incorporating its insights into how that situation really works, which it believes bears marked resemblances to the managerial situation. It then considers possible agreements between these two models. It tries to determine the extent to which the behavior of the one system throws light on the behavior of the other, in what ways the theories currently maintained by scientists in the one area might be transplanted into the other, whether the actual techniques of research and computation are appropriate, and above all, whether conclusions which hold for the one system hold in the other. The question left over from the previous discussion, which has now been reformulated, was to know under what methodology the correspondence could be regarded as rigorously valid. There are various levels of comparison at which the scientist might be trying to work. Firstly, there is the metaphor. But the metaphor is a 112. Poetic device, and its validity is aesthetic. It can offer science no more help than its verbal facility. Secondly, there is the level of analogy. The validity of this comparison is a logical validity, and a lot has been written by classical logicians to account for its usefulness and to circumscribe its limitations. But the explanation is essentially philosophic rather than scientific. The validity of a particular analogy must always be open to disputation, and its relevance in a particular instance cannot be formally demonstrated in a conclusive way. This leaves the third level of comparison, that of identity itself. If two things are literally identical with each other, then conclusions that hold for the one will surely hold for the other under similar conditions. But in this case the two things being compared are clearly not identical in any ordinary sense, if only because they are models of different things. The validity of the comparison of identity between things which are not in fact one and the same is a mystical validity. And mysticism is not generally regarded as useful to science. It may offer insight, but the vision is cloudy. In fact, there is in the research scientist's mind a blend of all these levels of comparison. In his own head, the scientist probably is thinking metaphorically. At the same time, he is aware of a need to couch his metaphor in severely analogical form so that it can be closely examined and tested, but the more he hopes to do this, the more he sees himself as destroying the identity relation that the metaphor poetically enshrines. The whole process is self-defeating, and the description of it is no more than an historical legacy. To use more modern terms, the scientist is attempting to establish a mapping between the two conceptual models, under some transformation which he would like to be isomorphic. How can he proceed and set about this task? His two models are conceptual, literary things. They are not well formulated in scientific terms. Therefore the first task must be to use the tools of rigorous science to formulate them more precisely. The scientist must undertake this part of the task in the only languages he knows how to use with precision, the languages of mathematics, statistics, and logic. All three are highly developed scientific tools. Basically, the first handles notions of quantity, the second notions of probability, and the third notions of quality. They are languages whose grammar and syntax is developed to a remarkable degree. The scientist therefore engages in a process of mapping each conceptual model into a neutral scientific language. This is a process in which some of the conceptual richness must inevitably be lost, for some of that richness depends on nuance, and some on association, and some on mood, none of which is transferable into rigorous terms. But 113. In return for this price, the scientist will obtain an account of the conceptual model that is precise and unambiguous. Returning once again to formal terms, the scientist now defines a set of transformations by which he can map contents of mind onto algebraic propositions. The correspondences are many. 1. This is what a loss of richness means. And if the well-formulated result is to represent the antecedent set successfully, it should be homomorphic. 2. The conclusion of the argument should now be clear. Having refined the conceptual models, the contents of mind, according to this procedure, the scientist produces two deeper-level homomorphic models, and these may well be isomorphic with each other. So he has achieved an identity between the managerial and the scientific situations which is shorn of mysticism and of poetry, and which is completely free of the bedeviling disputation that attends analogy. This, it is suggested, is the character of the scientific model depicted in Figure 4. A scientific model is a homomorphism onto which two different situations are mapped, and which actually defines the extent to which they are structurally identical. What is dissimilar about the original situations is not reflected in the mapping, because the transformation rules have not specified an image in the set the model constitutes for irrelevant elements in the conceptual sets. If the transformation has ignored as irrelevant elements which are in fact relevant, then the model will lose in utility, but it cannot lose in validity. This is its peculiar strength. Now the measure of utility is vitally important, but it may be accomplished by straightforward testing of the predictive value of the scientific model. If this predictive value is low, we had better start again. But if it is high, we can use it with confidence, and without further worry as to the appropriateness or otherwise of the analogy drawn at the conceptual level. This exposition is meant to account for what the scientist does, it is not meant to state what he explicitly sees himself as doing. However, some operational research has been undertaken which quite specifically takes account of this process, and tries to use the explanation to validate itself by specifying the mappings involved, making rough measures of the information dissipated by the many correspondences of the homomorphism, and by testing the model within the terms of the description according to its reaction to partition. It is worth noting that university teaching in operational research is devoted mainly to the study of particular mathematical techniques, and that the thinking on which this instruction seems to be based is that the modeling process is one of the direct algebraic formulation of relationships believed to exist. 114. Within the managerial situation. That is, the right-hand side of Figure 4 is altogether ignored, and the mapping processes of the left-hand side are not formally studied. Such activity should be referred to as applied mathematics, and not as operational research. In fact, the man. Figure 4. The nature of a scientific model. Whether he fully realizes this or not, is invoking analogical thinking derived from his scientific training in other fields, and it is surely best that this is recognized and the process examined. Where operational research has gone even further, by deliberately ignoring its roots in general science, and by trying to create mathematical models purely by abstraction from the system under study, the models have invariably 115. Been lacking in a reflection of the viability of the real-life system. The scientist should not only recognize his dependence on scientific insights from other fields, he should encourage it. For what is robust, dynamic, and viable about the real-life situations which the manager handles is mirrored in the processes of nature which scientists study in all their forms. In conclusion, and for the time being, Consider just one exemplification of this methodology in action. It is designed to illustrate yet another feature of its special value to operational research, as distinguished from other modes of scientific activity. An investigation is being carried out within industry, and a learning process is detected. For example, a big new plant has been laid down characterized by a number of novel features. When it begins to operate, its output is only a fraction of its intended capacity. But, as time goes by, the output rises, the plant is learning its job. Now this phrase may of course refer to many features of the total system. Doubtless the operatives are learning how to manipulate the plant, the engineers are learning how to sequence its output, the managers are learning how to control the whole project. Even the inanimate plant itself may be learning in some sense, all engines run themselves in. But we are not concerned with these details, and especially not with the precise sense in which any part of the total system may be said to learn. From a sufficient distance away, say the chair of the managing director, this plant is an indivisible whole, it has an output, and this output improves over time. The operational research people may be asked to estimate the level of output in a few years' time. They may be asked to estimate output of a new plant from its inauguration to the moment when the designed capacity is achieved as output. Of course, the very use of this word learning implies a biological outlook. It is perhaps not the sort of term which it would occur to an engineer to employ. But if there is an animal psychologist in the OR group, he will quickly have observed that the task set by the management is indeed to describe a learning process of some kind, and he will contemplate his knowledge of animal learning processes, which have been rather extensively investigated. He may consider, for example, the case of a rat learning to run a maze. This situation has been carefully studied, because the task which has to be learned can be unambiguously defined. The maze is an interlinked series of passages. There is only one entrance, but there are two exits. The rat is put in at the entrance. If he emerges from the right exit, he will be rewarded with cheese. If he emerges from the wrong exit, he will receive a punishment in the form of a mild 116. Electric shock. In running the maze, the rat has to take a number of binary decisions. It may turn left or right at each junction. Since there is no prior experience of this task, and if the maze is symmetric in relation to its exits, it may confidently be predicted that the rat has an equal chance of being right or wrong on its first run. Depending on the result of this run, the probabilities of the outcome will begin to change. After a sufficiently lengthy series of trials, the rat will learn the maze, and will almost invariably run correctly towards the cheese. The animal psychologist, in contemplating his knowledge of these facts, is setting up a conceptual model of a rat in a maze. To inject any kind of scientific rigor into this picture, a new model must be created, one which can be formally expressed and tested. This process has already been carried out by the animal psychologists who did the work, and the OR man can look up the results. He finds a chart on which the horizontal axis is marked out in a series of trials, and the vertical axis expresses the probability of the rat's failure to run the maze correctly. It is easy to realize that the line found on this chart begins at the first run with a 50% probability of failure, and that this probability declines over a series of runs until the line almost touches the horizontal axis itself, probability of failure being very low indeed. The shape of the curve is concave, and the typical curve represents the typical behavior of rats. Now this is, according to the terminology of this chapter, a homomorphic model of this learning process. It is, after all, a many-one transformation of the conceptual model. A good deal of information has been thrown away. No data have survived concerning the color of the rats, the noises they made, nor the variation that is found between rats. But the particular relationship which is of key importance has been preserved. That is, we know on the average how long it takes to reach any given percentage of final success. Let us now take this model as being isomorphic with another model of a machine which is capable of running a maze. That is to say, could we build an artificial rat whose behavior in the maze would be indistinguishable from that of a live rat? The answer is clearly yes, and indeed the job has been done. An artificial rat begins its learning task by making a random choice at each junction of the maze, and therefore has a 50% probability of reaching either exit on its first run. It is then made to store in an electronic memory the successive experiences of its trials, and this stored information is used to bias the probabilities of a left or right-hand turn at each junction of the maze. The logic of the control equipment can be designed so that the probabilities are actually used to procure a final learning curve indistinguishable from 117. That of the original animal. So, following the methodology set out in Figure 4, a scientific model is now available, consisting of a mathematical expression which defines the learning curve, statistical information about individual variation from this curve, and a logic which determines a behavioral link between stored probabilities, which change from trial to trial, and the rate at which total success is approximated. Let us note in passing that the methodology serves well in this respect, that we have an identity relationship between the live and the mechanical rat over a precisely defined area of activity and not over others. It is no good, for example, feeding grain to the mechanical rat, or trying to disconnect the live one. These are judged irrelevant elements in the sets defining the two rats, and have not been mapped onto the scientific model. The question now is whether this scientific model, already investigated in two dissimilar situations, will apply to the industrial plant. Again, the OR group would work backwards from the scientific model, which is of complete generality, to formulate what is intended to be a homomorphic model of the learning plant. The conceptual model of the plant is already known, and it now remains to establish the homomorphic mapping between these two. It is probably found that some adjustment needs to be made, most usually by way of constraining the completely general model in some way. For example, the a priori probability of achieving the rated output on the first run may not be 50%. Thus it is over this link that the more familiar experimental processes of science are carried out. But there is no need to be so vague as to say that the OR team is here engaged in trying to discover some mathematical formulation of the industrial problem which looks as if it might be appropriate, and then in proceeding to test it by any means in their power. We have instead, at this juncture, a rather precise problem of specifying a particular homomorphic transformation which will achieve a valid mapping between unambiguously specified sets. The total picture is illustrated in Figure 5, in which the general methodology of Figure 4 is adapted to the present example. It will be seen that all three real-life situations, concerning the plant, the live rat and the mechanical rat, in some sense resemble each other. They all learn whatever that means. At the level of their conceptual models, an analogy exists between them which can be inspected by the methods of classical logic. Each is then mapped homomorphically onto a rigorous mathematical formulation, and these three homomorphs of reality stand in isomorphic relationship to each other. They are therefore embodied. 118. In a scientific model which equally represents all three situations over a well-defined range of activity. Hence we have made use of a model from animal psychology, by pursuing it downwards to a scientific generality, pursuing it upwards to an experimental verification, and Figure 5. Application of the theory of models to a learning problem in industry. Then by pursuing it upwards once again to another problem-solving situation. A predictive model such as this is eminently suitable for resolving the managerial problem originally posed. The peculiarly advantageous feature of this methodology for operational research is that a correct answer is obtained by virtue of a behavioral definition of learning that identifies only what counts as being of interest to the management. In other words, although this word learning has been invoked, no. 119. One in the OR team or in the management group has the least interest in isolating the nature of learning as such. He has no interest in arguing about the right use of the word as a psychological term, but only in results. So the OR man is a special kind of scientist, for he does not have to bother with determining the laws governing basic natural phenomena such as learning. This is a preoccupation for the academic animal psychologist, who has a special responsibility to define the terms to be used in his science, and to denote the mechanisms for which the terms will stand. The or man has, however, other concerns which do not preoccupy the academic scientist who normally regards himself as a specialist in a fairly narrow field. He must operate across the various scientific disciplines, being sufficiently knowledgeable and mentally agile to identify the model he needs. For, to take the quoted case, it is not every or group that includes an animal psychologist. Or, if it happens to do so, it may not include the thermodynamicist whom we met before, nor the population geneticist whom we shall meet later. Secondly, the or man seeks other kinds of natural law than those normally investigated academically, namely those which are themselves interdisciplinary. For there are laws that apply to systems in general, and to control in general. These are the laws that management would like to discover. There are also laws, it may be thought, that have to do with logical induction and in particular with the conduct of operational research. Perhaps the methodology advanced in this chapter may diffidently be claimed as an example. 120. 7. Models in aspic. The world is not made up of empirical facts with the addition of the laws of nature. What we call the laws of nature are conceptual devices by which we organize our empirical knowledge and predict the future. R.B. Braithwaite in Scientific Explanation. 1. Reflections on models. The talk about models in the last chapter led to talk about laws, the laws that govern systems and indeed the laws that govern nature itself and therefore scientific inquiry. It may seem that the concept of a model, even when stiffened by the substance of homomorphism, offers but a weak account of natural law. Nonetheless, the laws of nature with which we all grew up, are not the absolute truths most people think them. They are essentially consequences of the conventions under which we formulate our thoughts about the world. They are deducible from the theorems which make formal languages consistent. This is a complicated and philosophical point, and one which is therefore often missed by scientists themselves. For example, scientists have not been quick to follow up the last great work of Eddington, his fundamental theory, a work which perhaps gives scientific expression to that philosophic thought. For what Eddington seems to be doing is to investigate the language in which science expresses itself, and to generate from it facts about the world outside. Of itself, this appears to be impossible, but if the idea is once grasped that a language that is competent to describe the world must be a mapping of the world, the process seems less silly. This may also be the answer to those who complain that modern philosophers, such as Wittgenstein, spent their lives in sterile linguistic analysis. If the language, whether mathematical or 121 metaphysical, is isomorphic with the world of fact, then its structure will reveal relationships which are true of the world itself. But how those relationships are expressed, where the emphasis lies, and hence in the long run whether those relationships are necessary or contingent, will depend on which language we use. For in practice, the mapping will be homomorphicable to preserve some structure, but committed to losing some information. Thus our account of nature is true, but defective, and our account of such characteristics of nature as causation and law will change with the linguistic mapping we choose. But if all this sounds obscure, the point is expressed with lucidity in the quotation given above. Science is certainly based upon fact and experiment, but the organization of its findings into coherent and useful generalizations is a subjective process. Perhaps the most pithy expression of this point was given 200 years ago by the philosopher David Hume when he wrote, "Necessity is something that exists in the mind, not in objects." It therefore comes about that the so-called laws of nature are contingent, and not absolute. They are contingent on the languages we use to express them, both as to the structure of those languages and their frame of reference. Thus as science collects more and more observations about the world, and undertakes more and more experimentation, discovery often awaits a conceptual breakthrough, a bursting of the thought blocks of the scientist himself. If the language is quite general and relatively unconstrained, we are not prompted to question the conventions it places on our thinking. And so a law of nature is derived from what is no more than a model of such general utility that it is never even recognized as such. Perhaps the ultimate model of the structure of the universe is indeed the structure of the human brain which contemplates it, For insofar as our brains can penetrate the mysteries of nature, they are mappings of the universe. By the reverse argument, we can understand only those aspects of the universe into which our brains will map. This is such a serious and ineluctable limitation on human understanding that one never hears it expressed. Yet, by these same standards, the homomorphic models previously discussed entail consequences that are natural laws. That is to say, their logical status is the same as that of the more familiar general statements about the universe, only their applicability is more circumscribed. What we usually call a natural law is a statement about a particular model of the universe. What we here call a model of a problem situation entails its own localized natural laws. All this is said to emphasize the validity of the processes under discussion, which must not be looked upon as tricks peculiar to operational. 122. Research. Although the whole field of scientific induction is difficult to penetrate, the inductions made by operational research are no more and no less difficult to understand and justify than those of any other kind of scientific activity. They simply make a more agile use of models than is customarily necessary in science. If the theory put forward in the last chapter is an appropriate account of what goes on in operational research, it also explains to just the same degree the nature of every developed scientific activity. Indeed, any set of rules for the making of inductions is itself entailed by a particular descriptive language, and to quote Hume once more, they are very easy in their invention, but extremely difficult in application. Success in their application is a matter of practice, not on behalf of individuals but of a society. How the descriptive language is to be acceptably manipulated, how the set of rules is to be acceptably applied, and therefore what emerges that will count as a valid model, these things are social conventions. Any society of scientists develops these conventions, although what is acceptable in one branch of science, or even in one school of that branch, will not necessarily be acceptable in another. Sooner or later, the model and all its trappings, so essential to actual progress, may begin to dominate truth. As new facts accrue, they are fitted into the language in a way that makes them consonant with the model, which expresses their consequences in a way that reinforces the rules of induction and ends of behavior itself. The italics draw attention to the fact that eventual outcomes are conditioned by this modeling apparatus. Facts, which are commonly supposed to be objective, turn out not to be unconditionally so. This was remarked elsewhere in this book. Now it is also seen that facts, which are popularly supposed to be neutral, turn out to be purposive, because of the way they are assimilated into a situation. This state of affairs is dangerous to science, if it is not clearly recognized, for it can block new discoveries. Progress in science might well be defined as the overthrow of a model, and its appurtenances, that has exhausted its usefulness. The great scientist is one who sees the need and the moment to destroy a mode and who can also create its successor. Perhaps the same is true of the businessman and his business. But science itself is in the long run protected against the dangers of its own intellectual apparatus. In the first place, it is founded on observation and experiment. Eventually the model that is no longer useful, and the model that can no longer encompass the scope of the scientist's insight are overwhelmed. For if objectivity and neutrality in science are nowadays 123. Regarded with more suspicion than our fathers showed in them, something of the objective and the neutral breaks through into our work from outside ourselves. In the second place, and most significantly, the intention behind doing science is to expose a reality beyond our own imagination and desires. Even when the scientist is most horribly trapped within his own conventions, it is in his own acknowledged interests to escape. Thirdly, science is aware that it deals in models and conventions, it is therefore well placed to keep a watch for insidious effects. Science, in the form of operational research, serves managers of business, industry, and government. These operations too provide a social milieu for intellectual processes of decision and control. All that has been said about languages and their conventions, models and their limitations, rules of induction and their consequences, applies as well to such occupations as to scientific pursuits. The dangers are the same, so are the opportunities. Only the protection allowed to science is notably missing. Management is not founded on observation and experiment, but on a drive towards a set of outcomes. These aims are not altogether explicit. At one extreme they may amount to no more than an intention to preserve the status quo, at the other extreme they may embody an obsessional demand for power, profit, or prestige. But the scientist's quest for insight, for understanding, for wanting to know what makes the system tick, rarely figures in the manager's motivation. Secondly, and therefore, management is not, even in intention, separable from its own intentions and desires, its policies express them. Thirdly, management is not normally aware of the conventional nature of its intellectual processes and control procedures. It is accustomed to confuse its conventions for recording information with truths about the business, its subjective institutional languages for discussing the business with an objective language of fact, and its models of reality with reality itself. Nothing emerges more clearly from this analysis than that management operates through a model of the business, a model in which the organizational structure, the structure of costs and prices, the structure of labor relationships, the structure of production itself, are all homomorphic mappings of the real thing. It is only in the works of Lewis Carroll that one finds a king who was really determined to have a truly isomorphic map of his country. He settled for the only one there is, the country itself. If a manager wants to do that, our theory can still handle the situation because there is an identity mapping in the language we are using which maps a group onto 124 itself. The trouble is that no manager can really handle the full-scale isomorph of his enterprise unless he is the only employee. To delegate is to embark on a series of one-many transformations. The manager can at best settle for a homomorph consisting of all the ones. Neither the earliest scientists, long since dead, nor the earliest managers, many still extant, were particularly concerned with problems that fitted this pattern of development. They had not got as far as seeking out systems and analyzing their structures. For as men began to probe the nature of the universe, or as managers appointed men to probe the nature of their enterprises, careful and systematic observations were taken for the first time. And the things that were seen and measured themselves constituted important discoveries. As late as the 17th century, Leeuwenhoek was the first man to see bacteria. In doing so he discovered something new about nature. As early as the 19th century, F.W. Taylor was the first man to measure the work involved in a man's shoveling coal. In doing so he discovered something new about industry. Today the optical microscope does not make discoveries. New insights into nature require that observations and experiments be compounded into hypotheses that explain natural systems. Equally, work study does not make discoveries about industry. Advances now depend on compounding facts obtained by such tools into models of business systems. The lag between knowing the facts and knowing the system which generates the facts can be considerable. It is one thing, for instance, to cut up the bodies of animals and to discover that each contains a heart. This fact has been known for thousands of years. It is another thing to suggest that blood flows from the heart to the lungs and back again. The man who first did that was burnt alive. But it was not until much later still, in 1628, that De Motu Cordis was published, giving William Harvey's account of the circulation of the blood. This represented insight into the underlying mechanism. It really said something as to what the facts were all about. Similarly, there is a lag in passing from the stage in which sets of empirical observations constitute exciting discoveries, to the stage of insight into underlying mechanism, in every field of management today. In controlling the economy and diplomacy and society at large, in controlling business and industry and commerce, we have collected facts and perhaps identified systems. But we have barely begun to explain their underlying mechanism. This is what operational research is for. It is in the natural course of the development of science to investigate such systems now. For they offer a new kind of challenge. In practice. 125. They are not susceptible to total dissection, total analysis, total measurement, perhaps they are inherently insusceptible to such complete specification. But this does not necessarily mean that we cannot identify their underlying mechanisms. The process of homomorphic modeling is at the least a heuristic method for inferring the existence and structure of systems of which the complexity defeats isomorphic modeling. It is now time to look more closely at a few operational models, to see how the process works in a little more detail. The examples which follow come up in no particular context, they are arbitrarily chosen to span the course of history, to span areas of application, and to span varieties of analogy. They are not connected with each other by anything more than their method, and they testify to nothing more than their own existence. They are models preserved in aspic, taste and see. 2 applications, an early operational model. If the early scientists did not use this method of consciously constructing a model, when did it first emerge? The technique of scientific analogizing in the more literary sense has a lengthy history. Philosophers, for example, have always been prone to compare a metaphysical system with a scientific system in just this way. As we have seen, the comparison itself achieves a scientific status only when a rigorous attempt is made to construct a formal mapping. The earliest deliberate attempt to conduct an inquiry on this basis that I happen to have encountered was made by a scientist of no less eminence than the Hon. Henry Cavendish, F.R.S., who published his results in Philosophical Transactions in the year 1776, which, as it happens, was the year of the death of David Hume. The problem facing Cavendish was this. There was a fish called a torpedo which delivered some kind of shock to anyone who touched it. A Mr. Walsh had brought forward supposed proofs that the phenomena of the torpedo were produced by electricity, but there were features of the situation with which this finding appeared inconsistent. For one thing, shocks were felt when the fish was held under water, that is, when there was an easier route for the electric fluid to take than through the human body. At the time of this work, some electricians contended that electricity passes along the path of least resistance alone, and that there could therefore be no flow at all along a more resistant path in the same circuit. So the shock ought to pass through the water, but not through the more resistant human body as it did. Moreover, when this fish produced its shock there was no spark, and no associated magnetism, 2 phenomena generally associated with electrical discharge in 126. Contemporary research. Cavendish wanted to verify or refute Walsh's assertions. Now it has to be remembered that when this work was done very little was known of the nature of electricity. Furthermore, the kind of apparatus available to scientists of the time for research into matters of this kind comprised batteries consisting of a series of discharging jars, Mr. Lane's electrometer, and a pair of pith balls. In these circumstances, no very obvious way of deciding the matter unequivocally by investigating the fish itself was apparent. Cavendish therefore studied the problem operationally, and it might be fair to call what he did operational research. In fact, he constructed a model. It was indeed a physical representation of the fish, which is described in full detail in Cavendish's paper. The model was made of wood, the electrical organs on either side being represented by flat pieces of pewter fixed thereto. These were connected by wires, through long glass tubes acting as insulators, to the positive and negative terminals of the battery. The whole thing was covered with sheepskin leather and soaked or immersed in water. For the model to impart a shock, the circuit had to be completed either through the wood or around the surface of the leather, or alternatively the experimenter could touch both of the electric organs simultaneously. With this apparatus Cavendish made a long series of experiments, systematically varying all the factors involved. He was in fact trying to simulate the operational circumstances, and took great pains to do so. In the course of the work he resolved all the difficulties that attended on Walsh's original explanation, and managed to get into mathematical form the relationships he discovered between various conductors in various kinds of media. He made tests in a tank, and also when the model was in air but still wet. He even simulated the effect of stepping on a torpedo buried in the sand while wearing shoes with wet soles. He attended also to the salinity of the water and recorded, for example, that seawater conducts 100 times better than rainwater, a factor that goes up to 720 times in the case of what the paper most charmingly calls a photorated foliation of Fia fault. So, by these operational means, Henry Cavendish resolved the problem. He did not prove the contention that the phenomena were electrical, but he did satisfy himself and others that this was a contention consistent with the facts. He also discovered the fundamental underlying relationships by experimenting with a model which had predictive value in that it could successfully forecast what experiences one would have with the living fish in any circumstances one cared to envisage. All that was nearly 200 years ago. Today the torpedo is more familiarly known to us as the electric ray. 127. Naturally, Cavendish would not himself have described what he was doing in the terms introduced in the preceding chapter. None of the branches of mathematics from which the terminology is taken were in existence at the time. It is nonetheless perfectly clear that in constructing his model Cavendish was undertaking a mapping. Momentarily at least, he set up a valid correspondence between the fish and the artifact. For example, his drawings clearly show that he copied exactly the outline of the fish in wood, hence its shape in plan is strictly isomorphic with that of the beast. In general, however, this was a homomorphic mapping. Cavendish was content with mignon correspondences. But at the same time he fully intended that the structural relationships with which he was concerned should be preserved in the model. As a result, his mathematical derivations measured the proportionality of electric charge flowing between various alternative sources and sinks. The rigorous homomorphic model, then, obtained fundamental structural information about the system constituted by the electrical phenomena involved. This outcome was surely more important than the confirmation of Walsh's hypothesis about the fish. It had quite general relevance. It was a death blow to the theories of some electricians who held that electricity followed the path of least resistance and none other. And what had been their error? Precisely the familiar error of failing to observe a system as being such. They wanted a simple rule which would select the answer from a range of mutually exclusive possibilities. They had evidently set up a thought block against a complex solution, in which every part of the system would have some role to play, and in which the possibilities were not mutually exclusive but could be mixed in varying proportions. This story is enchanting, rather fun. And admittedly the problem solved by this model was not a management problem. Oddly enough, however, it not only illustrates the key features of the OR approach, but points to the psychological difficulties which surround the use of that approach. Industrial managers faced with a problem in production control invariably expect a solution to be devised that is simple and unidimensional. They seek the variable in the situation whose control will achieve control of the whole system, tons of throughput, for example. Business managers seek to do the same thing in controlling a company. They hope they have found the measure of the entire system when they say everything can be reduced to monetary terms. And the Chancellor, 128, of the Exchequer, who tries to control the whole economic system by fiscal manipulations, is in the same difficulty. None of these things is possible, and arguments can be developed in each case to show why. More important, however, is the reason which underlies the denial of all three case solve for, if some electricians are included. It is that a ramified interacting system is strictly multidimensional and its structure cannot be preserved in a unidimensional mapping. In practical terms, this is because any conflict is apparently resolvable if it lies in a single dimension, whereas the homomorph required must reflect structures that support unresolvable conflicts. There is no unique path for the flow of electricity in a fully connected network, nor for decision-taking in a fully connected managerial situation. When Cavendish discovered this nearly 200 years ago, he advanced electrical theory. If managers could discover it now, they would encounter fewer strikes and fewer recessions. 3 applications, a recent operational model. Representations in physical terms of the homomorphic models underlying operational research work are, however, rare. They are instructive because they demonstrate, in a tangible way, the nature of scientific analogizing and of the underlying formalization, by rigorous statement of the identities that inform the analogy. Very often, physical manifestations of the analogy could be, yet are not, built. This may be illustrated by an immediate transition to modern times and to the proceedings of the Royal Society for 1955. Here, 180 years later, we find Professor M.J. Lighthill, FRS, making use of the same technique. He takes a different scientific model for the purpose of his analogy, but he also gives a mathematical formalization of underlying identities. Of course, the terminology put forward here as a means of explaining the inductive process involved was by this time available. Lighthill did not use it, but then he was not intending to comment on the basic nature of his method, only to expound his results. His problem was this: what approach can science make to the discussion and solution of the question, how should road traffic be organized so that the full benefits of our increased mobility can be enjoyed at the lowest cost in human life and capital? Now there are two basically different answers to this problem. First, the topic proposed is directly susceptible to scientific attack, at least in part. Lighthill began by noting that there is already an experimental science dealing specifically with this matter, the quantitative study of 129. Traffic flow, together with the analysis of resulting data by sophisticated statistical techniques. Some might call this work operational research, but it is better called traffic engineering. This is because its object is to improve a process, not to evolve a management policy. There are several aspects to the question posed in the last paragraph which cannot be handled by purely empirical techniques. Moreover, there is the problem of generalization, so familiar to science. To demonstrate that a particular street layout could be modified with advantage does not simultaneously adduce a general principle about the management control problem posed. Even when many particular cases have been studied, so that principles begin to emerge, the decision taker's criteria may call for information that is not available from an analysis of the existing traffic flow by itself. Secondly, then, comes the characteristically or approach, the construction of a model, based on some insight into an analogous system, and able to generate information not empirically available. Lighthill's paper, then, introduces what he calls a quite different method from that of the traffic engineer as such. His analogous thinking is derived from theories of the flow about supersonic projectiles and of flood movement in rivers. He takes his model in fact from the science of fluid dynamics. According to the classification of scientific activity adopted here, he is now using the approach of operational research. Whatever it is called, it is quite clear that this is a different approach from that of traffic engineering itself, despite the highly scientific nature of the research sometimes undertaken nowadays under that heading. The analogy used by Lighthill for his model begins from the insight of the fluid dynamicist that the flow of traffic along a road is analogous to any other kind of flow through any constrained channel. It is clear from the first that the analogy has limits of usefulness. Its application will be focused on a restricted range of problems. The reason is that vehicles are not joined together in a continuous flow, and that therefore the pretense that moving traffic is a fluid introduces a simplification. However, and interestingly, this particular simplification is often made in science, and is not as serious as it might at first appear. It has been emphasized earlier that distinctions which appear to reside in the nature of the universe may in fact be introduced by the language in which we seek to discuss that universe. Whether a moving stream is composed of individual and separate lumps of stuff, or is literally an indivisible continuum, may in the first place be merely a matter of resolving power. Water is a fluid, but we may think of it differently if we can examine its molecular structure. More important, however, is the fact that the matter is one of convention. 130. A man in a cinema can choose how to describe the film unfolding before him. He can examine his practical experience of the film show by introspection, and declare that quite certainly a film is a continuous process. Alternatively, he may examine the mechanics of projection and the piece of celluloid concerned. In this case he may declare that quite certainly a film is a collection of separate and distinct frames. In either case he is right. The assertions are not contradictory, for their validity depends on the language being used, not on the facts described. Similarly, it is common in astrophysics to employ mathematical languages which assume that matter at intergalactic distances is continuous, but of very low density. That is, instead of saying that it consists of lumps of solid material with a lot of nothing in between. This approach therefore treats solids as if they were gases, which at that distance seems quite acceptable. The comparison between thinking of the continuous and the discrete cases has the feel of a distinction without a difference. And so, in the present example about roads, we need not be concerned to ask whether the model from fluid dynamics is correct. We should be concerned only to survey the limits of the appropriateness of the language we propose to use. Thus Lighthill points out that the analogy between his kinematic model and a real road system is likely to hold for large-scale problems only, but if one considers arterial roads, where the traffic is crowded and sustained, useful conclusions may well be drawn. The model is then set up. According to fluid dynamics, the flow is a function of the concentration. This structural relationship in the proposed mapping has first to be tested empirically. It holds. Mathematical curves connecting flow and concentration are investigated. Their general shape is indicated in Figure 6. Naturally, the flow increases with the concentration until traffic becomes too heavy to be contained. The flow then diminishes until everything is at a standstill again. This is the point at which the underlying scientific model expressed in rigorous terms begins to emerge. Versions of the standard equations which describe this relationship in the case of fluid dynamics are developed in the language of traffic flow. If what the scientist is doing here be described in terms of a mapping, we can see that it is going to be homomorphic. For, if a continuum is to stand for a number of discrete objects, the translation from the one language to the other can be achieved conceptually by observing that the number of objects over any finite distance is infinite. Since one cannot compress an infinite number of vehicles into a finite stretch of road, the correspondence in this case is many-one. But that the system of relationships is nonetheless pre-131 served is demonstrated by the research, which shows that the flow concentration curve may yet be applied. It now remains to investigate the implications of the model as rigorously formulated by Lighthill. According to the discoveries of fluid dynamics, slight changes in flow are propagated along trajectories known as kinematic waves, whose velocity is given by the slope of the graph connecting flow and concentration. The tangents A and B in Figure 6 indicate wave velocities for the 2 points indicated on the curve. When this fact is mapped into the traffic situation, it becomes clear that a driver will experience such a wave whenever he adjusts his speed to that of the cars in front of his, by reacting to the next man's brake light, or by seizing an opportunity to overtake. Figure 6. General shape of a flow concentration curve. Now if a stream of traffic is dense in front and less dense at the rear, the kinematic waves associated with points I and II in Figure 6 have different velocities. Reflecting on this diagram, it can be seen that waves propagated from the rear are traveling faster than those propagated from the front, the former therefore overtake the latter. Given that a series of such kinematic waves can collide in this way, the model predicts the appearance along the wave collision route of kinematic shock waves. In Figure 7 we see how such a shock wave is formed. Kinematic waves ahead of it have velocities given by tangent B in Figure 6, and are therefore drawn parallel to that. Kinematic waves behind the shock wave are parallel to the wave velocity represented by tangent A. The shock wave lies where these two sets of waves collide. It is in turn parallel to the dotted core joining points 1 and 2 in Figure 6. When traffic runs into a kinematic shock wave, vehicular speeds will be sizably reduced quite quickly. All this conforms to experience on 132. Figure 7. Appearance of a kinematic shock wave. The road. The virtue of the scientific work lies in the predictive validity of the model describing this situation, for it is competent to forecast much more complicated effects in more elaborate situations. Suppose that a tributary road joins an arterial road, and that there is a period during which the traffic flowing in on this tributary is above the average. Clearly a knot of traffic will be generated which will continue to move down the arterial road. What happens when this intense local concentration of vehicles passes through a bottleneck, that is, a portion of road too narrow to accept the momentarily increased flow? What happens when the knot meets a junction? And how will the behavior both of the traffic, and of the backward propagating shock wave that it generates, vary for an uncontrolled junction and a junction that is controlled by traffic lights or a policeman? It is to questions of this type that Lighthill's work offers a quantitative answer. People have sometimes commented that it seems absurd to set up a complicated scientific theory to handle such questions. The outcome is to declare that the driver at the rear of a column of traffic encounters shock waves, which force him to accelerate and decelerate in an uncomfortable fashion. His consequent irritation may be compared with the relaxed state of mind of the driver proceeding at a steady 30 miles an hour at the front of the column. One has only to take a car onto the road, it is objected, to discover the truth of this proposition, and no Einstein is required to detect the basic reason for it. Now this is a subjective impression of the fact that oscillations in speed are amplified towards the rear of a convoy. When all drivers concur in the same belief, the value of this judgment is improved to the point. 133. Where the fact is socially accepted. Something may even be done about it. But it is evident that this belief has to be quantified before there can be any change in road design, since this demands decisions about quantities. Doubtless measurements have been taken to show the magnitude of these effects under different circumstances. But now a new question is reached. When it comes to devising a whole new transport system, consisting of an interacting network of roads, many difficulties arise. The characteristics of every road have to be described in detail, the magnitudes of each, and the arrangements for feeding one into another, whether crossings should be controlled or not, whether such controls should be linked or not, and if so in what way, and so forth. Moreover, these exercises in optimal planning have always to be undertaken, not in the abstract as if they were pieces of geometry, but having regard to the practical limitations of geography and topography, custom and convenience, public service and finance. Those who object to the use of high science in solving problems of this extremely earthy kind, on the ground that they could more effectively be tackled by straightforward engineering techniques, are hoist with their own petard. For, to use their own criterion, they have only to take a car onto the road to observe that the results of precisely this practice are today an expensive failure. The reason is that the straightforward approach, even the straightforward scientific approach, has no real depth. It may succeed in quantifying the situation at a superficial level, and it does recognize some of the mechanisms involved, but somehow it does not manage to account for the underlying nature of the system at large. Now the modeling process as outlined in the previous chapter, and exemplified in this, does provide that depth. Explicitly, the homomorph provides it reveals the deep identity between the problem situation and the model from science to which it is analogous. Given that demonstration of identity, profundity in the understanding of the scientific situation can be imported into the problem situation, where understanding would not otherwise be profound. Moreover, the model is predictive, it can be used to generate information, to facilitate experimentation, and to check hypotheses and potential solutions. It is surely to a whole series of models that the national transport decision takers need to turn, rather than to an even longer series of ad hoc studies leading to large numbers of local improvements. For the series of models may be combined into a complete homomorph of a large transportation system, and the characteristics of its optimal control strategy worked out. This global optimum cannot be expected. 134. To correspond with the aggregate of local optima, the whole is assuredly greater than the sum of its parts. For applications, a formal homomorphic model. Two examples have so far been quoted of the use of models for the solution of operational problems, ancient and modern. In each case it has been shown how the inductive theory based on the nature of homomorphism is useful in accounting for the processes undertaken by the two scientists concerned. It remains to illustrate the operation of this technique in a case where the method was used explicitly, that is to say, the mechanism depicted in Figure 4 was consciously in mind, and the homomorphism was formally constructed. This illustration is taken from my own work reported in Transactions of the University of Illinois Symposium, 1960, published by Pergamon Press under the title Principles of Self-Organization. The problem facing the scientists was this. The management of an industrial company involves its control as an organism within an environment which is sometimes propitious, sometimes hostile, but mostly unfeeling and arbitrary. Typically, a management seeking to exert this control organizes itself into a number of divisions such as production management, financial management, and so on, to which it allots different functions. Thus, to consider the cycle of company operations chronologically, some part of the organization must first of all be responsible for both stimulating and assimilating demand, and channeling it into the works. At this point, the production function assumes responsibility. It must find ways of converting this demand into goods, and of making these goods available for dispatch to the market. Another function is concerned with the purchase of raw materials, and another with all the transportation that is involved. Moreover, there has to be a financial function which supervises the economic activity throughout. This will seek to ensure that all aspects of these operations are financially viable, and will institute accounting procedures by which to verify this fact. In the case under discussion, all these processes were unusually difficult to maintain. The production process was of a highly patterned kind, that is, its profitable operation depended on lengthy runs of production carefully planned into the future. But the demand pattern was totally adventitious. It proved impossible to forecast, even by the use of advanced statistical methods, and its day-to-day fluctuations had a highly damaging effect on the economics of producing the goods. Hence very 135. Large stocks of finished material were held, and even then market shocks penetrated through to the works and interrupted optimal activity. Moreover, raw materials were in very short supply, and were controlled by special and rather unfavorable agreements. The company was not buying in a free market. In almost every other department of its activity, this firm was in special difficulty. The labor position, for example, was by no means easy. The company had been held to ransom more than once by groups of skilled work people. In all these circumstances, which are not recounted here in great detail, orthodox methods of management were proving successful but burdensome. The chief executive was by no means convinced that the best performance was being obtained. A new approach to control was being sought by the use of operational research. The scientific analogy which appeared most apposite was, as already indicated, an ecological one. The company is an organism which must adapt to its environment. It must find ways of adjusting itself to changing conditions. Most living organisms manage to do this, because the environment is to some degree patterned, and the pattern is one which the organism can learn. Violent change is uncommon, and when it is encountered the organism may reel under the impact and become quite unstable and ineffectual for a period, after which it is likely to settle down to the new circumstances. This state of affairs, familiar to the organism, is also familiar to the typical industrial company. As has been explained, however, this particular company was atypical in precisely the ways which make ecological adaptation most difficult. A scientist therefore casts around within his ecological analogy for prototypes of control organizations which are competent to handle such extremely trying circumstances. It seems clear that either of two possible creatures might expect to cope with an environment of this kind. One is an all-purpose, unspecialized creature, a blob of jelly, as it were, which can be tossed about unharmed by environmental storms. But this concept is a negation of an industrial undertaking, which must be in the very nature of things rather highly specialized. This is indeed what makes it so vulnerable. The second kind of creature, then, is one that protects itself by fast reaction, and moreover by perspicacious reaction. Now animal control systems of a purely biochemical kind do not have the required characteristics. One must pass to creatures having highly developed nervous systems. If the entire management process of the company under discussion is conceived of as a brain-like activity, the possibility of a successful outcome is assured. Accordingly, an attempt has to be made. 136. To expound the managerial activity in brain-like terms, to see whether this activity matches the activity already to be found in the company, and to try to develop better mechanisms on the strength of the comparison. And this is exactly what the study set out to do. In this investigation, therefore, the scientific situation to be compared with the managerial situation is that of a brain-directed organism operating in an environment. The conceptual model of this situation is inevitably taken from the science of neurophysiology. Just how valid the use of such a model could possibly be is a question which is vigorously debated among scientists, and particularly by those scientists who, though concerned with the brain, have no stomach for cybernetic formalizations of its nature, structure, or dynamics. Too little, they argue, is known about the brain for such a process as is here envisaged to be remotely possible, and perhaps too much is known for anyone to suppose that an artificial structure such as an industrial company could parallel the wonder of the brain. Such objectors are trapped in an ambivalence which may derive, at the worst, from a fear that science is on the verge of penetrating the mysteries of their own natures. This they resent. Or the ambivalence may derive, at the best, from a profound uneasy sense of inadequacy in themselves and in their techniques to cope with the mysteries of this most complicated of control mechanisms. Let it be made abundantly clear that many of those, and certainly myself, who have ventured into this awesome undertaking share these feelings in large measure, and are certainly neither underrating the task, nor laying an overweening claim to a knowledge they do not possess. We are on the outermost fringe of both comprehension and our own ability to handle the situation as so far comprehended. But, armed with the methodology in which this book is now immersed, we may make a diffident start without falling straight into the traps of which we must all be well aware. Anything that is said in attempting to explore the analogy now set up is, admittedly, a profound simplification. Opponents may suggest that a profound simplification is obviously dangerous, and possibly wicked. Yet we are protected in the task by the highly developed methodology already explained. The object is to construct a homomorphic mapping of the brain, which is by definition a simplification and, by definition again, a simplification of which the limitations are understood. The really pejorative term here would be oversimplification, but that stage is not reached so long as a certain structure is preserved in the homomorph, and so long as we know exactly what that structure is. In the case quoted, a homomorphic model of certain aspects of brain. 137. Function was constructed and used to explore the mechanisms by which the company could possibly respond to environmental change. The formal language employed for this purpose was the mathematical language of set theory, which, as explained earlier, is the very language in which the theory of homomorphism is itself expressed. Using this tool, it proved possible to state the required scientific model from neurophysiology by following exactly, instead of inferentially, the refining processes depicted on the right-hand arm of Figure 4. Simultaneously, the attempt was made to parallel this analysis in the real-life procedures of industry. Experimental control systems were installed inside the company, with the collaboration of the management, to represent the left-hand arm of the methodology laid out in Figure 4. Figure 8 is a schematic diagram of the neurophysiological model. It comprises 4 submodels, marked T, V, U and R. These are respectively homomorphic models, worked out in set theory, of the sensory cortex, the motor cortex, the thalamic level and the reticular formation, each a major area of the brain. The diagram merely indicates how these areas are related to each other in the brain topographically, and shows a coronal section. Obviously none of the detail can be discussed here, the mathematics is extremely involved. But, for the sake of interest, some comments are included about what was surely the first attempt to record the brain rhythms of an industrial company. An electroencephalogram is a record of electrical activity in the brain. Each line is inscribed by a pen activated from an electrode placed on a particular point on the skull. An electroencephalographer studies the rhythms produced from each of a number of different points simultaneously, and succeeds in detecting various forms of mental activity, he may also be able to diagnose an aberrant personality. It will be appreciated that the process of reading off electrical activity at a given point on the skull makes a many-one transformation from the electrical complexities going on beneath the skull in the brain itself. There, hundreds of individual neurons are firing, and thousands of nerve fibers are conveying impulses from one neuron to another. But only one stream of impulses is flowing down the wire to activate the pen recorder. Yet what is inscribed is a homomorphic record. There is certainly a structural difference between the rhythms generated by a sleeping brain and a brain engaged in conscious activity. The pens oscillate much more quickly in the latter case. Moreover, this structure of the rhythm preserves more important features of the very much more complicated structure of neural activity itself. For example, particular rhythm structures clearly indicate 138 epileptic tendencies in the living brain. All this is possible, although the many-one transformation has thrown away all information concerning particular neurons, particular nerve fibers and particular neural impulses. The encephalographer has no idea what precisely is causing the rhythm to oscillate as it does, but he can interpret the oscillations nonetheless. Figure 8. Diagram showing the connectivity of the four submodels comprising a neurophysiological model of the control of an industrial company. Successful management decisions were taken using this model of the company's brain. The parallel situation in an industrial company is clear. A financial expert diagnoses the state of the company from changes in rhythm read from balance sheets and profit and loss accounts. He also has no idea what particular occurrences in the works, what particular activities in the market and so on, have caused these changes. But, as will be argued later in this book, the rhythms he is studying are not generated by truly homomorphic mappings. The many-one transformation is there all. 139. Right, but there are reasons why the all-important structure is not fully preserved. Some of it is preserved, of course, this is what makes his job possible. But the attempt to map every feature of the business onto an unidimensional monetary scale does not succeed, and this is why wrong decisions are sometimes taken. Thus one of the objects of the OR study briefly described here was to construct a valid homomorphic mapping of the company onto a model of the brain. At the least, the order of complexity is right, there is therefore a possibility of preserving the important structure. In exploring the model, then, an electroencephalogram was taken of 10 areas of activity relevant to the company's management. This was not a genuine electroencephalogram, of course, it was an artifact generated by the company through the neurophysiological model. And it was all worked out by hand, we do not yet have machinery capable of doing the job. In short, it was an experiment. Part of the resulting chart is shown at figure 9, which is laid out as a genuine encephalogram. The inset picture of the head would normally indicate where the electrodes were placed. Instead, this inset picture nominates the 10 areas used to generate the rhythms. In reality, these activities have no definite sites inside the company that are topographically related in this way. The point is that we do not know, any more than the electroencephalographer knows, what particular events generate the rhythms. The model processes detailed facts available to the company, throwing away information steadily, and distilling structure. In the interpretation of such results, one does not look for the usual information as to whether outputs or profits are up or down, one looks instead at the relationship between the 10 lines. Some are correlated with each other, some are negatively correlated, some are correlated with a time lag. Above all, these rhythms are related to the major events of the world outside, and the research seeks to discover what bursts of rhythmic activity follow what major events, when, and how. The results of this piece of operational research were, as were called for, the acquirement of insights into optimal ways of controlling the firm as a whole, and the establishment of formal decision-taking procedures for the control of its buying, stock holding, production and marketing policies. The rewards were sufficient for a piece of operational research. Of course, The study could also be conceived as an exercise in the science of cybernetics, an attempt to gain automatic control for the managerial, as well as the physical, activities undertaken by the company. Some advanced automation was indeed installed, and a development plan aimed at the more far-reaching targets of cybernetics. 140. Figure 9. Encephalogram of the company's brain. An actual trace made by an industrial company via the model shown in Figure 8. 141. Certainly emerged. The advent of automatic decision-taking and policy-forming machinery for installation in companies must, however, await further investments. It will come. But these prospects are not of present concern to the argument here put forward, which is concerned with the operational research aspect alone. For this same reason, the model is not offered as a revolutionary technique for the presentation of company information. It was used as a tool for doing a particular job in a particular situation. Now it is a model preserved in aspic. We shall need it again. 142. 8. The formal languages. Un enfant instruit en arithmetic, ayant fait une addition suivant ses règles, se peut assurer d'avoir trouvé, tout la somme chu il examinate, tout ce que l'esprit humain saurait trouver. A child instructed in arithmetic, who has made an addition according to the rules, can feel quite sure that as far as that sum goes she has found out everything that it lies within the human genius to discover. René Descartes in Discours de la Méthode. 1. The formal language of quantity. The importance of languages has been canvassed insistently in this book, and a distinction has been drawn between social languages and formal languages. Having analyzed the inductive processes of operational research, and having discussed the nature of its models at some length, we should now consider the formal languages in which the scientific model is expressed. It is not one of our purposes to investigate the technical details of scientific techniques, still less to purvey a mastery over them. But it is a primary object to explain the meaning of these techniques, and if possible to distill their essence. As a means to this end, it should help to discuss how that which is done can conceivably be done. For there is a no man's land between the mere declaration that science is competent to express a conceptual model in rigorous terms, and a full-scale exposition of what those terms actually are. Each of these tasks has been adequately tackled elsewhere, it seems. 143. Clear that a managerial insight into the situation must lie somewhere between the two. Accordingly, we select the first of the formal languages used by scientists, namely mathematics, and try to answer the question why it is that this language is so important, and what special advantages it offers in the treatment of managerial problems which after all have nothing to do with algebra. In the first place, someone who is not himself accustomed to use formal languages probably suffers from a thought block in their regard. Mathematics, for example, may be to him a grim and intractable subject because he was not very happy with it at school. Moreover, it is clearly a dry way of discussing real-life affairs, so dry indeed that it cannot possibly cope with all the richness and color of the world. Therefore mathematics is suitable for calculating numbers that managers want to know, and has no other relevance for them. Although this conclusion does not follow from the premise, there is of course a good point here. The mathematician trades in a good deal of the sensual delight of empirical scientific inquiry, and for what? Clearly the main answer is that his delight resides in intellectual satisfactions. The mathematician is respected for this, people feel that he lives on a higher plane, but they do not really understand. Perhaps a clue can be obtained from Descartes, whose words head this chapter. The point is that a formal language is a deductive machine, it investigates itself, rather than the sensual world. Given a set of formal propositions, the mathematician investigates what they entail. He makes his work useful in society by matching his initial propositions to the world, so that what they entail is directly translatable into worldly consequences. What Descartes says is that the kernel of this process is a self-consistent, self-justifying business, it leaves no more to be said. The point to be taken for operational research is that formal manipulations inside the scientific model are assuredly the kernel of or, but for the very reason that they are self-justifying, this kernel must be properly embedded in its surrounding model. Hence models take pride of place over the formal languages used to make them rigorous. For a good homomorphic model that is less than rigorously expressed may be very useful, but a rigorous demonstration that derives from a poor model, improperly mapped from the problem situation, is highly dangerous and may be irrelevant. Mathematics then is an abstract way of talking about quantities. This is not the naive statement that it seems. There are mathematicians who would contend that it is naive, that mathematics in fact deals with something more than quantities, namely logical relationships. But although 144. That allegation is a more penetrating comment than the statement that mathematics is a kind of arithmetic in fancy dress, it is still not penetrating enough. If one goes into the philosophy of mathematics, it becomes clear that the relationships with which mathematics deals are basically quantitative, they derive from the nature of space and time. But the fact that the quantities involved are abstract is the really important point. Everyone who did school algebra knows that a 2b2 equals, and finds this interesting because it is a generalization. He does not demand to know what are the numbers of which this equation speaks, so that he may store them in his memory against the possibility of meeting them in practice. He prefers to store the basic pattern of the quantitative relationship, so that he may apply it to any set of numbers that he may encounter. This argument may be extended to the handling of managerial problems. Mostly people behave as if each decision with which they are faced is unique. Strictly, it has to be conceded that, since we live in a world of flux, no decision is absolutely and entirely repeatable. But the pattern of decision-taking may well be repeatable. That is to say, it is possible to set down equations which adequately represent a wide variety of managerial situations. This being the case, it is possible to substitute actual numbers from a given unique decision-taking problem for the letters which stand in the equation, and to obtain a unique answer for a particular occasion. The advantages are twofold. In the first place, a decision which may appear to a manager to be qualitative, because he is hemmed in by the psychological exigencies of the moment, may now be instantly recognizable as belonging to a certain pattern of decision which can be quantified. In the second place, and reverting again to figure 4, the same basic pattern may well underlie a host of apparently dissimilar managerial situations, therefore the amount of scientific effort which must be put into the task of modeling this pattern of decision is spread over many instances and becomes only trivially expensive. A point well worth adding on this score is that once a procedure has been discovered for solving a particular set of mathematical equations, a particular problem can not only be recognized and set up in rigorous terms quickly and cheaply, it can be solved quickly and cheaply too. Often, for example, the procedure may be embodied in a computer program, so that the particular solution may be obtained for no more effort than that required to feed this program from the library into the machine, together with the accompanying data that relate to this occasion. It is worth trying to illustrate this point, if only briefly, and in 145. Context. The example concerns a production shop containing a large number of machines, each of which can manufacture a range of items. Clearly, each machine can also operate at an intense or less intense level of activity. Into the department flow raw materials, which are converted by the machines into products, which then flow out of the department. Associated with all these activities are, naturally, costs. It is basically the problem of the production manager to decide how to fix all these variables to produce the highest profit within a given period. This statement of the situation does not of course reveal all the ins and outs of any particular example, but the general picture is surely sufficiently familiar. It is also too familiar to find that this problem is resolved on the basis of knowledge and experience alone. Probably no one man declares what the total answer is, rather, there is a group of men who plan the operation between them. They have a feel for the situation, by which is meant that they tend to recognize combinations of activities which are advantageous and others which are disadvantageous, and they piece together a total plan of campaign which takes account of these intuitions. Normally, this group of people will not conceive that the answer to the problem is even in principle computable. On the contrary, experience tells them that it is a matter for negotiation between themselves, a negotiation in which each of the men concerned exercises his judgment. This belief comes about because no one man has a brain sufficiently large or sufficiently competent to undertake the computation that would be involved, therefore it is alleged that the answer is strictly non-computable. But suppose that by this point we are agreed that, given the facts, an answer is in principle computable. How should we then set out a statement of what has to be computed? Any attempt to do this in ordinary English will be most difficult. It will place a considerable strain on the comprehension and the concentration of anyone who tries to formulate it or to read it. Let us undertake a practical experiment on this point. What follows is a purely verbal statement. Each machine has a definite average rate of production for each item at each level of activity. If we fix the item and the level of activity for each machine, we can see how many more or how many less units of production will come out of the shop as a whole in a given time, compared with some standard number. In order to procure such an adjustment to standard output, it would of course be necessary to add raw materials to, or subtract raw materials from, the standard set of raw materials going into the shop in the time 146. Period immediately preceding the one over which the output was measured. This consideration of a possible arrangement of work different from the standard arrangement of work might be more or less profitable than the standard profitability. In order to find out what is the most profitable arrangement, it will be necessary to consider in turn the manufacture of every item which that machine can make on each of the machines at the lowest level of activity. Next we shall have to consider that whole permutation all over again at a slightly higher level of activity, and so on, until the maximum level of activity is reached. But then of course it would be possible to mix the effects, and to consider combining this item on that machine at a certain level of activity with some other item on some other machine at another level of activity and so on. It might seem indefinitely. But take comfort, the number of possibilities is not actually indefinite, an end will be reached. Of course the number will be exceedingly large. Even so, all that is apparently necessary is to have the accountants cost each of this large number of possible arrangements, and then to choose the one that offers the highest profit. In practice, this cannot be done. An elementary mathematical argument is now used to quantify the basic problem to show just what its magnitude is, and therefore why the accounting exercise cannot be done. Consider the simplest aspect, and it is only an aspect, of this problem. There are n processes. Incoming material may be routed onto any number r of these n processes in any order, and the product may be sold at any stage. Admittedly, there will normally be side conditions to be met which make this problem as stated a little more fluid than one normally finds it, but think of a machine shop. In any case, this factor is compensated by making the shop in the example absurdly small. Suppose it has only 10 machines in it. How many different routing possibilities are there? How many ways of allocating work to these 10 machines? If anyone should wish to work this out, here is the way to do it. And in case anyone does not follow this expression, or does not want to bother with it, the answer is over 10 million. It is small wonder that most people have not yet realized that uniquely best arrangements can in fact be selected in circumstances of this kind, even for shops which are not ideal, which have a very much larger number than 10 of non-interchangeable machines, and which in adding 147 should have to cope with thousands of different items and many different levels of activity. But surely the point has been demonstrated that the production planning man can hardly be expected to do the optimal job, and also that the mere task of stating what the problem is may produce a headache. Then let us just glance, without any detailed explanation, at a mathematical formulation of the original generalized problem. There is no algebra to be understood here. The object is to give a practical demonstration of the power of formal languages to be precise, and to condense long-winded verbal statements. We are concerned with times, which are numbered consecutively 0, 1, 2, 3, 4, and so on. Typically, the time is t, and the time before it t1, so the gap between them prescribes a basic interval, typically the tth interval. There is a range of activities which could occur in this interval, and a range of items which could be manufactured too. These could all be nominated by a string of consecutive numbers as well, but typically there is a jth activity and an ith item. Now if an increment is defined as an addition to the cumulative flow function through the works, it must relate to a certain time interval, and it may pair off any item with any activity. The whole range of such possibilities is written similarly. A decrement is defined as subtracting from the cumulative flow, its particulars are specified in the same way. The first is an input coefficient, occurring at the end of the interval. The unknown, x, which must be calculated is in this case the number of units of each item that must be produced by each activity. The following expression accounts precisely for the equilibrial condition of the dynamic system described above. Here the summation sign S shows how the system of equations entailed by this expression ranges over all possible activities in the shop. And system of equations is the correct term, for it would take many pages to write out the entire piece of algebra prescribed by this one expression. If we may revert briefly to the vocabulary introduced much earlier in this book for other purposes, this expression defines a particular mathematical space, namely a space which has the shape of the situation under discussion. But it does not yet define the phase space of the problem. It is still of complete generality, and would permit answers to be given to the manager which invited him to manufacture a negative number of items on certain machines. And so the phase space 148 must be carved off this total space, not by the device which was uncovered in human psychology, that of erecting thought blocks, but by stating the limiting or boundary conditions which obtain. Thus the equations must hold for every item, and for every time, there must be a positive activity, there cannot be an implied decrement before the first moment of time considered. The search starts from that moment with the possibility that one item of something is produced, and a negative number of any item cannot be produced. So the equation has to be solved subject to these conditions, written respectively. In practice, moreover, the range of possible solutions will be limited by more factors than these logical ones. For example, there will be items which cannot be made at all on certain machines, and items which cannot be effectively produced at certain levels of activity. There may be minimal quantities of certain items that have to be made to accord with outstanding commercial agreements, and there may be items which we do not intend to produce at all this month because no one will buy them. In fact, all these limitations can be added to the list of logical constraints already given in similarly mathematical form. And here is an interesting comparison. When a human planner is given a long list of constraints of such a kind, he is prone to tear his hair because his mind cannot assimilate all the ifs and buts. Scientifically, on the other hand, the more of these constraints that can be added the better, for they delimit and reduce the phase space which has to be searched in order to find the answer. It is now clear that all possible answers to our question lie within the boundaries now fixed, and that one could prescribe the rules which would enable all these answers to be generated and listed from the basic equation. But of course nobody wants all these answers, although they will all be feasible solutions to the management problem. Only one answer is required, that is, the most profitable arrangement of the lot. Therefore another equation is required, which will state quite precisely how to recognize this unique answer. To obtain this other equation, a measure of the profitability of every combination is required. If is the cost per unit produced of the JTH activity, then it's 149. Negative, L, is a measure of the profit. Hence the profit, P, for the JTH activity is Lj, Xj, and the total profit P for the totality of activities sums them all thus. Now time must be considered. Another summing term has to be included to cover the range of times. And the resulting expression has to give the maximum profit. Hence, The rule for finding the solution is now this: search the whole phase space for an answer which conforms to both equations at once. This is the best production program. These equations are typical of those devised to express this kind of problem rigorously. The credit for devising a rigorous set of rules for searching the phase space and recognizing the right answer belongs to an American, Dr. George B. Dantzig. All this work was published as early as 1949. By now there is a large number of variants of this approach, collectively known as linear programming techniques. There are also variants of the original set of rules for finding the answer. Dantzig's own algorithm is called the simplex method. It ought by this date to be possible to remark that every competent industrial management uses this method for analyzing its production problems, but it is not. And please let no one counter with the argument that his own production problem is not of this kind, for of course the illustration given is only an example of a whole family of patterns which could be used. Yet this presumably is just one of the thought blocks which have been erected to curtail the application of this immensely powerful approach. Because the plain fact is that most industrialists have never even tried it. Moreover, the results can be so startling that they fall foul of every one of the stereotypes of managerial thinking discussed in Chapter 4. On the first attempt of my own to use this approach, a potential increase in the profitability of a small but very complicated works was disclosed of the order of 500%. This at once set up in the management a whole row of wedged bears, transfixed in every possible attitude. It was an education. We set out to exemplify the use of the rigorous language of mathematics in an operational research problem, in order to show how 150 complicated verbal arguments can be succinctly expressed when an appropriate language is used, and to explain how decision problems which may appear to many to be qualitative can in fact be quantified. But there was a second point at issue. This was to demonstrate how a particular mathematical pattern informing a scientific model may underlie a variety of problems which appear dissimilar. This mathematical model is in fact a formalization of a conceptual model drawn from an understanding of the nature of equilibrial systems. At the conceptual level, the model is not very rich. This is why many people concerned with linear programming regard it simply as a process of applied mathematics. Or they may call it applied economics, for it can be looked on as an extension of the famous input-output econometric models of Leontief. What then is the point of calling it operational research, or alternatively what is the point of insisting that the business of operational research begins in this case with a scientific analogy founded in a conceptual model? The answer is simple. It is just because the conceptual model is not very rich that this technique is not as widely used as it should be. In our nomenclature, the mapping from real life is not strongly homomorphic. For there will be a variety of managerial considerations which were not included in the story as earlier set down. For example, the theory procures a statement of the optimal mix of which the production program should be compounded, but it tells nothing of what should be done if for some practical reason the manager is compelled to depart from the optimum. It simply is not true to say that his best course in these circumstances is to adhere as closely to the optimal mix as he can. Ideally, a new computation should be made, and if the situation is sufficiently fluid this may simply be impracticable. Again, even when the marketing constraints have been taken account of, and the phase space of the problem duly reduced, the very existence of a unique answer to the problem may itself offend against a hitherto unexpressed constraint. To quote an actual case, the optimal mix, not of machine loads but of actual products, had been computed by linear programming in order to maximize machine utilization. The solution had the mark of a valuable or result, namely the payoff from the study showed an increase in profit of 700%. And yet the solution could not be implemented, for the solution gave with exactitude the precise amounts of each product which would have to be made and sold. The commercial manager objected that, although the answer lay within the range of possibility which he himself had laid down, it would in terms of practical marketing prove impossible to sell precisely this balance of output. To come near to 151. The result, it is emphasized again, is not necessarily the best policy if the target cannot be exactly hit. That is to say, then, that the solution in this example was not very robust. The reason for all this was that adequate account had not been taken of the environmental facts of the market. Moreover, the prospect of uncoupling production from the market by the use of a properly organized and controlled stock holding system for finished goods, which would have resolved the difficulty, had not been investigated. The reason for this in turn was a serious commercial thought block: it is not our policy to manufacture for stock. This fact was well known to everyone concerned, and in the event it proved impossible to question it, although it most certainly should have been questioned. Thus it comes about that a perfectly satisfactory piece of applied mathematics, entitled linear programming, was not on this occasion a satisfactory treatment of a managerial problem. In other words, it was defective operational research. And the trouble lay in the failure to formulate a good model. When the matter is studied properly, and a genuine conceptual model of the real-life situation is formulated first, the actual technique of linear programming may prove invaluable in solving the computational problem which the model generates. There is a wealth of difference between trying to do a linear program on a situation such as this, and finding that in order to calculate a particular answer within the framework of the neurophysiological model mentioned in the last section, or of a systems model that accounts for the company-market interaction, the technique of linear programming is indispensable. This story illustrates the difference in approach between the applied mathematician and the man, and it is not invented, rather too many instances have been observed in actual industrial work. But, given a sound methodological framework as a setting, the technique of linear programming is invaluable. The technique was brought forward here in answer to a particular problem concerning the loading of a production shop. But it should by now be clear from the analysis of the problem that has been given, that the mathematical model generalizes. It can handle any equilibrial system of inputs and outputs, in which the allocation of resources to outcomes is permittable under certain constraints, and for which there is a unique criterion of success. Hence the management of a warehouse can be controlled by the use of exactly this model. Such a warehouse maintains an equilibrium between the goods delivered to it and the goods issued from it. For each class of goods there is a rate of turnover which can be accelerated or 152. Decelerated within limits by various devices. The factor that might create the major managerial problem in this case is the price differential from season to season. What is the optimal mix of products, both the cost and the price of which vary from time to time with a seasonal lag between the two? The model is the same and the technique is the same as the one already discussed. Again, if the problem is to transport goods from an alternative number of origins to an alternative number of destinations at differential rates of transportation charge, the underlying pattern of the decision to be taken is at once recognizable. Again, both the model and the technique are identical. In fact, this technique has been used widely and most lucratively in the coal industry, the electricity industry and the oil industry to solve this very problem. How, for instance, should crude oil from a number of oil fields be transported to a number of refineries to minimize the cost? One British oil company claims to have saved £1 million a year by the use of this method. And yet the success of such applications may confuse both the managerial and the operational research issues. They seem straightforward. The reason is that the model of such a transportation situation is indeed very straightforward: a simple network linking origins to destinations, plus information about the availability and cost of the requisite shipping. Thus the limelight does not fall on the model, but on the technique. When it comes to transposing the problem from a given set of ports and a given set of refineries to a retail distribution network, the problem is more difficult. There are many destinations, and many routes to them. There is a variable number of possible warehouses, cited in an infinite number of possible situations. Indeed, the problem may be to find the optimal sites. The model is now all important. The technique of linear programming is worthless until a homomorphic mapping of this retailing world is found. 2. The formal language of probability. Mathematics, the rigorous language of quantity, provides the operational research scientist with a generalized way of talking about the measurement of his conceptual models in formal terms. In reaching the quantified answer to a particular problem, however, he has to substitute numbers for the letters that stand in the mathematical equations. What are these numbers, and where do they come from? Certainly, each of them is a measurement of some kind. People behave for the most part as if a number, having been measured, must certainly be right. In fact, reflection will show that this claim cannot often be made, and that the CIR 153 circumstances in which it can be made are extremely difficult to define. We can exemplify the possibility. To say that there are 3 people in the room is to utter what is probably an incontrovertible statement. To enumerate the number of people milling about in a cocktail party, however, is not so easy. One would hardly take offense if told that one's count was in fact mistaken by 1 or 2. Many of the counts made in industry for managerial purposes, it must be conceded, are probably not exactly right. Moreover, the measurements used by managers for taking decisions are not often straightforward enumerations, they are more likely to measure some kind of average. Thirdly, they may not even pretend to be legitimate average-sunly estimates of averages. So a particular measurement may turn out to be simply one of a number of estimates we might have obtained. A different answer would be right had we taken a few more instances, or done the measuring on another day. In fact, the comforting solidity of the digits neatly listed in front of the manager collapses under scrutiny. There are many kinds of uncertainty attached to each number, and there is no need for present purposes to identify them all. It is sufficient to recognize that the real truth is something we never apprehend, it is always lurking elusively behind the measurements we are able to take. All this adds up to one simple assertion: the quantifiers of real-life situations are variable. Since the special circumstances which generate a number are never exactly repeated, never exhaustively enumerated, and never precisely measured, we are not entitled to regard that number as a sharp point on a scale. It is unfortunately clear that some people do regard managerial data in this fallacious way. They were first educated in a universe of numbers with hard edges, things to be counted, concrete, discrete. It contained 6s that were by no means 5s or 7s, those who said the 6s were 5s or 7s were told that their answers were wrong. They grew up in this same universe of hard numbers, they knew that a balance had to be struck each night at the bank, and that everyone would be late home if a halfpenny were missing. All this promotes an outlook that is projected into management. A great industrial company will quote the capital tied up in stocks with the same precision. I have seen those big beautiful numbers myself, 8 digits long, given to the nearest pound. Yet the numbers of items in each stockpile have been estimated, multiplied by an estimated average weight per item, and multiplied again by the estimated average value per unit of weight. The company will be lucky if its stocks are evaluated correctly to the second. 154. Of those 8 digits. Per contra, managers do not call for the numerical penetration of quantity when they really do need it. For example, they may reject one process or product in favor of another when the difference between the two, though small, is clearly present on the average. Figure 10. The contour map of probability. Associated with the measurement scale at the bottom of the illustration are the zones of likelihood surrounding an estimate of a particular measure. The true figure is most likely to be found in the center, the chances of finding it further out drop steadily. The contours join points of equal likelihood, and the numbers ascribed to them indicate the relative frequency with which the true figure will lie as far out as the circle shown. But if the variability of each set of data around its average number is relatively great compared with the small difference between the two average numbers, the decision may be invalid. The difference on which it is based is not statistically significant. Some managers reach this understanding by intuition, but even then they may fail to observe that the significance of this same difference, set within the same framework of variability, changes with the number of items considered. How often does one see tabulations of averages intended for comparison, which 155 have been computed from sets of data containing wildly different numbers of instances, yet there is no mention on the tabulation of what these sample sizes are. But this is not a dissertation on the proper use of figures. There is another point to be made. Thoughtful managers may well be aware of these difficulties, and resolve to be cautious in making decisions which depend on the precision of the data before them. That is one thing. But it is another thing altogether to use these insights to create a new approach to the problem of measurement, and to the use in decision-taking of the numbers that measurement generates. Figure 10 is a novel picture of a numerical scale, spread comfortably over two dimensions in order to make the point clear. This diagram looks like a contour map. The concentric rings represent zones of likelihood which display information as to where the number sought probably lies. The shading indicates that the most likely position is in the bull, and that the least likely place in which to find this number is on the periphery. This picture faithfully represents the account of measured quantity given above, and may be instantly recognizable as a fair description of the manager's own feeling about the matter. After all, if he were trying to shoot at this target with a .22 rifle, he would mostly score bulls. There would be a rather high score of inners. Very occasionally he might jerk instead of squeezing the trigger, so a few of his shots would fall on the periphery. And so he would say that any one shot would most probably hit the bull, or that the chance of scoring an outer has a low probability. It is in just this way that concepts of probability derive from concepts of variability. The link is the notion of frequency. But if this diagram looks like a contour map, we may proceed to treat it as one. A cross-sectional projection of a piece of terrain can be obtained by drawing a line, which positions the cross-section, across the contour map, and by scaling out the profile of the ground underneath. This is done for the contour map of variability in Figure 11. It can be seen that the most probable location of the required number on an ordinary scale of measurement is now represented as being at the top of the hill. From there, the curve slopes away on either side. What does the vertical scale represent? Supposing that the number sought is an estimate of the average value of some variable, then the vertical scale represents the frequency with which the value indicated on the horizontal scale will appear. Obviously, in these circumstances, the average value is also the most typical value, which is to say the value most often encountered. Values close to this average on either side will appear with a lower, but still relatively high, frequency. As we move further and 156. Figure 11. Projection of the contour map of probability onto an appropriate scale of measurement. This hill is a probability distribution. NB, the proportion of the shaded area to the whole area under the curve, measures the chance of exceeding the value 10. Further away from the mean, the values are less and less frequently encountered. The picture obtained is, nowadays, familiar to many managers. It is in fact a picture of a probability distribution. It is certain that the number required lies somewhere under this curve. This is guaranteed by the fact that the two tails never quite reach a zero frequency of occurrence. They spread out infinitely on either side. This means to say there is always a finite chance, however low, of encountering a ridiculously atypical value, however freakish. Now if the number sought certainly lies under this curve, the probability that it does so is unity. Then it is possible to measure the probability that the number sought is actually greater than any given number. For example, it may be important to the decision taker to know that on the average the value with which he is dealing is 7.5, but it may be even more important to know in this case what the chances are that on any particular occasion the value will turn out to be 10 or greater. So we cut off the right-hand tail of this distribution at the value 10, and compare the area under the curve to the right of this division with the area of the whole. It is transparently clear that the ratio of these two areas measures the chance that any random occurrence of this event will have a value greater than 10. If this curve is, as was alleged, so familiar nowadays, it may be thought impertinent to have engaged in this lengthy account of its nature. Forgiveness is sought as appropriate. In consulting with managers, however, it has been noticed that a use of distributions does not always guarantee an understanding of the nature of variability, nor of the way in which this in turn entails the concept of probability. The next object is to dispose of a clear-cut misunderstanding, which is this. Some people would say, on the one hand measurements may be taken to produce data which are correct, on the other hand some of the things we would like to measure keep recurring with slightly different values, so not one number but a spread of numbers must be considered. This is an incorrect, dislocated visualization of the matter. A better account would say that nature is mutable, every facet of the real world is quantified, but the attempt to label each variable with a unique number is incompetent and can only lead to misapprehensions. For one thing, what is measured may change, for another, our sample may be inadequate, for another, our measuring apparatus will not be perfect. Most of the things we wish to measure may, for a large variety of different reasons, assume from time to time one of a range of possible values. In this case it is important to nominate that range, and to quantify each value within it by the probability of that value's occurrence. Fortunately, it is not necessary to undertake fundamental research into the precise shape of this contour map and its associated topography in every instance of industrial measurement. Mathematical statistics has developed a codified way of describing the kinds of probability distributions which are most frequently encountered. The mathematical characteristics are known also. This means that we can readily write down 158 probabilistic statements about chance and risk in a rigorous form. For example, it was said just now that the chance of a random values exceeding 10 for the case depicted in figure 7 would be given by calculating the proportion of the tail greater than 10 to the whole area under the curve. This can be done if a way can be found rigorously to compute the area enclosed in the tail. The expression to be evaluated is: when the number given by this equation has been calculated, the proportion it bears to unity is the probability of a randomly selected sample from this distribution having a value greater than 10. This presentation illustrates incidentally how science should be put forward to the manager. The principle is easy to understand. The theory is necessarily complicated and difficult to understand, as that equation shows. Yet the calculation is easy again, because one can have a whole range of values tabulated for an expression of this kind. The manager, then, should be enabled to examine the bases and to obtain the outcomes of science with ease. And he should be given the hard science in between for the record, and perhaps for verification by other specialists. In a report such equations, and other formalizations such as are scattered through this chapter, would be found in technical appendices. Now this particular curve, for which the integral has just been quoted, is the Gaussian or normal curve. It is encountered a great deal in nature, and in industrial and commercial activities too, for these after all are part of nature. But there are other varieties of curve, of equal importance to the Gaussian, with which any good introductory textbook on statistics will acquaint the reader. Suffice it to say, for present purposes, that many probability distributions are not symmetrical and would not be expected to be so. For example, the distribution of the probability of making defective items in a plant will have its peak well to the left of center. The object is, after all, to make zero defectives. Moreover, one cannot possibly make fewer defectives than that. Consequently, there is an expectation that the distribution will start on the left with a high probability of making zero defectives, a somewhat higher probability of making a few, followed by the usual tailing away to the right as the number of defectives increases and the probability of making that number decreases. Mathematics is used in operational research because it knows how to handle the number of things, or it may suppress this raw number, and coalesce the things into groups, going 159 on to discuss their number. It knows how to relate these numbers and discuss their modes and rates of change. The subtlety of the subject does of course enable the scientist to undertake the investigation of such things without knowing what the numbers actually are. Algebras permit us to discuss them as generalities, and to solve a management problem subsequently by associating with those generalizations actual numbers, which are business and industrial data, at the moment when managers wish to know what the numerical answer really is. The building block of the mathematical language is really X, and the kind of problem discussed in the last section may be resolved because X is the number of machines, or X is the profit in March, or X is the number of refineries to which oil must be shipped. But the building block of statistics is a distributed X. This is not just a number, but a range of numbers to which various levels of probability are ascribed. Armed with this concept, operational research is enabled to discuss those things that are clearly quantified, but to which no actual number can, equally clearly, be firmly attributed. For the manufacturer of a machine to quote a delivery promise, for instance, it will be necessary to know how long it will take to obtain all the components and to put them together. We want a collection of numbers, but what these numbers are will not be known until the machine has been dispatched. To do the planning, unfortunately, the numbers are required now. Eventually, when it is much too late, we shall know that one of these numbers, for example, is 17. At this moment, however, we may know that the most likely value of this number is 15. It would clearly be unwise to use this number and hope for the best in the event the prediction will be falsified. But if we compute with probabilities, if the calculation ranges experimentally over all the values which this X could take, from the very lowest to the very highest value, computing in passing the probability of encountering each of the values between them, then obviously a better insight into the forecast will be obtainable. It will prove possible to obtain the limits within which the final answer is likely to range, and also to state the probabilities of missing the target date by any given time. This at once reveals the extent of the liability for missing the target date which the management can afford to accept. It shows, when a number of forecasts for order deliveries are amalgamated into a production program, how much slack ought to be allowed to encompass the risk that individual target dates will not be met. It shows, in a word, what the vulnerability of the production policy is. 160. The division of the quantitative aspects of a managerial decision or policy into determinate and probabilistic elements is important, but not often undertaken by managers. They seem to regard the situation with which they are dealing as predictable in principle, but likely to go wrong. But if the whole situation is properly analyzed, a clear picture is obtained of which elements are, or can be, determined, and which elements are susceptible to chance and in precisely what way, then the interaction between these two can be computed. The theory of probability, which is central to this undertaking, is a full-scale subject in its own right. All competent or men know something about it, all competent or groups contain mathematical statisticians. But it is not an easy subject and there is no space here to go much further with the exposition. For, despite the existence of a vast range of mathematical statistical techniques, dilemmas still exist at the level of philosophy of science. No secret can be made of the fact that eminent statisticians disagree about the fundamental nature of probability and how to compute it. Nonetheless, science has a great deal to offer the decision taker in considering the impact of chance and risk. For the plain fact is that the man who has not studied these matters, but who works on an intuitive notion of what is likely, will often mislead himself quite wildly. There are, it may be suspected, biological reasons why this is so. The manager is not pure intellect, he is a living organism, and his basic impressions about chance and risk are derived inevitably from his need to survive as an animal. These impressions are not necessarily at all relevant to his profession as decision taker. For example, to take a straightforward situation, there are 23 people sitting in a room. What are the chances that 2 of them have the same birthday? Most people feel that this probability is exceedingly low. 1 in a million, people say, or there is not a cat in hell's chance. In fact, the chances are better than evens. That is to say, if you made a bet that 2 people in the room had the same birthday whenever you saw 23 people gathered together, you would make a profit in the long run. If 90 people are present, the probability is not 1 in 4, but virtual certainty. Even scientists familiar with probability calculations were surprised when Professor William Feller produced this example. And so it behoves the manager to base his decisions on quantified assessments of outcomes, which are compounded of determinate and probabilistic estimates. Tools are available for handling each of these component factors. Mathematics is competent to build great edifices of 161 quantities, showing the connectivity between aspects of the situation. Statistics is competent to enrich this architecture with its calculations about chance and risk. Certainly the manager can employ a mathematician or a statistician, and ask them to investigate a particular situation using these tools. But because of the arguments which have been advanced at considerable length in this book, these men may fail to understand the nature of the situation with which they are dealing, the fundamental character of the system which causes it to behave as it does. It is better to tackle the matter through operational research. The balanced, interdisciplinary or team will examine that situation and that system, create a conceptual model of it by the use of scientific insights, and will then set about the task of constructing a rigorous model by the use of those same tools which have been described in this and the foregoing section. In short, what was said of the use of mathematics in OR applies also to the use of statistics in OR. This section is, after all, about a formal language which is, strictly speaking, a sub-language of mathematics itself. No wonder the same considerations apply. There are two reasons for discussing it separately, nonetheless. First, by no means all mathematicians are fully competent in statistics, a fact which should be known and borne in mind by both OR leaders and the managers they serve. Second, the topic with which mathematical statistics grapples is that of probability, a topic of peculiar importance to managers. This is because it underlies every one of his problems. If this were not so, the problem factors and their magnitudes would be known with certitude, the answer would be definite and incontrovertible, and there would not exist a problem any longer. Managers are needed because their zone of responsibility is subjected to chance and risk. In modeling such a situation, the fact of variability must invoke the concept of probability. Statistics is the formal language for quantifying that concept with rigor. 3. The formal language of quality. The appropriateness of discussing mathematics and statistics before turning to logic is dictated by a quirk in the syllabus under which scientists are trained. Few of them get round to a study of formal logic. From a more objective point of view, however, it would be proper to start with this subject. It offers a rigorous way of discussing the structural relationships of a language and therefore of the realities which may be mapped onto that language. It seems reasonable to say that this qualitative application of rigor is methodologically prior to the rigorous. 162. Treatment of quantity in the arithmetic sense. Logic indeed sets the stage for measurement, with its own special way of handling quantity through the distinction it draws between general and restricted cases, the all and the some known as universal and particular quantifiers. What counts as a coherent statement, what implies it and what it entails, whether an argument or demonstration compounded from such statements is valid and can support the conclusions it purports to maintain, these are all questions of logic. It is surely absurd to discuss the quantification by number of these statements and arguments unless they are themselves first recognized as competent. But, although the whole of life demands a minimal competence in the handling of such matters, few scientists go so far as to acquire a command of the formal techniques which sustain them. In fact, the subject of formal logic is an art subject. Pedagogically, this strikes someone who is not a pedagogue as an aberration. From the point of view of operational research, there is a crying need to include a trained logician in the interdisciplinary team. The role of formal logic in helping to supply the rigorous statement of a scientific model will be exemplified from two cases, one military and one industrial, previously unpublished. Again, an opportunity will be made to show that there may well be an underlying formal identity between two utterly different problem situations. The military situation is this. There is no war, but there does exist a complicated and dangerous political situation beset with the risk of uprisings on the part of various interested parties. A strange assortment of military and quasi-military detachments is responsible for law and order. They come under various different authorities. There is doubt about the loyalty of some of them. The efficiency and reliability of these forces covers the whole gamut from crack troops, to organized rabble. Some of the detachments, although nominally accountable to the center, are legally autonomous, and may do unexpected things. Communications are precarious, whole areas are sometimes cut off for days. The situation deserves the adjective Gilbertian. The orthodox military model used to study a situation such as this is, of course, a map, an ordinary, geographical, map. Locations are marked, and many conventions depict the state of affairs. Although one must confess that this is a homomorphic mapping of the terrain, the model is not homomorphic with the operational facts. The main reason is that the distances indicated are measured 163 uniformly against a rigid grid. But what is interesting to a commander about such distances is not their absolute length. He wants to know how long it will take for a given detachment to move and to provide cover for a new area. This depends on a variety of probabilistic factors, as well as the determinate distance between the present and the intended sites and the determinate nature and size of the detachment. For example, its speed of advance has a range which is weighted by a probability distribution. There is a finite probability that the detachment will simply not get there, and it matters very much what hostility, if any, is encountered on the way. The orthodox model, which can itself be manipulated by mathematical techniques, had therefore to be redeveloped to meet operational needs. A probabilistic model was superimposed on the topographical model and its invariant quantities. This attributed statistical numbers to the terrain, it loaded all the determinate factors with measures of chance and risk. This effectively compressed and stretched the orthodox map, as if it had been printed on a sheet of elastic material. Using this more sophisticated model, it became possible to define a new sort of measure, that of coverage, a rather complicated statistic expressing the ability of a particular detachment in a particular place to give cover to some other nominated area. The use of this concept meant that a maximum time had to be fixed within which the forces of law and order had to arrive at a potential trouble spot. It also meant fixing an acceptable probability that the arrival occur within this time, for, once probabilities are invoked, there is always a finite chance that the detachment will not arrive in time, however long the delay that is allowed. The distance reached for the probability fixed was called in this work the threshold of coverage. When any military activity of any sort occurred, it at once became impossible to know for certain what was actually happening because of the feeble communications. It was therefore necessary to amass such information as was available, to assess this within the framework of the coverage model, and to infer such consequences as one could. Here is an example, based on an actual incident, to show what is meant. There has been some kind of trouble, but no detachment, in town B8. 5 detachments were originally within threshold cover of town B8, which they encircled. According to the plan, one or more 164 of these detachments should by now have entered the town. Communications with headquarters from this operational zone have broken down, but it is assumed that the 5 detachments can communicate with each other if only by messenger. Their instructions are clear. A detachment asked to move on request from the authorities of such a town as B8, must do so if, and only if, its present location is within threshold cover of an adjacent detachment. It follows that, if all detachments that have gone to town B8 have threshold cover from an adjacent detachment for the zone previously under surveillance, then some detachments have not gone to town B8. Now if any one detachment has wrongly moved towards town B8 without threshold cover for its zone, the situation must have been remedied. For the rules provide for this situation by stating that adjacent detachments will continually check on their threshold coverage. It follows that the detachment adjacent to the defaulter will discover its default, and will then move in closer to the center of the ring and close the gap, or it will call on the adjacent detachment in the network behind it to help provide new coverage facilities. Unfortunately, experience has already indicated a flaw in this plan. If the authorities in a town such as B8 send out a general alarm, then all the detachments near to it on each side may begin to converge on the town. This produces chaos, because each detachment is relying on its adjacent detachment to cope with its absence, whereas no adjacent detachment is present either to do so or to provide the counter-check. Hence, either all detachments have gone to town B8 or all detachments have threshold cover from an adjacent detachment for the zone previously under surveillance. In fact, if a general alarm went out, then all detachments which had threshold cover ought to have gone to town B8. The suspicion is that some detachments without that cover may have gone too. So, if all detachments that have threshold cover have gone to town B8, then some detachments that have not got threshold cover have also gone to B8. The question is, does this follow? For if it does follow, there is by now something very wrong with the internal security of this neighbor. 165. Good. Now it seems that even when there are only 3 elements in the situation, as there are here, it is well nigh impossible for the unaided mind to decide whether the conclusion follows from the premises and or not. This, then, is the type of argument that can be examined by formal logic. There is still the same old X in the situation, this time it stands for a possible detachment. There are 3 schemata of X. These are, Fx, Gx, and Hx. The algebra of the propositional calculus of logic is now used to link these schemata in order to restate the 3 propositions in a way which unambiguously expresses their meaning. As in the last 2 sections, they are written down here to show what this rigorous language looks like. Is the universal and the particular quantifier, E signifies implication, negates the following schema, V signifies disjunction, the dot Beto-Ken's conjunction. To find out whether the first 2 propositions jointly imply the third requires a formal test of the supposed implication. The analysis is not given here, but the point that must be taken is that no thinking process is now undertaken. Instead, algebraic rules are applied. The argument is first reduced to its simplest form, by appealing to logical theorems whose function is the same as those met with in Euclid. Then this formulation is subjected to a truth-value analysis which determines algebraically whether the implication holds. In this case it does. Something has been proved. On a question of practicability, it should not be thought that the object here was to supply the military men with a logical slide rule by which, in the course of an engagement, to determine decisions. This point must be made clear, because any such notion must surely appear unreal. The objects were to investigate the plans that had been made, to test their good sense, to uncover weaknesses and to probe in retrospect actual incidents which in fact led to chaos. The example quoted is based on one such incident, even then it is not completely factual, for real problems are more complicated than this. And so the story has been condensed to fit a standard logical format due to Professor Quine. 166. Which well demonstrates that a problem in no more than 3 schemata of X is not easy to resolve without the proper tools. The second problem to be discussed was tackled exactly 5 years after the military one just described. The same ore scientist was then to be found in an alloy steel works in Britain, investigating the flow of steel ingots from 3 different melting shops through varying selections of 11 different processes, the last being a rolling mill. Of the remaining processes, 5 were concerned with cooling, and 2 with surface preparation prior to rolling, 1 was a stockyard for cold material and 2 were concerned with heating prior to rolling. A model was developed to account for this situation. Conceptually this too begins with a topographical layout, for the processes are related chronologically, and the flow of material covers actual terrain. But of course a mapping of geographical features is almost irrelevant. Once again we find that a perfectly good homomorph of the layout is not homomorphic with the operational facts. Instead, the important thing to realize is that we are confronted by an interactive system that is zero-sum. This term means that if the system is disturbed, and in this case if products are routed to alternative pieces of plant, the sum total of all these changes is nothing at all. Take 5 ingots from A and put them in B, take 7 ingots from C, putting 2 in A, 1 in B and 4 in D, put 3 ingots from B into C process and now has 3 less ingots than before and process B 3 more, process C has 7 less and process D 7 more. Everything is different, but 3 to 3, 7 plus 7 equals 0. Not all systems operate in this way, but systems that are zero-sum have interesting properties. If more ingots arrive at one process than this process can accommodate, the extra ingots do not vanish. To preserve the zero-sum constant, they have to appear somewhere else. In many circumstances, a machine shop or an office, for example, the extra work piles up in front of its next process, forming a stock or a queue. But when hot ingots of highly alloyed steel are involved, this will not do. If they are allowed to cool in air, they will pass too rapidly through a critical temperature range, and crack. So these ingots have to be put into another process. Even if the delay is too short or the steel is not highly alloyed, the situation is not a neutral one, for the ingots are losing heat, and the effect will be felt later when they take longer to reheat to a uniform rolling temperature. Now the steel-making business would be uneconomical if a system of 167 this kind had much slack in it. This means that the process immediately in front of the rolling mill, through which all ingots must pass, is congested. It also means that when an ingot destined for this process has to wait, which happens often, it must go somewhere else where it adds to the congestion. And so on. However, actual ingots are not allowed to trail around a works like so many frustrated passengers being shepherded round an air terminal. What moves around is information, statements about ingots and about processes, proposals and counter-proposals, instructions and countermanded instructions. All this happens at a fairly low organizational level. If a serious alteration to plan is contemplated, it will be referred to the shift manager. The or man, actually measuring the impact of one such change in the course of a night shift, recorded the manager as making 28 telephone calls around the works in order to sort out the repercussions of that change. This gives an indication of the size of the repercussive effect. But no managerial intervention is called for in normal running, only the repercussive effect exists. How can this be investigated? The conceptual model of this situation was taken from the science of acoustics. According to the analogy set up, a disturbance of the kind described sets up a noise which reverberates round the 11 processes, and finally dies away. This reverberation may be measured according to the amount of rerouting it causes at each point. The length of the reverberation will be affected by the occupancy of each process, for this determines its ability to absorb, or necessity to reflect, the noise. These two measures take the place of the sound intensities and absorption coefficients found in acoustical science, and facilitate the statement of a homomorphic model for the steel works of an acoustic situation. When this model is understood, the usual advantages accrue. It now makes sense to devise a reverberation constant, for example, and to work out the effects of changes in the control system which might reduce it. It is also clear that acoustical chaos supervenes when a succession of sounds fails to reach the acoustically steady state, for the reverberation of the first sound persists while the next sound occurs, they overlap. Equally, industrial chaos supervenes when the reverberating information from one process change is overtaken by the next. So a measurable criterion of stability begins to emerge. Moreover, we can as usual make use of the insights of the scientific model within the managerial situation by importing acoustical laws into the homomorphism. For example, we know that reverberation increases and decays logarithmically, with a steady state period in between during which the rate of emission and the rate of absorption are in balance. This produces the peculiar curve 168, shown in Figure 12. Industrially, as acoustically, irregularities in the situation mean that this curve is not exactly followed, but we do know the basic pattern to seek. This is not, however, the full story of an OR job. We must return to the use of logic as a formal language. When an ingot arrives at the penultimate process, it may be accepted or diverted. Its arrival makes a noise. If it is diverted, the noise reverberates. If it is accepted, the noise may be totally absorbed, or it may yet reverberate, be interfering with the arrival of the next noise. This, then, is a reverberating ingot, one whose Figure 12. The pattern of reverberation. Arrival noise is not totally absorbed by the receiving process. No steel maker would know this term, of course, it is special to this study. The next special concept required is that of a harmless ingot, another term unknown to steel makers. This is defined as follows. The penultimate process is a soaking pit, a special kind of furnace in which ingots, already hot, are soaked in heat sufficiently long to give them a homogeneous temperature ready for rolling. The optimal soaking time had already been established by statistical studies of considerable elaborateness. An ingot which turns out to need no more than this time in the pits is designated harmless. An ingot which has to remain in the pits longer than this is harmful, because it causes a strange local effect different from reverberation. This is that ingots already withdrawn from the previous process are held up on the track between the two processes where, it is known, some of them crack as a result of being delayed too long at ambient temperatures. What was actually happening on this track was not at all clear until the probability distribution of delay had been evaluated, a study that proved inordinately difficult. This most unusual prob. 169. Ability distribution, unlike any other the scientist had ever encountered, was compressed, skewed, and truncated, and had to be explained. 4 factors accounted for it. First was the back pressure from the pits just mentioned. Second was a special forward pressure from the previous process deriving from surges in the flow of ingots caused ultimately by the bunching of steel furnaces. This was difficult to sort out, too, because there were 3 separate melting shops using 4 different steel-making processes. Third was a metallurgical instruction ruling that a given track time must not be exceeded because of the danger of cracking. Fourth came the effects on the records of clerical efforts to show that the ruling had been obeyed when it had not. Now a harmful ingot in the pits would make the situation on the track worse, and could provoke a special delay causing a cracked ingot. Therefore measures had been taken to direct any apparently cool ingot into preheating furnaces before sending them to the soaking pits. But this had to be done at the cost of heat, which naturally set up ambivalent feelings in the management. Economic pressures suggested that everything should be direct charge to the pits, metallurgical pressures suggested that any ingot suspected of having been cooled somewhat should be routed via preheating. Everyone claimed that the metallurgical rules were obeyed, but cracking continued. If all reverberating ingots that are direct charge to the pits are harmless, some reverberating ingots are not direct charge to the pits. The truth of this proposition is clear, because reverberatory effects are being picked up and a harmless ingot does not reverberate at all. If that condition of being harmless is not in fact being met, however, it is quite possible that all reverberation emanates from direct charged ingots. The economic pressure referred to means that the preheaters are not desperately congested, they may not reflect noise at all. Either this is true or all the harmful ingots are non-reverberating. For a control policy for reverberating ingots which makes free decisions about their routing will render them harmless. This is known, because in every trial of this freely mixed strategy no single ingot ever exceeded the optimal soaking time. Hence, either all reverberating ingots are direct charge to the pits, or all reverberating ingots are harmless. 170. What is the management trying to do? It is trying to save heat, and it would therefore wish to charge all harmless reverberating ingots directly to the pits, and route only potentially harmful ones through the preheaters, thereby rendering them harmless too. But we begin to see that this is not possible within the existing situation. Even if all reverberating ingots that are harmless have been direct charged to the pits, then some reverberating ingots that are not harmless have also been direct charged to the pits. This has been a difficult argument to present. It is hard to follow the establishment of premises and, because the two concepts of reverberating and harmless ingots are elaborate ideas, and because the real-life situation is intensely complicated. So the possibility of feeling certain that, the conclusion, really follows is remote without the use of formal logic. The variable x this time stands for some ingot. Once again there are 3 schemata of x, fx, gx, and hx. Again, the propositional calculus will show that the conclusion is correct. For the record, this is what the three propositions look like in formal Quinian terms and employing those schemata. As before, the argument has been simplified and expressed in a slightly different way from that originally used. But this was indeed one of the logical investigations made of a quantified acoustical model in order to reach a managerial decision. It is worth comparing the two examples given, the military and the industrial, as the comparison throws a good deal of light on the nature of management science. In both examples there was a determinate and a probabilistic component of the situation. Neither model has been fully explained here, but the size of military detachment was analogous to the size of lots of ingots, and both examples were basically concerned with movements of these detachments or lots. In each case the speed with which anything arrived anywhere could be expressed only as a probability distribution. In each case, there was a finite probability of non-arrival. Above all, there is a 171 resemblance in the fact that decisions have to be taken on incomplete information. This is the more important because it is not often realized and is often denied. It simply is not true either that you can find out anything you want to know in industry, or that you absolutely cannot find out anything you want to know in war. As far as industry is concerned, situations change in the process of being measured, information is slanted or frankly wrong, some things are hidden from observation and have to be inferred. Above all, gathering really deep, detailed and exhaustive information can be absurdly expensive. As far as warfare is concerned, any particular fact about a military enemy can usually be discovered if the price can be afforded in money, trouble, time, and men. And so scientific inquiry, although it necessarily requires data, must make good use of what data it collects, inferential as well as direct use. The framework of the model helps vitally in this. In the military example, an initially orthodox topographical model had to be enriched by a special elastic geometry before any sort of homomorph could be understood. In the industrial example, an initially orthodox flow chart had to be enriched by a model from acoustics, for the same reason. In both cases, these conceptual models led to the identification of sophisticated and previously unrecognized concepts, which could then be measured and manipulated. In each case, too, all three formal languages of science were used to express the scientific model in rigorous terms, although the logical language alone has been discussed here. Finally, then, turning to the formal logic, one wonders whether the reader has noticed the trick played on him. In each case it was remarked that the presentation had been adjusted to fit a standard logical format. In fact, the logical structures of the military and civil arguments are identical with each other, as can be verified by examining the two sets of algebraic propositions. Needless to say, this did not happen by coincidence, nor would it have been important if it had. The trick was done to re-emphasize that situations are subject to laws which pertain as well to the field of decision-taking and control as to the physical universe, and that these laws are conceptual devices by which we organize our empirical knowledge and predict the future. That is what makes them useful. 172. 9. A walk in the ramified system. Ita vita est hominum, quasi cum ludus tesseris, si illud quad maxime opus est jactu non cadite, illud, quad sucidit forte, id arte ut corriges. As when you play with dice, so is the life of men. If that which you most need to throw does not fall, then you should set right by skill the lot which has fallen by chance. Terence in Adelphi. 1. The building block of planned chance. However vigorously the manager qua policy-maker sets about the task of determining events, the manager qua decision-taker is a professional manipulator of chance effects. Although he has determined the general pattern of his activity, the stimuli which assail him and call for response are randomly assorted. This is, in a lambent clause taken from a works report of happy memory, owing to the day-to-day nature of actual events. The manager sees what the fellow means. In the quotation provided above, Terence forthrightly asserts a major aspect of the management task. A less literal interpretation was set upon the words by Ralphie Robinson, when he quoted them in an introduction to the second edition of Thomas More's Utopia, which Robinson had first translated from the Latin in 1551. This Tudor scholar lived in difficult and far from utopian times, as do we. He favored a more cynical account than the words of Terence strictly warrant, and so may we. His explanation runs, meaninge therein, if that chance rise not, which is most for the player's advantage, that then the chance, which fortune hath sent. 173. Ought so cunningly to be played, as may be to the player least damage. Whether we seek to amend things when chance upsets the plan, or simply to get out from under as Robinson would have it, we need a right approach. To the martinet, life must abide by the plan. But the influence of the manager does not extend to the control of force majeure. It may not even cope with the foreman. A viable plan has to recognize the role of chance, and the manager who is not neurotic knows this. It is commonplace to say that therefore the plan must be flexible, and also to say that decisions should therefore be taken sequentially. But it is not trivial to assert that chance is an intrinsic part of the plan, and necessary to it. In fact, entertaining genetic models leads to a conviction that planning cannot be adaptive to changing conditions unless random mutations are included in the plan. According to this view, the manager is not the opponent of chance, but its collaborator. This is well understood by diplomats, politicians, and perhaps big businessmen, that is because they deal with men and events. The manager, whose decisions also largely involve things, does not think of himself as manipulating malice in the object which is insensate, unresponsive, but he might well begin to do so. He needs to undertake engineering in probabilities. To do this he may employ the conceptual system which will be outlined, with its applications, in this chapter. It begins by walking out onto the shop floor and confronting the first down-to-earth, hard fact that is encountered. Suppose that this is a production machine operating in a simple environment. This machine makes things, and takes on the average 5 hours to do so. Its total product is passed on to the next machine, which also takes on the average 5 hours to complete the next process. Machine B receives no other raw materials than the product of machine A, and since the two machines stand side by side, no time at all is consumed in transportation. A naive account of this process declares, this is a perfectly balanced situation, there need be no idle time on these machines and there is no need for any inter-process stock. Now of course this on the average talk will not do as the man discovered who was drowned while crossing a stream of average depth 4 feet. Individual process times will be distributed around a mean of 5 hours. If the situation is as well behaved as it appears, a scientific account of it will show that process times around the mean are those most frequently encountered. The risk of encountering a particularly bad time decreases the worse the time is, while the chance of encountering a particularly good time decreases the better the time is. Very occasionally. 174. Say, an especially favorable combination of circumstances arises, and the job is completed in 3 hours. Very occasionally also, a concatenation of unfortunate circumstances will conspire to make the job last as long as 8 hours. In short, for each of these machines, the time taken to do a job may be viewed as a spectrum of likelihood centered on the mean, and the attendant distribution of frequencies can be drawn. In the present case, however, it will be noted that the distribution will not be symmetrical, the tail on the right will be longer than that on the left. Even so, an examination of past records will reveal what the distribution is in each case. It is no surprise to learn that statistical ingenuity can encompass this situation. In short, the probability of any particular occurrence can be measured. But to know what is really happening in this basic production situation, more than this is needed, for it is the interaction between the two processes that is managerially important. So time must come into the story. Suppose that a job is done on machine A, there is no means of knowing how long it will take, but we do know that this time will be a member of the population of times outlined by the distribution. The completed job is passed, at the end of this time, to machine B, which will now process it. The time this job takes is independent of the time taken on machine A. Again, there is no means of knowing what this time will be, other than to say that it is a member of the population of times depicted by the B distribution. This dynamic situation is illustrated in Figure 13. Here are the two distributions, dynamically connected by the transfer of two specimen jobs from A to B. Figure 13. The building block of planned chance. Here is shown the stochastic interaction between two processes having the same mean duration and the same pattern of probability. An infinitely long queue of work will be generated in front of the second process. The symbol underneath shows how this stochastic interaction is represented in subsequent diagrams. 175. Consider transfer I. The two machines start work together. A is lucky and takes 3.5 hours to complete its job, B is unlucky and takes 6.5 hours. Hence, when the operator of machine A hands his piece to the operator of machine B, he will not be ready for it. In fact, the piece will lie on the table between the two machines for 3 hours. This begins the formation of a queue. For, if by chance precisely the same thing happens next time, a second piece will join the queue at precisely the moment when the second operator picks up the first piece. If the same thing were to happen again, there would be two items in the queue 3 hours before B finished his second job. Now consider the second sample transfer. A takes 7 hours, by chance, to complete his first job. But B has been lucky and has taken only 4 hours to complete his. On this occasion, then, B will have nothing to do for 3 hours until A completes his work. If this situation were to repeat itself several times in succession, B would enjoy 3 hours with nothing to do in every 7. In practice, these runs of arbitrary couplings do not often occur. As a matter of fact, we can measure the probability that they might. If there is a chance in 100 that the extreme item we have considered should occur on machine A, and also that it should occur independently on machine B, then the probability that this couple will occur is the multiplicand of the two probabilities, namely, 1 chance in 10,000. To find the probability that this same couple would occur 3 times in succession, we should raise the probability of the couple to the power 3. The answer is 1012, or 1 chance in 1 trillion. It is clear that the manager need not worry very much about these particular risks. On the other hand, something must happen each time and there is no means of knowing what it will be. It might add to the queue of material between the machines, or it might suddenly cause idle time on machine B. Now it should be fairly obvious that although no particular event can be forecast in this situation, it must be possible to say something about the dynamic interaction of the two machines. It is in fact possible to calculate, by the use of mathematical statistics, the extent to which this queue will grow, and at what rate. In the case quoted, it is clear that although idle time may be encountered on machine B for a certain period of continuous working, the chances that a queue will eventually begin to form are very real. Once the queue does begin to form, the likelihood that B will ever catch up becomes increasingly remote, because it would have to engage in a very long run of unlikely couplest chances of which, as we have seen, get very rapidly more remote as time proceeds. This thoroughly basic situation is so important in operational research. 176. As applied to dynamic systems, that a whole branch of mathematical statistics, known as queue theory, has been developed round it. One of the first results developed by this theory was to show that, in the conditions we have been examining, which is to say where the mean times are equal, the queue will eventually become infinitely long. This account has tried to reveal why this is so, but the result was, in its day, most unexpected. At the start of this story it was said that, naively, the production situation appeared in balance. Surely this was intended to convey that a fairly satisfactory arrangement existed. Did we, in all honesty, at once suspect that the situation was foredoomed to run completely out of control? Most people do not. Indeed, our ways of accounting in terms of numerical averages precondition us to believe that this situation is all right. Queue theory, it was said, accounts for the formation of queues in this way between a probabilistic supply and a probabilistic demand. On occasion, as has been shown, idle time is caused on machine B. One can see the sense in which this could be described as the formation of a negative queue. In the positive case, a collection of items forms on the table between A and B. In the negative case, a kind of vacuum is created on the tabli vacuum which seeks to suck material towards B and, failing to do so, results in idle time on that machine. These two terms will be useful. But the term queue normally carries a pejorative sense. It seems to declare that it ought not to exist. In the situation recounted, however, the manager will probably wish to avoid idle time on machine B, he therefore wants a queue. In these circumstances he will surely call the queue a stock. Indeed, he will surely be asking how much stock is required between these two machines to avoid idle time on machine B. It is not likely that refuge can be taken in the theorem from queue theory already quoted, because in real life these two distributions are unlikely to be identical, and their means though close to each other will not be identical either. Moreover, production will not be continuous forever, it will be interrupted from various causes, and one machine may have the opportunity to catch up with the other. But these complications can of course be encompassed by the theory. Now, although it was shown that the likelihood of long runs of unusual couples is remote, a finite probability still exists that any run we care to nominate, however bizarre, might occur. So there is no categorical answer to the manager's question. What can be calculated is the size of stock required to meet a given level of risk that it will run out. And so the key insight is reached. The manager should make no attempt to specify what the stock ought to be, his job is to specify the acceptable risk. Once he has said, supplies of these goods are so critical to our policy that I will not accept more. 177. Then one chance in 1,000 that the plant concerned will ever be idle, the statistician can do the rest. He will be able to say, for this given probability, what stock should be held between the two processes. The word statistician was used advisedly, for this is a straightforward statistical job as it stands. It seems very possible, however, that the manager will have no particular reason to nominate one probability rather than another. He will probably say, I do not really want to incur the risk that machine B will be idle, but on the other hand I am not prepared to see a huge stock investment laid down in order to meet this condition. And so we reach the question, how much capital can we afford to tie up in stock? Obviously, this is a relative question. The answer to it depends on the state of other stocks in the production situation and various other factors as well. It is for this reason that the wider view and interdisciplinary approach of operational research is necessary. But we shall return to this point later. For the moment, it is salutary to contrast what has already been said with the ways in which stock levels are actually fixed in industry. For the example of machines A and B is no more than an archetype of any demand-supply interaction. Perhaps a little hyperbole will be forgiven in describing what happens. The language is not unrecognizably extravagant. Manager A declares that he will supply Manager B with everything he wants, he prides himself on the service he gives, he declares that no intermediate stock is required at all. Manager B says that Manager A is a very nice man and means well, but he would get no sleep at night if he had to rely on the absurd arrangements made by Manager A to look after him. An argument develops. A financial man joins in, very properly doing his job of protecting the company's capital investment. Technical advisors join in, the stock will deteriorate, the stock will be unsafe, the stock is strategically vital because of scarce materials. And so on. Is it going too far to suggest that the stock level ultimately fixed will be proportionate to the resultant of all these forces measured in decibels? Certainly, the senior manager called in to adjudicate has an unenviable task. It has been shown here, on the contrary, that this problem when shorn of factors which impinge on it from the side reduces to a scientific calculation. This, then, is the building block of planned chance, the notion that two interacting probabilistic situations are dynamically related in a way which can be measured by the use of probability theory. Throughout this chapter the notion will be used diagrammatically, and it will be depicted as two dots joined by a line. It is to be understood that each dot represents a measurable probability. 178. Distribution, and that the line connecting them represents the statistical convolution, as it is called, of the two sets of probabilities. So the simple diagrammatic cipher which looks like a dumbbell is not the oversimplification it appears, it stands for a very real and down-to-earth interaction of considerable complexity. Remember, too, that most dynamic situations can be thought of in this way. Some of the earliest Q-theoretic notions were developed around the problem of the doctor's waiting roomie's appointment system, and the length of queue required to minimize his idle time. Queues form for buses too, and queues form in retail shops. But one encounters precisely the same phenomenon in the queuing of capital development projects for available funds, in the stock of nuclear weapons which one country may be waiting to deliver to another. In all these cases, management seeks to cope with chance, but this is a chance whose pattern can be measured on the lines that have been indicated. Once this has been said, the notion of planned chance becomes tolerable. For although it is still impossible to predict any single event at all, the pattern of interaction is predictable. This is to say, in turn, that any proposed alteration to one part of the system will have an effect on all the other parts, an effect which can be measured. Even the simple illustration given concerns a system. To improve the average time taken on machine A by 5 minutes will alter the idle time on machine B and have an influence on the stock held between the two machines. In the case of much larger systems, they may possibly be depicted by single interactions of this kind because the interaction of a large number of variables may nonetheless result in a single queue or stock. Finally, two special points must be made. Firstly, the problem of transportation time between a demand and its supply has so far been ignored. In fact, however, it is not difficult to deal with. For the time taken to transfer material from one place to another has a mean value, and is itself distributed about that mean. So there is no difficulty in nominating transportation as a process. In a scientific account of probabilistic interaction, this process will behave no differently from the production processes that are more familiarly called by this name. It also operates unpredictably within a predictable pattern. According to this view, machine A interacts with transportation which in turn interacts with machine B. Obviously this pair of interactions could create a need for two stocks, one awaiting transportation, and the other awaiting use at the other end. But, for the sake of the diagrammatic convention proposed above, the transportation distribution will be assumed to be accounted for on the line which joins the two dots. Thus, 179. The dumbbell still stands for the interaction of two major activities, and their convolution is represented by the line which joins them. But this convolution may be mediated or not, as the case may be, by a probabilistic process of transportation appearing on the line. Secondly, a point of technique deserves mention. It was said that the probabilities associated with this statistical model could be computed by the theory of queues. But this is true only in special cases which are as simple as that quoted. In other circumstances, although the theory is still perfectly correct, the mathematical apparatus for computing answers has yet to be discovered. For example, the pictures of the two distributions drawn in Figure 13 include one slight deviation from the account given of them in the text. A scrutiny of the figure will reveal a strange hump at the right-hand tail in each case. This hump stands for the occurrence of some kind of discontinuity which is very common in real life. In this case, the idea is that these machines operate an 8-hour shift. Thus a job taking 8 hours is bound to cross the shift boundary and have to be taken over by the next worker. This means that it will probably take still longer to complete. Hence the probability distribution may show an unnatural attenuation just before the hump, and an unnatural hump a little later. It cannot be overemphasized that the existence of such peculiarities is the rule rather than the exception in actual industrial studies. Backroom boy statistics is of little avail in these circumstances. It takes an operational research inquirer to elicit and to understand the full facts, and operational research expertise to discover ways of manipulating them. In this illustration, it is clear that the theory still applies. What is not clear is how the convolution should be computed, since there is no known way of solving the very peculiar mathematics which would result from an attempt to describe this particular curve. The solution is the technique known as simulation. This is very easy to understand because a simulation was indeed begun earlier in this section. It will be recalled that a start was made in creating an artificial log of the behavior of the system. A time was taken at random from the distribution of machine A times and compared with another time taken at random from the B distribution. The effects were evaluated. Another couple was then chosen, and so on. In this way, the behavior of the situation is simulated, and it is clear that if this exercise is done sufficiently often and at sufficient speed, we do not have to wait for a 180 work study measurement of what is happening in order to evaluate the queues and stocks involved. In fact, in large studies of ramified queuing systems, such a simulation would be mounted inside an electronic computer, which could then generate the equivalent of 10 years production experience in 10 hours. By examining the artificial log thus created, the scientist can estimate with great accuracy the characteristics of the fluctuating queue or stock. To control dispersion. Having worked out with some care what is meant by this notion of a building block of planned chance, the conceptual modeler may now build with it. It is clear that serial production could be envisaged as a Figure 14. Dispersing stochastic network illustrating production flow, retail distribution, transport system, etc. Long chain of dumbbells, the output of each process is fed to the next process, the output of which is fed to the next process, and so on. But few activities in which the manager is interested are as simple as this. The product of one process branches out to several more, while the input to any one process may derive from several sources. Hence the attempt to picture any large-scale activity in terms of an assemblage of these building blocks will necessarily look like a network. One basic configuration of such a network is given at Figure 14. Time may be regarded as unfolding from left to right, and very likely space does as well, although the picture is not meant to be topographically correct. In this configuration, it will be seen, everything begins with one basic activity, the outputs of which generate the activities of the entire network. 181. This network has a hard and fast look about it. It is necessary at first to remind oneself that each dot stands for some complicated probability function, and maybe the connecting lines do as well. What does it depict? Starting with production, it may be that the dot on the left is the output of a primary process, such as oil, or a plastic, or a flow of timber from a sawmill, or a flow of metal ingots from a primary mill. In that case, the output is divided into two streams, which proceed to feed other processes, until a whole range of endpoints is served. The diagram does not, of course, neglect to indicate that in reality such flow lines are not normally isolated from each other. There will be a certain amount of interchange between them. The problem of determining inter-process stocks, which has already been discussed for a pair of processes, can now be contemplated as a totality. In general, the inter-process stock gets more expensive as the diagram moves to the right. The penalties attaching to idle time will not be uniform throughout the system. A policy about the whole matter will be very much influenced by the possibility or otherwise of adopting alternative process routes. In short, the basic conceptual model, although quantified by the probability factors earlier mentioned, can now be weighted in various ways by other factors which may be obtained. As all the relevant information is made available and fitted into this picture, it becomes steadily clearer that we can talk of solving the network. This is a strange phrase from a literary point of view. All it means is that the operational research man is now in a position to calculate whatever parameters of the system the management would like to know. The proper scientific model will not look like the diagram, needless to say. The pure connectivity of a network like this can be written down in terms of symbolic logic, thus doing away with the diagram. The functions by which the constraints affecting the network are related may be written down in terms of mathematics. And of course the general quantification of this essentially probabilistic system will be expressed in terms of mathematical statistics. How to calculate the answers that are called for is a matter for the specialist. The object here remains to convey an insight into the nature of the problems involved, and if possible the conviction that the answers required are in principle calculable. The generic term for the behavior of a system of this kind is stochastic process. Such a process is one in which chance governs the particular selection of events unfolding in time or affecting any particular item moving through the network, but where the probabilities which govern these chances are themselves patterned in the way earlier described. Thus, although it is impossible to 182 determine what the state of the network will be next Thursday at 10 a.m., or to say precisely when an item beginning today at the left-hand point will emerge at one of the right-hand points, it is possible to say everything about how the system should be managed. Particular stochastic processes are examined mathematically, or experimented with by simulation, or they may be subjected to control in practice by the feedback techniques which will be discussed in Part 3. It will not have been forgotten that in Part I one of the points stressed about the nature of operational research was that it must consider a situation in its totality, and refuse to be blinkered by the conventions of description which already exist. Note then how a network such as this can be fully specified without any mention of particular areas of management responsibility, geographical boundaries, technological phases, or historical groupings. As a last remark on the stock holding issue, for example, it may be noted that solving the network could include the specification of its optimal uncoupling. That is to say, the location of present stocks is doubtless affected by the list of factors just enumerated. But stock ought not to be a device for uncoupling one manager from another, or one accounting schedule from the next. A stock is a machine for uncoupling demand and supply. It is a common outcome of operational research to demonstrate that the stock investment can be substantially lowered, not only by proper calculations as to optimal stock levels, but by a more ingenious distribution of the stockpiles themselves. Look for example at the top right-hand corner of Figure 14. 8 final processes are shown as deriving from a common source. A particular or study showed that a large stock was held at each of these final points for immediate dispatch to the custom rand, as in fact there were nearer 80 than 8. The investment was large. No one had thought of holding one stock at the previous process instead, a stock only fractionally as large as the total existing investment in finished goods. The reason for this failure to recognize an apparently obvious point was primarily that the production technology did not lend itself to the idea. Set-up times on the final processes were long, and therefore lengthy production runs appeared to be economically vital. Secondly, the production control technique did not permit effective machine loading in the more flexible situation. Thirdly, the sales department was convinced that immediate delivery from finished stock was commercially vital. Once the OR study had broken down the barriers that existed between the various functions, however, the whole matter was resolved with ridiculous ease. The engineers who had not been able to justify the 183 expense of improvements in the machinery were assured of massive savings and went ahead to change the plant. Once production control was assured that it had a new and different and readily resolvable machine loading problem, it speedily installed a paperwork system both cheaper and more rapid than the last. Once the sales department was assured that all these changes could be properly effected, it abandoned its die-hard policy that finished stocks must be available on the shelves at all times, and closed down its section devoted to juggling with stock balances. The cost office noticed the difference, the customers got better service, the technical people gave up worrying about stock deterioration, and withal quite staggering savings were made. Just how trivial is this example? Before anybody begins to complain about the use of steam hammers to crack nuts, let it be said that the annual savings in this case would have paid for the entire annual cost of the whole operational research department. Furthermore, the little example isolated here for discussion featured as little more than a footnote in the report which examined the network as a whole. Just as the conceptual model nicely obscures the conventional descriptions of the system which are best avoided in any competent new study, so will its solution avoid stereotypes as well. It has just been shown in microcosm how an apparently stock-holding study may have roots in both production and sales, and an outcome mediated by production control, costs, and other departments. Again, this is not the truism it sounds. There are a great many firms, for instance, in which the finance people determine stock levels on the grounds that they are the controllers of capital investment. So they are, but finance is rightly regarded as a constraint on a stock-holding policy. Finance has nothing whatever to contribute to the nature of the policy itself. This is an obviously correct assertion about the situation, when seen through the eyes of the conceptual modeler and his network. It ought to be obvious to management. That it is not so in the case of many famous companies may be brought home by observing their actions when the stock investment has risen to such proportions that some sanctions have to be applied. It is common, for example, for an appropriate stock level to be computed by such devices as comparison with other companies and indeed industries, or by extrapolating from earlier figures achieved when the company was quite different from the company that is now, or by making a financial judgment about the stock. 184. Investment the company can possibly bear. In any case, having determined a suitable total level and having calculated the excess of stock now held over and above this level, it is common for an edict to go out that all stocks will be cut by 10%. This is totally inept management. The likelihood that such a policy will lead to an optimal distribution of the stock investment is virtually nil. Moreover, and ironically, the best managed sections of the business will already have the least margin of excess stock, and the blanket ruling may force these sections below the critical threshold of efficient operation. This is bad in itself, but it should be noted that the stock they now hold is bound to lose effectiveness in the return on capital it can provide. Now it is a common argument that when financial considerations make a stock reduction of paramount importance, there is no time to commission an operational research study which would master the entire production network and discover the best solution. If the firm has not had the prudence to compose the appropriate models before the crisis comes, this may well be true. But there is a matter of the degree of resolution to be considered here. A full-scale study of the detail might well take 6 months, this is admitted. But what does in detail mean? Remembering the inductive theory advanced in earlier chapters, we know that the most advanced study, even if it lasted 6 years, would still involve mignon transformations from real life. Thus, as usual, it is a homomorphic model that is being considered. A competent or group should be able to carry the homomorphic reduction of the model down to a point where this problem could be solved in a day if necessary. To do so it would have to abandon a great deal of information and finesse, but it would produce an approximately correct answer. This very notion offends some pedantically minded people, but an approximately good answer simply must be better than a bad answer such as we know the blanket reduction policy to be. The point has been made in a more scholarly way earlier, but it will bear a pungent repetition. The man is paid by the management to help it make decisions, he is not paid to write PhD theses. If the management is compelled to take a decision tomorrow, it is incompetent in or to reply that its scientific integrity demands a 6-month study. If it literally can do nothing in the time available, of course it must say so, but normally, or can give some slight assistance, however short the time, particularly if it is an institutional or group, which is already fairly familiar with the general picture. Again emerges the justification for reminding young scientists entering the field of the wartime origins of the subject, deeply as some of 185 them resent this approach a generation later. For it should be so easy to see that if the enemy is standing over you with a drawn sword, there is no time to finish the calculation. Archimedes was killed in precisely this way, as is well known, thereby failing one of the important tests of an man. This is a pity, since in other ways he may be regarded as the founder of the subject. The manager he served was King Hieron too, for whom he brilliantly applied science to the strategic problems of defending the city of Syracuse against the Roman siege. But to return briefly to the matter of controlled dispersion, it is worth a moment to reflect that the production system used here to typify the conceptual model could be replaced by many other managerial situations. For example, the left-hand point might represent a factory serving two huge depots, which in turn serve numerous warehouses distributing goods to retailers. This is the classic distribution problem, a commercial topic. And yet, when the underlying model has been located, the logical structure is seen to be no different from that of the production setup. There are still the problems of stock holding, still the questions of location, and there is the eternal dilemma of investment costs versus customer services. Again, just as we may wish to discover the best route for a product to take through the production system, so we may wish to find the best route for a traveling salesman to take from his factory through a complex of market possibilities. The product and the salesman are both taking a walk through a ramified system, they are both continually entering and leaving zones of probability. The same is precisely true of a message propagated from a source to a destination, through a series of junctions or exchanges or people, or of the progress of a virus from a single infected person through a population of potential invalids, or of the propagation of a brand image through a market of potential customers, or of a flow of spare parts to broken down machines, such as cars or aeroplanes, that are in service. In short, in a great many cases the dispersing network built of stochastic variables offers a basic insight into the system under discussion. We know how to describe it rigorously, how to quantify it both structurally and probabilistically, and how to calculate the decisions which the dynamic power of chance demands that management should take. Moreover, we can as it were float on this network a large variety of scientific models, competent analogies, whose ways of talking and laws. 186. And techniques can be imported to the problem in the standard way. One of them was slipped into the list given in the last paragraph, the propagation of infection. This is an epidemiological model which has been used as a basis for solving management problems in advertising. But particular models are matters for the or group itself. One of the benefits that managements should gain from these considerations is the notion of underlying identity between many of the systems they handle. Any two systems which can be visualized as dispersing networks can be mapped onto each other under some transformation. This is true of two managerial situations or of two scientific situations. It is also true of two situations, one of which is managerial and the other scientific. There is the or trick. There is also the reason why managers and ministers can often be moved successfully from one area of activity to another. It is one of our managerial beliefs these days that this should be done. The procedure is often justified by the broadening experience it bestows, and often accounted for by the tautology that management is management. It is suggested that this tautology expresses, on a single plane, the identity which is best understood by looking for the underlying and common conceptual model on that deeper plane onto which all managerial experience maps. It has been shown how this works for a dispersing network, but obviously the networks describing systems that have to be managed do not all diverge. Then the question arises, does it make any difference if we consider converging networks? 3. Controlled convergence. From the point of view of production, a converging network represents assembly operations. Just as the diverging network provides a picture of production in which raw materials are broken down into ever more highly finished products or into byproducts, so the converging network is concerned with putting components together to form subassemblies, and subassemblies together to form complete assemblies. So the network pictured in Figure 15 might be the flow diagram for the production of a radio set, or an account of any other kind of construction, say of a cathedral, a power station or a submarine. Once again, however, this is not necessarily a picture of production at all. It might account for the supply picture of raw materials being brought into a factory, it might be a representation of demand, it might be the prognosis for a research and development program. 187. It will be at once obvious that this new illustration has been obtained by rotating the last illustration through an angle of 180 degrees. The two figures are manifestly isomorphic with each other. So there is a deep sense in which the answer to the question whether converging networks are different from diverging networks is that they are not. There is a different feel about them in management practice, and this is because each network unfolds in time. That is to say, instead of rotating figure 14, a similar result to that of figure 15 could have been achieved by figure 15. Converging stochastic network illustrating production assembly, construction of power station, capitalization of development, progress of research project, etc. Reversing the arrow depicting the flow of time. Since time is irreversible in real life, the diverging and converging situations do yield different features. For example, all inputs to the converging network must eventually reach one point, regardless of the route followed, whereas, in the other case, there is a wide range of terminal points, and an input will only reach one of these in particular as the result of a special switching procedure. On the other hand, the requisitions sent back through a converging network to obtain supplies have to be routed and timed to reach particular initial points. Managerially speaking, each of these basic structures has its own peculiar difficulties. Nevertheless, the planning effort needed to guarantee results, and the amount of control effort needed to obtain them, are identical. Hence the structural isomorphism is very important. IP 188 uncovers the level at which the control problem in any ramified system of probabilistic components is invariant. The point may be considered again in another context. One of the systems pictured as a divergent network was the distribution system of a company. Remarks were made about the outward flow of material through depots and warehouses and retail shops to ultimate consumers. Instead of thinking of the flow of goods through this distribution system, imagine the flow of information which the movement of goods generates. That is, the changing balances at all the storage points are being monitored, and the flow of transport is being detected, so that information is seen to be diverging through the network. Now the target at which all this information is being aimed is the ultimate level of demand at each terminal point. So if figure 15 is now consulted, demand information is being propagated through the network in the reverse direction. This information may be regarded as representing a vacuum for goods. It results in negative queues and negative stocks in the manner described earlier. Now the matching of supply and demand through isomorphically congruent networks is a particularly interesting phenomenon. For again it is possible to map a conceptual model from the physical sciences onto the situation. The flow of goods through the system implies a potential difference which is being offset. There is an evening out process in train. Such a process in physics is measured in terms of entropy ratio, which describes the amount of unevenness in question. But information is a negative entropy. If a mathematical expression is developed for each of these notions independently, they are found to be identical except for the minus sign in front of the second. Hence the energy transferred through the system is exactly balanced by the information flowing the opposite way. To speak of a change in entropy is ipso facto to speak of an equivalent change in negentropy. This equation at once provides a measure of the amount of control information that must be handled to contain the physical movements generated by the process of distribution. The model enables the scientist to determine the adequacy of the control system, the capacity of the computer required to automate it, and so on. However, the most noticeable feature of any walk through a ramified system, whatever its basic configuration, remains the stochastic interplay that shimmers across the nodes and lines of the network. The word stochastic, incidentally, comes from the Greek which means to aim at a mark. Now the manager who is concerned with assembly or construction procedures, on the basis of a converging network, is indeed aiming at a mark. He has to bring together various items which converge on a single node. This itself represents not only their physical conflux, but their coincident arrival at a particular moment in time. It is not always easy to hit this mark in a well laid out shop using flow production. In a jobbing engineering shop, where large custom built machines are made, it is yet more difficult. When it comes to building ships, motorways, power stations, and cathedrals, the task is more difficult still. But the conceptual model that has been constructed still holds. The manager well knows that the mark at which he aims is not a unique point in space and time, but one of those target-like patterns representing zones of likelihood, which generate a probability distribution. The manager's plan takes aim at the center of the target, and we can measure the chance that the arrow will miss by any given amount. And so the task of controlling the development of a massive construction project can be viewed as the generation of a stochastic process across a converging network, and as time unfolds and the target nodes are missed to a greater or lesser extent, the original network becomes distorted. A subsidiary job which is completed late will push the node representing its completion to the right on the diagram. There will then be consequences, in that the rest of the diagram must change. In the simplest case, a tremendous new effort may shorten the time required to hit the next node, so that, by the time this point in the plan is reached, construction has caught up with events. If the plan were conceived merely as a long line of successive nodes, one might have a good deal of confidence that the errors in hitting the center of the mark at each node would tend to cancel out, with the result that the final target date would be hit. Our problems in real life are exacerbated because this model does not hold. It is indeed a network with which we have to deal, and not a linear progression. Thus, when a job is completed late, difficulties resulting at one of the succeeding nodes may be overcome. For example, a colossal effort may be made to restore the plan and to hit the original target date for this next operation. Or, quite possibly, we may be passing through a portion of the network which is not critical to the completion of the whole. In other words, there is some slack at this point which can be taken up without real damage. Unfortunately, while the staff is attending to this 190 matter, a further chain or chains of events may have been started which it will prove impossible to control. For the node which represents the completed job that was late may feed other nodes as well as the one to which attention is most readily directed. These others may look less important, but in the long run they may themselves prove to have been critical points. Reflection on the diagram will suggest that secondary activities, which are begun late because of this primary delay, may feed other portions of the network, which might eventually deliver their effects in the mainstream of construction with disastrous effect. Anyone who has ever been concerned with this kind of productive activity will understand the point. In the limit, a large and expensive machine which is virtually complete may be held up for a long time awaiting the completion of some relatively minor aspect which suddenly achieves monumental importance, for the simple reason that the completion of the contract, as a whole, now depends upon it. If this is not to happen, it is vital that the plan should recognize which of the various links between nodes that are under stochastic implementation at any one time really is critical to the success of the ultimate aim. Nor can the most critical of the momentary links be recognized unless the antecedents and consequence of all the links are examined. This is, after all, a ramified system. The object must be to consider its ramifications. It thus comes about that a necessary stage in planning of this kind is an examination of the entire converging network, and the isolation of that route through it which is composed of all the critical links. This is in fact the longest route through the network, for time once used cannot be reclaimed. In rugby football, the ball may be thrown in one direction alone. In a converging net, to commit a foul against this rule is equivalent to a demand that time run backwards. The longest route is uniquely the route which guarantees that all the subsidiary loops of the network can be accommodated within the time allowed. This route is called the critical path. A whole collection of operational research techniques has evolved from this concept. These techniques all depend upon the recognition of the critical path, but they differ in their recognition of the criteria by which the longest route should be ascertained. For example, if the major object is to finish the entire job in the shortest possible time, the critical path may be different from that which would emerge if the criterion of success were that the job should be completed at the minimum possible cost. The basic reason for this difference is that, if cost is not of overriding importance, a stochastic delay can be made good to the extent that the proba 191 probability distribution at the succeeding node may be assumed to operate at a low level of probability in favor of rectifying the plan. In real life, This desirable consequence may be achieved by taking special, if costly, precautions such as increasing the labor force. Naturally, the critical path through a converging network can be discovered under any criterion or balance of criteria. The corpus of techniques which flow from this particular aspect of the conceptual model is known as critical path analysis. In some quarters, highly specialized versions of the approach have been developed with particular criteria in mind, and the resulting technique has been given a brand name. Thus managements are sometimes offered these techniques under their brand names as ready-made means of optimizing performance on a construction job, provided that the criterion of success can be stated in advance. But it is not really in the spirit of operational research that techniques should be sold in this way as pre-packaged commodities. Their application, sight unseen, is risky. It is, on the contrary, most important that proper research into the managerial desiderata in a particular case be undertaken before the program that will isolate the critical path is settled. When it is settled, however, the critical path is of paramount importance to the management of this kind of production. In the first place, it will be clear that to know what is the critical path enables a manager to concentrate his managerial resources on the task of meeting the delivery dates represented by the nodes that lie on this path. Provided that this particular collection of nodes can be adhered to as a series of target dates, it is guaranteed that the total job will be finished on time. Managements have been aware of this fact for many years, and have often tried to isolate the critical path as a guide to their control of the situation. But it is only since the advent of electronic computers that the full possibilities of this idea have been developed as a practical proposition. For the fact is that quite early in the production process difficulties are likely to be encountered which will involve a late completion at some node on the critical path. Hitherto, it has been a practical necessity to adhere to the prearranged path, and to use one's resources to try and catch up on the prearranged plan. But, given that a delay does occur, it is probable that the critical path from that point onwards is not the same as the critical path originally foreseen. The balance of interacting probabilities in the stochastic progression through the network causes a shift of emphasis which dictates a new critical path from the point at which things began to go wrong. In practice, this means that the critical path should be re-evaluated more or less continuously in the course of construction. This is a very difficult 192 task when there are no less than 30,000 nodes in the network and 11,000 different contractors responsible for achieving the target dates they represent. In such circumstances, a computer program alone is competent to re-evaluate the critical path more or less continuously, and thereby to guide management in its control of the situation. It is worth considering just one example of a situation that can readily arise, in which the value of this technique becomes fully apparent. Let us suppose that a stage of a construction job is most seriously delayed early on in the proceedings. The completion of this phase is 2 weeks later than envisaged in the plan. Now it is simply not true to say that everything can be delayed by 2 weeks, and that the completion of the entire contract will also be 2 weeks late. The network, if it has been properly constructed as a model of events, will undoubtedly wander outside the sphere of influence of the management itself. For example, if there are indeed 11,000 contractors, then the entire job is heavily dependent upon their cooperation. The fact that the program is now 2 weeks late may prevent one of these contractors from undertaking his part in the program at the expected time. If this happens, there is no guarantee that his services will be available precisely 2 weeks later. The economics of his own business may compel him to embark on other work, and to get out of phase with the program in which we are interested. It could thus happen, by a concatenation of such circumstances, that a 2-week delay encountered within the construction program itself might result in a 6-month postponement of the final completion. This outcome would be thanks to the ramifications of the system concerned. It begins to act as an amplifier of delays. Now the managerial consequence to be drawn from such a situation is of the keenest interest. Instead of embarking on the new critical path, which has been computed to result in a 6-month delay in completion, it is open to the management to determine that they will after all adhere to the original critical path. This is usually a physical possibility. By taking quite extraordinary measures it may be possible to achieve very high speeds on the next phases of the program. Normally, if these exceptional measures are extremely costly or otherwise causes for alarm, no one would seriously consider them. The stereotyped answer is that since a delay of 2 weeks is in question, only 2 weeks' worth of expenditure at the most is justifiable in order to catch up. So the phase space of acceptable solutions is narrowly determined. Once it has been calculated, however, that a 6-month delay is now inevitable, the losses that would accrue. 193. From this delay are the measure of the opportunity loss incurred in accepting the situation. This is a scientific measure of something that would normally be regarded as imponderable. It may suddenly become clear that the cost of taking utterly extraordinary measures is much less than the loss which would be involved in accepting defeat and adopting the new critical path. Without the benefit of this operational research result, many mistakes are made by acquiescing in alternative routes to the conclusion which are simply not economic. It has to be noted that orthodox accounting procedures will not be able to measure the amplified loss generated by the ramified system following an initial delay for the simple reason that orthodox costing procedures have no means of including this factor in their measurement task. Hence in practice, in a case such as that quoted, the cost to the program of the initial 2 weeks delay will be costed as an ultimate loss of 2 weeks. And this is quite wrong. These then are some of the insights into managerial situations that are obtainable using the converging network configuration. It has been shown how a situation of this kind can be controlled, despite the risks and chances that are built into it. The key thought remains that the probabilities built into the system can be measured and accounted for by various means. The manager is not at the mercy of fate. Of course, he already knows this, and he seeks by determination and skill to amend the hand that is dealt to him by chance. But if he should decide to call in science to aid him in this task, he will find that much more about the system can be measured and predicted and controlled than he hitherto believed. It is vital to make use of the understood patterns of stochastic processes. With a knowledge of these patterns and how they can be manipulated, the concept of control returns to a situation which might otherwise be no more than a sustained fight between inflexible intentions and bad luck. Control, seen in these contexts as the confident manipulation of apparently random events through an understanding of probability, remains possible. To achieve it, the manager must engineer with probabilities, he must build an edifice with the building blocks of planned chance. 4. Controlled hierarchy. By rotating the now familiar network through another 90 degrees, a new diagram is obtained. This at once creates the impression of 194. An hierarchical structure, but one which differs in a number of important ways from the familiar family tree type of organization chart. In the first place, the nodes in the network which now represent individuals are not very tidily placed in ranks of equivalent importance. This is realistic. Whenever one lives close to a group of managers alleged to be of equivalent rank or status in the organization, one rapidly discovers that this is not strictly true. Because of a differential importance in the Figure 16. Hierarchical stochastic network illustrating company organization structure, the devolution of government, military command in the field, etc. Activity each commands, or because of historical associations, or in the limit because of the personalities of the men concerned, it is possible to produce a rank within the rankdodicide of any two of the men which is the more senior. Secondly, there is diffuse responsibility and authority indicated by this diagram. In places we may detect the normal rule that each man has only one immediate superior, but in other places he appears to have two or more. Again, this is no more than realistic. This diagram has not been handed out by the firm as an account of the way it is managed, it has been created by an operational research investigation which has sought to depict the relationships which actually exist. Very often a man will accept instructions from someone who is not his nominal superior, and equally he may be able to influence people of 195. Senior rank to whom he does not nominally report. Thirdly, it is important to remember the convention of the dumbbell. This diagram does not represent merely a chain of command, but a flow of information and decision. Consequently, this is a dynamic picture of stochastic interaction. This network, with its three distinctive features, forms a good basis for discussing models of organization. One of the first questions which ought to be put to any alleged representation of a management structure is, what happens when someone fails in his job? Supposing that a manager, having received various information through the network, gives a wrong decision, what capability has the network for rectifying the error? An excellent model through which to discuss this problem, and indeed to quantify it and to reach conclusions, may be taken from neurocytology. Parts of the brain contain networks very like the one shown. Each node or decision taker is a nerve cell, called a neuron. The neurons are connected together by nerve fibers, of which there is a very large number. The diagram poorly represents a neural network, because the nodes are firmly connected by single lines. In brain tissue, a neuron is approached by a large collection of transmission lines which are themselves net-like. They are the dendrites which impinge on the neuron and cause it to change its state. Nerve impulses arriving at a particular neuron, therefore, do not come thumping in as might be imagined from figure 16, they dribble in with more or less reliability. And yet, the convention underlying the networks printed here is that the lines drawn on them represent stochastic interactions, so information flowing through this particular network must be regarded as arriving at any one node with a certain probability. Whether the neuron fires or not, thereby transmitting information down its axon, is also a probabilistic matter. The brain is a computer having 10 billion unreliable computing elements. So the analogy again holds. Few managers would claim that the stream of decision which emanates from them all day long is uniformly of very high reliability. Remember that people often speak of decision as if the word related only to that vital moment when a verdict must be reached that changes the future course of the company. We are here considering instead the total communication of a manager within the network, a man whose judgments are flowing upwards, downwards, and sideways through the organization whenever he writes, speaks, uses the telephone or has lunch. So this is a viable conceptual model. Now it must be followed down to the rigorous level. Figure 17 shows a formal neuron. It has two inputs, A and B, and 196. A single output C. Its job is to compute A plus B equals C, that is to say, the neuron should take a decision when it receives information from both A and B, and then pass on a message. Thanks to the general unreliability of the network of which this node is a part, it may well be that the information coming in down both channel A and channel B is only 70% accurate, while the neuron itself fails to draw the right deduction I in 200 times. These figures may well be realistic ones to use where the brain is concerned. Perhaps they are also reasonably good estimates of the kind of situation in which a manager finds himself. Figure 17. Decision-taking node of hierarchical network. With error rates A and B 30% or N 0.5%, C gives wrong answer most of the time. A manager whose two sources of information are on the average 70% correct, is, perhaps, fairly lucky. After all, the men who advise him may have misunderstood the situation, misinterpreted the facts, incorrectly conveyed their own understanding, or they may have changed the emphasis either by accident or design. As to the manager himself, even in this elemental, archetypal situation he may very occasionally produce the wrong answer. The first question is, what are the chances that the neuron or the manager will give the wrong decision? This probability is very readily computed. The probability that A is correct is 0.7, the probability that B is correct is also 0.7, the probability that the decision taker is correct is 0.995. Since the chance of making a mistake at any one of these 3 points is independent of the other two, the total probability of obtaining a right answer is 0.7 times 0.7. 197 times 0.995 equals 0.48755. The chance of getting the answer wrong is then the complement of this, namely 0.51245. That is to say, the neuron will be wrong most of the time, and so will the manager. In this situation, it looks as though some very extraordinary advice ought to be given to the manager. His chance of being right is less than evens. In fact, out of 100,000 trials he can expect to be wrong 51,245 times. Had he given the opposite answer every time, then, by saying yes instead of no and no instead of yes, he would have been wrong only 48,755 times. The advice appears to be that he should most carefully consider the evidence, take a cool and deliberate decision, and then reverse it. A manager who felt constrained to spend his life in issuing the opposite of his most carefully considered decisions might well regard it as a mockery. And if this is the best that the computing elements of the brain can do, then equally it is a wonder that we humans are as well served by our brains as we evidently are. There must be an answer to this extraordinary paradox, and there is. Historically, light was first shed on this problem when that great mathematician, the late John von Neumann, asked the following question about the taking of alcohol. It seems that a modest amount of alcohol in the bloodstream will cause a neuron to change the threshold at which it fires. That is, the amount of stimulus received from A and B before C will be triggered off alters. Now, if the brain consists of an intimately interconnected network of 10 billion neurons, and if the taking of alcohol causes all of these to change threshold, how can the brain possibly function when people are drunk? Of course, drunkenness causes people to behave in strange ways, this is known. But considering the radical change made in the whole computing circuitry, it is surely extremely remarkable that people manage to behave in a manner in the least approximating to that of a normal human being when alcohol has been taken. Von Neumann soon showed that the basic trick used by the brain as a means of making reliable computations with unreliable components is the principle of redundancy. If one suspects that a vital telephone line may be cut by the enemy, the obvious precaution is to lay a number of lines in the hope that at least one of them will survive. This is known as multiplexing the channels of communication. Equally, if it is suspected that the telephone instruments themselves may not work, it becomes possible to consider the connection of these multiplexed lines to a collection of instruments. One could then take, as it were, a vote on the outcome. This design is called a majority organ. Computations of the probability that a message 198 will be correctly received show that the chances increase very rapidly as the level of redundancy in the circuitry rises. From these early calculations, several scientists have developed an advanced theory of redundancy in neural nets, notably McCulloch and his collaborators. It is now clear that the brain manages to achieve its high level of reliability by multiplexing its nodes and its channels according to a very complicated logic. By doing so, it overcomes not only the influences of such threshold-changing stimuli as alcohol, but also the inherent unreliability of the components themselves. Living components have an inevitable tendency to atrophy and fail, and it seems likely that the neurons in our brains are cutting out at the rate of 100,000 a day. For example, McCulloch has estimated that at the age of 60 a man will have lost between 10 and 20% of the Purkinje cells in his cerebellum. Yet the machinery still works. The cerebellum continues to control his posture, and he does not fall flat on his face. The brain is in fact imperfect, from the very beginning of life to the very end, and its machinery is moreover constantly falling into disrepair, so the trick by which it produces a reliable output is important. Using the model to comment on the managerial situation, it is clear that human societies have adopted the same device. Not only is there a tendency to form boards, committees, conferences, and meetings of a formal kind, there is also the tendency to undertake a great deal of unofficial consultation within any managerial group. Hence people are accustomed to monitor each other, in both formal and informal ways, and sometimes the informality can extend to complicated networks which extend out of the organization and return to it, having passed through quasi-members of the organization on the way. This band of quasi-decision takers may include people from supplying or consuming companies, from university research departments, or from comparable companies in the industry, and they may include such people as bankers, stockbrokers, city editors, and even wives who have been talking to other wives? That all this kind of consultation goes on is well known, but its importance has not perhaps been fully understood. Had it been understood, it seems impossible that the kinds of organization chart with which we are most familiar could ever have been drawn, or that responsible teaching establishments could continue to instruct senior managers on the importance of defining unique responsibility within an organization. The trick of redundancy is the means of reliability, and it has to be represented within management theory in a measurable way. In that case, it will be well to examine a redundant network, which might either be a neural net from the brain or a management consultative situation. 199. Figure 18 shows a redundant network in which the same two inputs A and B are multiplexed into 5 line inputs. The error rate on each line remains 30% as before. These inputs now stimulate 4 unreliable neurons, each of which gives the wrong answer 1 in 200 times. It will be noted that all the lines are connected to all the neurons, and that the assembly of neurons then commonly supplies the output C. The diagram is drawn to suggest a section of the cerebral cortex, but it shows the formal connectivity just explained. Figure 18. Decision-taking cortical-looking system with unreliable components and 5 line inputs. Gives the wrong answer once in 100 million trials. The computation of the probabilities is now more difficult. Here, at any rate, is the expression that has to be evaluated to find out how often this network will give the wrong answer. The result of this calculation is. This is to say that there is only a chance in 100 million of obtaining a wrong answer. Using the same input information as before, and using decision-taking elements of the same order of reliability as before, a fantastic increase in reliability has been obtained. This cortical-looking network is further formalized in Figure 19. Here, for the sake of variation, 10-line multiplexed inputs are used. These are enclosed in cables the more clearly to indicate the connections. This is still a brain-like system which may be copied electronically. Alternatively, the diagram shows a group of 4 managers, well supplied with unreliable information, reaching a corporate decision. With this system, the probability of obtaining a wrong answer is 0.63 x 10 to 8. That is to say that there is only a 63% chance of obtaining one wrong answer out of 1 billion trials. This network is in fact over 800 million times more reliable than the original. 200. It has to be reiterated that Figure 19 is very much simplified. For example, it makes assumptions about the nature of the error in the system and about what counts as a correct output at C. On the other hand, it uses only the crudest of the logical devices made available by this research. In fact, we learn from the brain how to use inhibitory impulses as well as excitatory ones, and in practice the whole treatment is vastly more complicated than this simple example suggests. Figure 19. Decision-taking system with unreliable components, and 10-line cables. With the same error rates as before, this network is 800 million times more reliable. Even so, on seeing this demonstration, some people may think that there must be a fault in the argument somewhere, for it appears that something has been created out of nothing. It is well known that one cannot have a perpetual motion machine, and that something is always lost when any kind of activity is undertaken. But here something seems to have been gained a great deal in fact. The reason for this mistaken notion is that a wrong model is being used. It is a model taken from heat engines or from mechanics. Now it is certainly true that redundant networks are inefficient in terms of the energy they consume, or of their cost. But this is not the parameter of the system in which we are interested. The concern here is with information, and the information in this example has been amplified. So the right model to have in mind is perhaps a radio set. The sounds emitted by 201 radio transmitters fill the air around us, but we cannot hear them. A radio receiver amplifies them to the point where we can listen without difficulty. It is a device that consumes a great deal of energy in the process of providing amplified information. So the trick is possible. Now von Neumann propounded a mathematical theorem which showed that if one is prepared to go on increasing the redundancy of a network without limit, it is possible to obtain an output of arbitrarily high accuracy from a network whose components are of arbitrarily low reliability. This is an extraordinary guarantee. Neither brains nor company organization would work if it were not so. It is one of the uses of operational research to deploy this neurophysiological model in the analysis of organizational structure and in the design of more effective organizations. For it should be noted quite clearly that for a given level of redundancy it is possible to construct a network whose reliability is either almost the same as the equivalent non-redundant network, or one which is enormously better. The difference lies in the skill with which the logic of neural nets is deployed. This has been an example, no more, of the thinking which operational research can bring to bear on organizational problems. The principle of redundancy is relevant to any sort of control system, whether this is an industrial management, a government policy, an army command in the field, or a signaling system on a railway. The neurophysiological model has much to offer the designer of managerial control systems, as will be investigated further in later chapters. This discovery is very recent. In fact, before it can be exploited in even a small degree, people at the top of major organizations will need to assent to the propositions that management structures need to be, can be, and should be designed at all, and that they are stochastic, not formal, networks. Experience suggests that they prefer to rely on the self-generative properties of social groups, on oversimplified pictures of the stochastic interactions of their nodes, and on the guidance of this growth on the organization chart according to the principles of aesthetics. Whoever saw an organization chart that was indefinite, redundant, or even asymmetrical? The lack of cogent thought about these problems, let alone of a competent scientific formulation of the principles involved, explains much that is inefficient and even futile about the direction of contemporary affairs. Above all, it explains the unhappiness and frustration of many junior people, in the lower and often middle levels of management, among professional men such as accountants and civil servants, in the research laboratories and other fields of scientific endeavor. The more 202 lowly placed individual sees himself at the bottom of a massive organizational structure, the weight of which bears down upon him, and the limits of which fade out of sight and comprehension. He does not see the top of the pyramid in all its simplicity. He sees the man above him and his colleagues, and the rank above them. He knows that at this point other sister organizations merge with his own, multiplying the list of high officials. He hears tell of associated enterprises overseas, and visualizes how they add to the score. Certainly he may know the name of the Figure 20. Hierarchical stochastic network illustrating the limit of upward vision of a lowly plaqued person in a large organization. Chairman, but the limit of his practical understanding is a pantheon, not a father figure. He simply does not understand, nor, in the context of an irrelevant organizational model, is he understood. This lengthy chapter ends with the fourth and final rotation of the stochastic network. It gives some idea of how this person feels. The difference in viewpoint for the lowly individual is now obvious, yet its importance might still be underestimated. Professor R. W. Ravans has made a study of what he has labeled the opaqueness of organizations. How many people believe that they understand the problems of those who work beneath them, or that those for whom they work understand theirs? Ravans found that 28% of shop floor operatives believe their own foremen understand the operatives' problems. Of these 203 same foremen, 88% believe that they understand the operatives' problems. Of these foremen, 43% believe their own works managers understand the foreman's problems. Of these works managers, 94% believe that they understand the foreman's problems. Of these works managers, 59% believe their own general managers understand the problems of works managers, and all general managers believe they understand the works managers' problems. Looking down from above, we can roughly quantify what Ravans happily calls the downward transparency of the enterprise by multiplying out the levels of belief which people hold about their own understanding of the next junior rank, 100% times 94% times 88%, which is roughly 83%. This is the degree to which management corporately believes it understands operational problems. The man shown at the bottom of figure 20 might measure management sympathy for his problems as 28% times 43% times 59%, which is roughly 7%. This is the upward opaqueness of the enterprise. However critical one may be of the crudity of these two assessments, they are supposed to measure the same thing. The disparity between 7% and 83% is sufficiently large to indicate that the observer's vantage point conditions his results, and to imply criticism of communications within the enterprise. 204. 10. Apollo's gift. Quic quid dicam aut erit, aut non. Divinere itanem magnus me I donat Apollo. Whatever I say will either happen, or not. Truly the great Apollo grants me the gift of forecasting. Horace in Satires. 1. The architectonics of planned chance. A particular configuration of a network was used in the preceding chapter, and all four of its right-angled rotations were mentioned in turn. This was convenient for expository purposes, but the whole idea can be generalized in the picture of an unspecified, undifferentiated network, having no origin and no terminal points, no apices and no directionality. It is stochastic, in the sense already described. It is probabilistic, moreover, in a further sense. That is to say that no route or trajectory through it is fully determined. So far a pathway through a network has been treated as definite, each node presents a set of alternative possibilities, it is true, but one of these is chosen at each successive node whereupon the route is prescribed. But now the picture is further generalized so that each node presents a number of alternatives, each of which has a finite probability of being chosen, the sum of their probabilities being unity. No diagram is given of this picture, for any one exemplification would betray the qualities of abstraction and generality which inform it. The object now is to give texture to the talk of management topics. Just as a picture may be painted on canvas, or a decoration may be printed on paper or cloth, this discussion is mounted on a stochastic network. Just as the picture will be affected by the texture of the canvas, or the fibrous structure of the paper, or the woof and warp of the cloth, so the dis. 205. Cushion in this chapter is affected by the substratum laid down for it in chapter 9. For the flow of decisions and events through time and space is spread inevitably across a stochastic network of probabilistically interconnected nodes, and the pattern shows through in the picture of management activity. The chances with which management copes are always there, and they are planned chances in the sense already given. Their reticulated structure has an architecture devised by nature, and systematic knowledge about the principles which guide that architecture is called architectonic. Although the use of the term model in this connection has been avoided, the network notion may have been thought of as being one. Indeed, some writers refer to it in this way. A fresh reading of the preceding paragraph may make my own attitude clear. The network notion is part of the structure of the language we use to talk about these matters. A real-life managerial situation which conforms to such a network, is best discussed in a language which implicitly expresses network-like notions well. This is the language developed in the preceding chapter. The same is true of any network-like conceptual model which operational research draws from science to map onto the situation. The generalization propounded in the first paragraph informs our discussion of both situation and conceptual model. When the real science begins, and the scientific model which underlies them both is sought out, a rigorous language of networks will be needed in which to express that model. This is given by the branch of modern mathematics called the theory of graphs, of which more will be said later. The aspect of models to which attention now turns is their predictive value. The adjective predictive has been used to qualify the noun model many times in this book. Models are devised to describe what the situation is, but if they can do no more than this, any decision based on a model will be competent to determine the existing situation alone. Since the existing situation already exists, there can be no point in seeking decisions which would bring it about. Not so. The model may be required to indicate decisions which, when applied to the existing situation, will change it in some desired way, or it may be required to say what decisions will offset an anticipated or possible change in some desired way. So the use of the model is predicated of the future. The attributes that are desired are called criteria of success. The formulation of a set of states for a model which meets the criteria of success is called its objective function. Now the sense in which a model can be called predictive must be considered with care. Neither managers nor men are fortune tellers, on 206. The other hand, they cannot afford to be as blithely helpless as the satirical Horace suggests at the head of this chapter. Apollo does not hand us a crystal ball, and the man who declares that he can foretell the future is no scientist. Yet in some way or other and to some extent or other we know what will happen, otherwise all management is meaningless. Apollo's gift is best described as an architectonic of planned chance. There are three main points to make about the kinds of prediction that can justly be called scientific. The first is that the uncertainty of the future may relate only to the details of a pattern which is itself highly likely and therefore predictable. For example, the manager of a retail shop selling clothes cannot tell whether the next customer will be tall or short. But he can say that, over a period, the proportion of customers of each height of individuals is randomly spread over a scale where the frequencies follow a Gaussian distribution. So the scientist can help the manager to calculate the probabilities of his having a run on the less common sizes of garment, and can help him also to fix the required stock levels for any given interval between deliveries of stock at a quoted risk of not being able to serve the randomly arriving customer. He can in fact specify the reorder rules. These rules say when and how much material to reorder. Similar problems occur in production processes too, and although such statistical techniques are patently relevant and useful, it is amazing how infrequently they are applied. When the situation does not declare itself as patterned in this stochastic way, the techniques are not used at all. This is where the question of prediction is so important. If the manager believes that the future is veiled in mystery, he may have a thought block about the very possibility of perceiving a stochastic pattern in events. The second point to make about scientific prediction has to do with induction. In arguing from an enumeration of particular instances to a general proposition, a precarious conclusion is reached. The 7 Danes I have met have blonde hair, therefore all Danes are blondes is such an induction. The conclusion is in fact false, and the reason for the mistake is that the sample size is too small. But, given a properly designed sampling scheme based on statistical theory, an inductive conclusion can be raised to an arbitrarily high degree of probability although it remains precarious. Now some people confuse this logical process, which is enumerative, with another which is quite different. Consider the general proposition, any kettle placed on a fire will boil. Is this an induction by simple enumeration? There have been a 207 great many kettles placed on a great many fires. As far as anyone seems to know they all boiled. No one ever seems to have recorded that a kettle left on a fire indefinitely failed to boil. This argument appears to be all right, the sample size is enormous, so the conclusion becomes highly likely. In fact, however, science provides an entirely different argument from this. It explains what happens when water is heated, it knows the chemical change that occurs, and why it occurs. In short, science has discovered the mechanism involved, and has no need to rely on the argument from multiple coincidence. That is the third point. In a great many management situations the possibility of prediction is denied because the manager's attempts to learn inductively fail. He is searching for the reiterated coincidence which will link two sorts of event, and he does not find it because it is masked by the complexity of the ramified system. Science can come to his aid. It may be able to identify the elusive correlation by multivariate analysis which sorts out the interactions of more variables than the unaided brain can simultaneously contemplate. Then prediction, based on what J.S. Mill called concomitant variation, becomes possible again. This process is scientific, because there is statistical evidence that the two variables are correlated. Therefore, an hypothesis can reasonably be formulated that they are linked by some common causal nexus, although what this may be is unknown. Alternatively, and preferably, science may discover the linking mechanism itself. If this happens, it seems unlikely that the scientist will refer any longer to prediction. One does not predict that a kettle will boil. Very often in operational research, however, the scientist penetrates what has hitherto been regarded as a mystery in a circuitous way. He may identify only part of the mechanism, or the whole of the mechanism imperfectly. Real life is after all extremely complicated, and its ramifications may defeat perfect understanding. In this case, the scientist may buttress his insights with inductive arguments of the other two kinds. He looks for some statistical inference, either in the form of a stochastic pattern in events or in the shape of high-probability generalizations based on samples, which will enable him to interpolate numerical relationships in models at points where the deductive mechanics are unknown. When he has to try and assert what will happen in the future against this background, he is not fully confident. So he may call his effort a prediction after all. The manager certainly will. 208. Expressing this account of prediction in terms of the network language is straightforward. As time unfolds, history fixes the uncertainties, the probabilities and the stochastic elements vanish in ascertainable facts. But although all the facts are in principle ascertainable, only a few will be ascertained. So the record of the changing network of the past is a many-one reduction of what actually happened. If its key characteristics are to be understood well enough to make a reliable prediction about its future states, that many-one reduction ought to be a homomorphism. That is, we must get its structure right, and we must decide on the selection of facts to illuminate that structure. It is, however, logically impossible to use the language of the network's description to comment on its own structure. There are profound reasons for this which belong to metamathematics. The commentary has to be made in what is called a metalanguage, which is to say a language of higher order than that of the system itself. There is no need to go into the technical details. The point may be exemplified through any of the well-known logical paradoxes. The barber shaves all those, and only those, who do not shave themselves. It is impossible within the linguistic framework of that sentence to discuss the problem of who shaves the barber. If he does not shave himself, he shaves himself, but if he shaves himself, he does not. Logicians call a proposition of this kind an undecidable sentence. But we can and do discuss this problem. We observe that the language in which it is couched is self-defeating. A language competent to express this discussion is a metalanguage. Now the network language which spans the gap between a problem situation and its conceptual model also contains undecidable sentences. This matters little in the course of managing, perhaps, but it can matter a great deal in operational research and the practice of management as applied to its own procedures. For it is then necessary to analyze the structure of the language spoken within both the problem situation and its conceptual model if the deeper lying scientific model is to be made rigorous. This analysis of the network cannot be undertaken in networkese. This problem is of course resolved by the creation of the scientific model, the language of which is a metalanguage with respect to the network language of the practical situation. From within the model, that is, one can discuss the situation which the model analogizes and ultimately maps, without being trapped into undecidable statements. All this is said at the level of philosophy, but its practical relevance is great, particularly in the context of forecasting. Here is an example. In a labor dispute, a bargaining network is set up between employers 209 and employed. Each of the contestants is himself a member of a wider network, and may see himself as spokesman for and responsible to his brethren, be they other trade unions or other employers. Sometimes, particularly when points of national interest appear to be involved, the stands taken within the bargaining network become reinforced by positive feedback from within the supporting networks on either side. For instance, Some tough demand that was initially advanced with due caution across the negotiating table is reported through the press, the supporting network hums with activity, the negotiators are pushed forward when perhaps they would rather withdraw. At any rate, deadlocks develop across the total system of networks because the equations that the network is trying to solve are insoluble. One sees the same thing in international diplomacy. In the limit, the labor representatives may refuse to settle for less than would literally bankrupt the firm, while the employers refuse to give more than will hold the employees to the firm. It is rare to see the undecidability of the conclusion quite starkly, because other forces tend to intervene, which they do in a meta-language. But the structure of the network language itself is undecidable in the limit, because if the employers win they cannot continue operations, and if the work people win they have no jobs. In short, whoever wins, loses. Again, compare international affairs, particularly unworkable peace treaties, which reveal that intelligent people, trapped in undecidable situations, cannot always find a way out. The disruption of undecidability may come with official arbitration, speaking a meta-language. But it could also be achieved through the metalinguistic or model. This would probably be taken from the theory of games. The situation is studied as if it were a game, with two sides and certain rules. This is the conceptual model. The rigorous model requires the mathematical analysis of the game's structure and constraints, followed by an evaluation of all possible strategies for each player. Since the likelihood is that an implacable opponent will select his own optimal strategy for each move in the game, the other player selects his strategy on that assumption. The scientist would seek to compute the best strategies by interpreting the player's criterion of success in mathematical terms, and using it as the objective function for his matrix. For instance, it may be decided to select the minimax strategy. This is a prudential course to follow, because it computes the maximum risk and then selects the strategy which minimizes this. Notice how the architectonics of planned chance permit the discussion of future. 210. Situations. According to a mixture of the three predictive methods, the game is the mechanism, the matrix is quantified by enumeration, the strategies are stochastic patterns. However, if the players have committed themselves to impossible positions, the game theoretic inquiry will quickly show this. Then what happens depends upon whether the game is zero-sum or not. It may be recalled that a zero-sum game was explained earlier. It is a game in which the total payoff is fixed, and the bargaining decides how this total is to be divided. Perhaps the contestants in most important games nowadays too readily regard their games as zero-sum. It is a possible opinion. If the game is non-zero-sum in principle, and those mentioned surely are, it certainly should not be constrained to a constant payoff. For a game that is freed from this constraint can generate a new and higher payoff to share, with the result that each contestant now receives a much better reward than he conceivably could have done under the old conditions. To do so, the players must form a coalition with respect to this particular game. The extra reward is generated by their refusal to lose payoff in friction, and is called collaborators' surplus. A meta-language in which it is possible to talk like this is clearly competent to resolve the undecidability described earlier. Moreover, the scientific objectivity of the model, and of the scientists who compute within it, might help to reduce psychological tension between the contestants. It seems possible that something of this kind has already been successfully operated in international affairs, and within the affairs of an industrial company. But there is no sign whatsoever that the available or approach has been used at national level to resolve the problems of social and economic affairs that are normally labeled political. Meanwhile, and instead, policymakers in both government and industry play strategies that are not so much good or bad as meaningless because no meta-language has been created in which to discuss them. They are caught up in undecidable sentences, which is the reason why no one ever wins the argument, and no decision ever turns out to be wrong. The nation suffers for this. For example, the industrialist who adopts a bad development plan and begins to make a product of national importance uneconomically is supposed, by classical economics, to go bankrupt. In fact, when he raises his prices, his competitors smile and raise their prices too. Legislation exists, of course, to stop this happening and can do so when formal coalitions are formed. But the 211 unexpressed, even unconscious, search for what is actually collaborators' surplus goes on. The theory on which we work supposes that this cannot be done without chicanery, deliberate abuse of the competitive code of Western society. But this presupposes that everyone in the game really knows what his costs and profits are, in detail and absolutely. He does not. Large ramified systems obscure these issues, and accounting systems are not clever enough to penetrate their complexities. Hence the smiling competitor who raises his prices too is probably saying in all honesty, I thought we were not charging enough for this product, now I am sure. The worst feature of all this is that it destroys the learning mechanism by which decision takers ought to learn through their mistakes. For an undecidable language has been revealed here in which no mistake can possibly count as a mistake. The bad development policy is shown by subsequent events to have been a good one all the time. The industrialist, or the minister, who is trapped in this undecidability is all too happy. Quick quid dicam aut erit, aut non, whatever I say will either happen, or not. In either case I am going to be right, good old Apollo. 2. Decision theory. The foregoing discussion of the nature of prediction is set within the general theory of model building. The sense in which a model may be called predictive has now been explained. A methodological amalgam is required, having three separable aspects: a correct identification of underlying structure and mechanism, a stochastic scheme of quantification, and a knowledge of statistical interaction. Decision, then, is an event detectable, describable, and indeed determinable, by the parameters and states of a model, whether this be formulated rigorously by the scientist, or unconsciously by the manager. Decision is effective to the extent that it is competent to modify future states of the system in a way which meets the pre-established criteria of success. Given this framework, the process of reaching the best decision is known as optimization, and the corpus of theoretical knowledge which bears on this process is called decision theory. Decision theory comprises a large number of mathematical techniques, details of which need sponsor no delay. 4. Using the network language, it is very easy to understand what kinds of problem will yield to these techniques, what is their fundamental nature, and through what kind of rigor they may be approached. They are divided arbitrarily here into three groups. 212. Geometric approach. The rigor of the first group is geometrical. Clearly the network is a geometric construction, and this may be valuable in tackling certain kinds of problem in which physical space is actually involved. Most notable among the applications of this idea is search theory. This is of predominantly military relevance. It has to do with the optimization of tactics for finding an elusive target. If Allied and enemy forces are each regarded as following a line depicted on the network, then they may encounter each other at a probabilistic node. Targets for each force are randomly distributed as the potential intersections of lines advance according to certain probabilities of which the density can be measured. The search procedure to be followed will depend on the information available about the enemy, whether his probability densities are uniformly distributed or are concentrated in particular areas, for example, and whether the likelihood of one tactically significant event is contingent on another or independent of it. Criteria of success in such problems are formulated as the requirement that the probability of a target entering the range of the Allied strike force as it moves down its path should be maximized, or that the number of randomly assorted targets which could enter this range should be maximized, or that the proportion of potential targets which can escape detection is minimized. The scientific elucidation of these strategies is of course important in the field of operations itself. But perhaps the most valuable management aid which the technique provides lies in the comparison which can be made of the effectiveness of alternative weapons systems and detection equipments. For it is possible to assess which is more effective when using its optimal search technique, and which is more vulnerable to failure if strategic exigencies compel the forces to depart from optimal tactics. All operational research techniques, once they are properly described in an appropriate language and are correctly referred to their underlying models, turn out to be relevant to a variety of problems, some of them not envisaged from the start. Search theory is potentially applicable to any sort of searching process, for searches are conducted outside the sphere of military operations, for example in the quasi-military searches undertaken by police forces. But we also speak of search in connection with patents, legal precedents, library references, genealogies, and so on. These searches are not conducted in physical space as were those studied by military or men. Nevertheless, this is not to say that search theory is 213 altogether inapplicable, for perhaps a given program of logical search could be mapped onto a geometric program of search through physical space. The barrier to such a development is conceptual rather than scientific, for in the geometric group of applications decision theory is concerned with an ordered series of decisions which trace out a course or pathway of action. It is of no theoretical importance whether this pathway exists in physical or logical space. For example, the search by a commercial company for customers requires a serial decision procedure on the part of the management which optimizes the use of its selling resources. Whether each sequential decision refers to the selling technique to be tried next or to the direction a traveling salesman will next take is scientifically immaterial in terms of the geometric rigor of a network into which both sequential decision problems can be mapped. Statistical approach. The rigor of the second group of decision-theoretic techniques is statistical. This group has to do with decisions that are in fact determined by the probabilities generated at each node of a network by the statistical convolution of the probabilities which flow into that node. Sequential decisions are not now concerned with tracing a pathway through the network, but with an instantaneous change in the state of the entire network as between one moment and the next. Mathematically speaking, if we write down the probability that the system is in one particular state at a given moment, and add to this the probability that it is in another particular state at the same moment, and so on until the probabilities are exhausted, we have a way of describing the stochastic nature of the system in its entirety. For the expression just calculated for a given moment in time is complete, it has unit probability. And it has all the resolving power needed by a network description, because it enumerates in mathematical shorthand all possible states of the system. Now it is fundamental to this thinking that the probability that a system will be found in a given state at a given time is conditioned by the state it was in at the previous instant. The passage of a system from one state to the next has, then, a transition probability which can be measured in terms of the likelihood of the immediately preceding state. This is called a Markov process, and a sequence of such transitions is called a Markov chain. When decision-taking is based on a theoretical foundation of this kind. 214. We are in precisely that area of forecasting most familiar to the practical man. He is often heard to say that the most reliable method of prediction is to assume that what has just happened will happen again rather than to work out a theory which will attempt to compute from scratch what the next state of the system will be. In fact, however, the scientist also knows full well that real life is a self-perpetuating business. The system with which the manager is concerned is a dynamic system, and not merely a random succession of states of affairs. This is precisely why the scientist who studies the stochastic processes implicit in a given network regards it as Markovian, and seeks out what he will call the dynamical equation which links the probabilities that one state will transform to the next. Moreover, the practical man knows that if a system is left alone it will run to some kind of equilibrium. A great deal of management technique is indeed based on this expectation. The question the manager wants to answer is, given that the profitability of the system is so much when the system is in a given state at a given time, to what level will the profit rise in how long before it levels off at equilibrium? Alternatively, if a profit is generated in the act of the system's changing state, what can I expect this profit to be in the equilibrium condition? The scientist computes this answer with ease, once he has established the transition probabilities of the Markov process, and found the dynamical equation of the system. It is with this statistical rigor that operational research tackles a large variety of problems which depend on stochastic interactions in the network. Queues and stocks and inventories are all residues of statistical interactions, as was described in some detail earlier. According to queue theory, it is possible to determine how long a queue should be to ensure that the process for which queuing is going on will undergo no delay for any given probability. In hospitals, this conclusion is important to consultant physicians who do not want to waste their time, but who do not wish to keep patients waiting unnecessarily. It is important to production economics if a machine is not to experience idle time. It is, conversely, important to a supermarket to ensure that even at the risk of some idle time on the part of the cashier, a queue of customers does not get too long. The same arguments apply to stocks of raw materials, finished goods, warehouse stores, bins of spare parts, and so forth. They are all affected by exactly the same statistical considerations, and inventory theory seeks to determine how big these stocks should be and what are the APRO. 215. Priate policies for managing them for a given probability. With techniques of these kinds, decision theory can take its stand on prescribing a queue discipline or a reorder rule after the manager has prescribed acceptable probabilities of failure to meet the criteria of success. Once he says what these probabilities are, all the parameters of the network fall into place, and the system can be optimized to procure a minimal capital investment, for example, or a maximal profitability. But it is most important to take note of the case where, instead of prescribing these probabilities, the management decides to allow the stock levels to fluctuate of their own accord. Normally, this happens faute de mieux, in which case the fluctuations may be embarrassingly large and the investment involved may become uneconomic. All this can, however, be avoided if the control system underlying the entire operation is properly designed. This probably means floating a scientific model onto the network language in which the system is described. For example, a model may be taken from servomechanics, and the system designed to become self-regulating. For the point about any servomechanical system is that, when it is distributed, it goes into an oscillation of which the behavior can be measured. Basically, one of three things may happen. Either the oscillation will be amplified by the servo mechanism, so that stock fluctuations grow ever more wild, or the oscillation may simply be perpetuated, so that no one is ever quite sure what is happening, or the oscillation may be damped finally to disappear. This admirable outcome does not happen by chance, it is fully determined by the design of the servo-mechanical control. If, then, the OR model succeeds in identifying a set of communications and decision rules across the stochastic network which conform to the laws of servomechanics, the queues and stocks and inventories can be guaranteed to be self-regulating. In this case, the whole of the mathematical theory recently described can be brought into play. The system is running to an equilibrium whenever it is disturbed. Very well, we may calculate the economics of its steady-state behavior. Operational research has made good use of this model from time to time in the context of particular problems. More recently, however, the model has been extended to cover the entire operation of a business. The topic of industrial dynamics deals with this class of model. These are powerful tools indeed for any management. And the list of specialized OR techniques which belong to this genre may be expanded still further. For example, mention was made earlier of the technique of critical path analysis, which is of course just such an application of stochastic theory across a network, considered with statistical rigor. 216. Renewal theory concerns itself with strategies for replacing worn-out parts, machines, aircraft, or anything else that has to be renewed. This work depends on the notion of life cycles, and its terminology is roughly actuarial. Here are the birth-death processes which have been studied extensively mathematically, and which lead to policies for making replacements, and for undertaking preventive maintenance. These ideas naturally lead to the whole question of breakdowns and the way in which they influence the smooth running of any whole system. And breakdowns need not refer to mechanical failures on the part of production plant, they may refer to any kind of stoppage. For example, in the process of weaving, an automatic loom may be stopped by the breakage of a thread. Thus the amount of time lost in such a situation will depend on the availability of the relatively few operatives available in a large weaving shed, and a variety of decisions about the labor force and the production system itself will be determined by stochastic interactions. This leads to the theory of machine interference. Finally, at any given node in a network where there is an interplay of probabilities, a random fluctuation will be acceptable. But if something goes wrong, that is to say if the system goes out of control, these fluctuations may become dangerous and they will have to be detected. Decisions are required as to the correct moment for intervention and the correct action to take. All such cases are governed by the need to recognize when some fluctuation is no longer due to chance. In the simplest case, the techniques of statistical quality control are fairly familiar from applied statistics. At a more advanced level, there are the sequential decision techniques which consider not only individual instances of fluctuation, but accrue whole runs so that the moment of decision is recognized far more quickly than the unaided brain can possibly detect a significant change. There are indeed many highly developed ways of looking at this group of decision-theoretic problems, and there is a risk that their very multiplicity will persuade the skeptic that somewhat trivial notions are being proliferated here for the sake of effect. On the contrary, an entire literature exists for each of the theories italicized above, and there are many first-rate scientists working in industry who specialize in the application of these particular techniques to the exclusion of everything else. Their activities are confined and their lives may be boring, but it has to be faced that there is enough waste, enough lost production and lost profit, enough futile occupation, enough sterilized capital and labor, to keep an army of such scientists indefinitely and most profitably busy. 217. Algebraic approach. The third and last group of techniques of decision theory relies not on a geometric nor a statistical rigor but on an algebraic treatment of the network language. These techniques are the optimization methods par excellence. They may be summed up under the name mathematical programming. The original, and still the most potent of these methods in practice, is linear programming, which was discussed in Chapter 8. According to this, all possible permutations of the resources available to the management in a complex situation are connected to all possible outcomes. This can be viewed as a complicated and tangled network existing in as many dimensions as there are resource-outcome connections. Such a network of possibilities carves out a phase space within which the solution of the problem, good or bad, must inevitably lie. The problem is handled by the algebra of convex sets and, as was shown in the earlier example, an optimal solution to this allocation can be discovered given that the criteria of success can be properly formulated to create an objective function for solving the mathematics. But phase spaces are not always built up of a tangle of straight lines, and a network of curved lines can easily be envisaged. Such curves would represent the fact, for instance, that the relationship between the amount produced of some product and its profit-earning capacity is rarely linear. For the handling of such problems, more involved techniques of nonlinear programming have been devised. Now all these approaches are directed towards a static situation. Given that there exists a range of possible resources and a range of possible outcomes, the best connectivity between them can be found. It is not usual, therefore, to regard these approaches as offering a forecasting technique. On the other hand, the solutions they propose are offered to management as policies which they may adopt. If the management responds by altering its existing arrangements to conform to the optimal solution, then it is indeed expected that the profitability which has been computed will accrue. And this is what happens in practice. So the procedure does amount to a forecasting technique, and the solution is a prediction in the sense discussed in the last section. The sense in which we know what will happen has been pinpointed. The interpretation most definitely requires that the situation be static, or at least that any drift in conditions is slow and sure, so that its effects can be taken out of the calculation. The case may well arise, however, where the static assumption is obviously a wild oversimplification. Perhaps the situation is changing markedly and in a not very straightforward manner. In this 218 case, the technique of dynamic programming is used, for this is a form of the general technique especially adapted to the description of changing situations. These then are the main techniques of decision theory, arranged arbitrarily here in three groups for ease of understanding. Decision theory provides the engineering lore for building management policies within the architectonics of planned chance. It was said in the first section of this chapter that the most useful scientific language for discussing the networks that underlie all this is really the theory of graphs. Yet the mathematics of decision theory is not historically of this kind, as has been seen it is basically geometric, statistical, and algebraic. The answer to the implied question is that graph-theoretic approaches to or network description and manipulation have only recently started to acquire a coherent form. Clearly a network is a graph, and clearly a graph is a geometric entity. Also, a graph whose transitions are probabilistic is clearly a statistical entity. Thirdly, a graph which is unoriented is an algebraic entity. These viewpoints have been considered, and a fourth might well have been added, the graph as a logical entity, consisting of an arborescence of binary relations to be treated by Boolean functions. Now the modern mathematical statement of graphs is achieved with the help of the theory of sets, and it looks like subsuming all the other descriptions in one. All the techniques of decision theory can, it seems likely, be expressed in these common terms once the theory of graphs is more widely taught and understood. But these technical diversions, although important, should not hinder understanding of the general argument. The techniques of decision theory exist, and although scientists will eventually discover more economical and elegant ways of expressing them in a consolidated form, they exist to be used now. As a battery of weapons they have already proved themselves immensely useful, and indeed most of the literature of operational research is concerned with them alone. In fact, some authorities declare that operational research itself is simply a part of decision theory, since all is aimed at helping the decision taker to optimize, and since decision-taking situations exist in which cannot help at all. Yet in this book the matter has been dealt with in this one section of this one chapter. So definite a rejection of the popular view, and so cavalier a treatment of so wide a subject, merits some explanation. 219. 3. Against scientific impetuosity. Despite the technical brilliance of many of the decision-theoretic techniques, and despite the very large savings which they have brought about in practical industrial and governmental situations, classical decision theory suffers from three major limitations, one mathematical, one methodological, and the third pragmatic. From these small points consequences of some moment flow. It was said at the very beginning of this part 2 that the kind of science which is preoccupied with analytic method is not altogether adequate to the task of dealing with large and exceedingly complex systems and situations. It was indeed for this very reason that the whole theory of modeling and mapping was embarked upon. It is therefore rash in the extreme to charge at a real-life managerial problem, with an impetus derived from pure mathematical thinking which claims to have penetrated the nature of this problem in its generic form. Operational research is an empirical science, it is concerned with actual situations and not with idealizations of theme, and what is important to the manager may not have been present in the minds of those who developed the technique. Put dramatically, there is no point in making a coruscating scientific presentation of the reasons why a factory should be built at site A, if the manager has his eye on the trout stream at site B and his wife prefers the shops there. This is not at all to say that decision theory is of no use. But, as with every other kind of tool, one must know and understand its limitations. The mathematical difficulty and value theory. As was explained in Chapter 6, it is mathematically impossible to optimize more than one variable of a situation at a time. That is to say, when a mathematical model has been set to maximize profit, or to minimize cost, that is all that it can do. If the management has other objectives than this, they have to be handled by other means. In the limit, the really impetuous decision theorist will ignore these other criteria of success altogether, acknowledging to the management that he has done so. His recommendation is of the form, this is the program that makes the largest possible profit, I cannot guarantee that your employees will not immediately come out on strike, nor that your customers' goodwill will be retained, nor that the plant will withstand the battering I propose to give it, but you are the manager and had better take care of these matters. This is incompetent operational research, because OR is supposed to be giving the manager scientific advice on a policy which he can actually 220 follow. It is fostered partly by academic research, which sometimes forgets that OR is an empirical science, and partly by managers who feel that their prerogatives are usurped if the scientist is allowed to try and cope with all the facts. But it will not do, and we have to seek out ways in which the unidimensionality of the decision theoretic approach can be handled. The method usually adopted in practice, usually by people who have not thought much about it and who do not recognize precisely why they are doing this, is to prescribe constraints to delimit the phase space of a feasible solution so that the answer looks sensible. If an optimal solution to a production planning problem acknowledges a sufficient number of constraints about the way the labor force is used, then it is most unlikely that there will be a strike. If the optimal solution to a stock holding problem acknowledges the constraint that only one chance in 1,000 will be accepted of failing to meet an order, then the customer's goodwill is likely to be retained. If the optimization of a scheduling problem accepts the constraints put on plant performance by the most lugubrious of the maintenance engineers, then it is unlikely to fall apart at the end of the year. In this way, a large number of other desiderata appears to be met, although the optimization is quite strictly concerned with one variable alone, such as cost or profit. Considered as a solution of the problem as it was originally raised, however, this answer is trivial, bad science and actively misleading to the management. For of course it ignores the nature of the ramified system, it pretends to know the absolute boundary conditions of the system which are not in fact known, and not in fact absolute. The whole point about prediction within a ramified system is to be able to see how existing restraints will be moved in or moved out or utterly changed by an alteration in policy or environmental circumstances. So the approach freezes all the degrees of freedom which the system naturally has except one. And there is usually no justification for doing this. Sometimes, however, it is at these moments that decision theory comes into its own. Now it will have been noticed that of the restraints which surround a problem situation, some are of fact and some are of value. That is to say, that whereas the maximum speed at which an engine will turn before it blows up is accepted as a fact, the proportion of late deliveries which a customer will accept before he seeks a new supplier is accepted as a value judgment. For example, it is typical of a manager's life that he should have to take a decision between two clamant customers, each of 221, whom is demanding a service which only one of them can have. And yet this dichotomy between fact and value, when projected into an actual decision-taking situation which refers to the future, turns out to be invalid. In the manager's mind, the judgments he makes about value are as clearly facts of the problem as are physical limitations. The real nature of the manager's dilemma is not that he has to arrange a marriage of fact and value, as so many analysts presume, but that his decision is taken with incomplete information. What normally pass as facts and values are both ascertainable in a completely specified situation alone. Important decisions, which concern a fairly distant future, relate to conditions which are not completely specified, which is why there is a decision to take at all. The future circumstances which can so easily affect and change a value judgment can just as easily affect and change the facts of the case, because of the ramified system. Hence the criteria of success which are applied to a given problem are in very large measure arbitrary choices made by the management in the face of a large measure of ignorance about what the circumstances will really be like at the time. They are statements about how the decision takers envisage that they will be conducting themselves at the time when the decision becomes operable. For this reason, when a management group takes a corporate decision, it is probably solving a problem in social dynamics. The decision taken will be the one that minimizes the expected level of conflict. We are now in the field of value theory, the subject which attempts to bring managerial value judgments within the compass of decision theory. But it has already been argued that the distinction between fact and value is unreal in a particular practical context, and this makes the attempts to escape from unidimensionality somewhat unreal as well. For according to value theory, one should try to ascribe numbers to value judgments in order that they may be built into the decision theoretic model. There are various technical problems lying in wait, which there is no room to go into here. But overriding all problems of theory, comes the point that the whole approach assumes rationality in decision. Now the allegation is not that decision takers are irrational. It is to say that most important decisions are non-rational insofar as they contend with incomplete. 222. Information. The people who have gone furthest with the decision theory incorporating a value theory as a means of meeting the difficulties discussed above, seem to gloss over the arbitrariness of temperament. If decision can be lifted out of the emotive plane altogether, as some of them would claim, then there must be a way of measuring an appropriate risk which is independent of the attitudes of the managers who will be taking that risk. If not, then the managerial temperament has to be built into the model. This is sometimes done unwittingly by theorists who are not immersed in empirical or science.